Improve your C++ skills in this course on creating a music plugin with C++ and the JUCE framework. You'll learn how to set up your project, add DSP features, and build a custom GUI. Each section guides you through essential steps from basic setup to advanced audio processing. Charles from MatCat Music created this course.
Hey folks, we are back again with another C++ audio tutorial. Today, we are going to build this plugin from scratch using modern C++ and the JUCE framework. Check the description for links to the repository and to download the final build. Okay, what is this thing? This is the little brother of my new audio plugin and course for programming for musicians, where you can learn to build these other plugins, and also where you can learn modern C++ and the JUCE framework taught from the context of writing audio software in a mentored environment. In programming for musicians, you're not following videos, you're not learning from an AI chatbot, you're not watching someone else code, and you're not copying them either. You're coding it yourself from a design spec, and I'm reviewing your work every step of the way. All right, enough about those. Let's learn about what we're going to build today. This is a multi-effect audio plugin featuring the following DSP audio effects: Phaser, Chorus, Overdrive, LadderFilter featuring 6 different filter slopes, and a general filter that is switchable between the following filter types: peak, notch, band pass, and all pass. All of these effects feature a bunch of adjustable parameters such as frequency, depth, feedback, gain, etc. It also features a dynamic signal chain, meaning you can reorder the effects. If you want to filter the phased sound and then overdrive it, you can. If you want to chorus the overdriven sound and then filter it, you can. Simply drag the tabs around to change the effect order, and click the bypass button on the tab to disable that particular effect. We're going to learn how to implement the DSP reordering in a thread-safe way. We'll also build input and output gain controls, as well as input and output metering. The input gain is applied before any DSP processing, and the output gain is applied after all DSP processing. We'll build a responsive GUI that is intuitive to use, including disabling the sliders when the selected effect module is bypassed. Finally, we'll integrate the spectrum analyzer from Simple EQ and Simple Multiband Comp so we can see how our DSP is affecting the audio running through the plugin. We're going to build all of this from scratch and learn a bunch of C++ tricks along the way. Okay, that's the feature set for this plugin and for this course. My name is Charles. I'm MatCat Music on YouTube, Instagram, Threads, and X. Once again, check the description for links to the repository and where to download the final build of the plugin. Let's get started and write a multi-effect audio plugin using modern C++ and the JUCE framework from scratch. Welcome to Chapter 1. I'm going to be looking at this monitor over here, which has my script. So if you ever see me just kind of looking that way, that's what's going on over there. All right, here are some prerequisites your computer will need before proceeding. You already need to have Visual Studio 2019 or newer installed on your Windows computer, and that is not Visual Studio Code. If you're on Mac, you need to have Xcode installed. If you are on Linux, you need to have Make installed. You can easily download the installers for these build tools by Googling them. I am going to use Fork for Git repository management, and all screenshots of the repository will reflect that. You need to know how Git works at a basic level, meaning you should understand what branches are, what commits are, and the difference between staged and unstaged changes to a repository. Now, every time I mention committing a change in the tutorial that follows, it is assumed that you know you need to stage each file before you can commit the changes. If you need to brush up on your knowledge of how to use Git, use the following search query and watch one of the videos that pops up. Once you have installed these tools, proceed with the rest of the tutorial. Our very first job is to create a repository and then add JUCE to the repository as a submodule. This will be very different from most other tutorials that I have released, where we would first clone the JUCE repository, then build ProJuicer, and then create a project and a repository. This time, we will make the repo and add JUCE to it so that the project will be locked to a particular version of JUCE. Then we will build ProJuicer, then we will create our project. This approach solves the problem that occurred when someone would follow one of my video tutorials from a few years ago, which was made with JUCE 5 or JUCE 6, and then they would inadvertently clone JUCE 7 and end up experiencing a bunch of compilation errors because JUCE changed so much over the years. None of that is going to happen with this approach of adding JUCE as a submodule. So with that said, let's get started. Let's create a folder in our user folder in a directory called programming and name it project 13. Next, we need to create a repository in that folder. Use fork to do that. Open up fork. Create a new local repository from the file menu and then navigate to the folder that you just created. Select the project 13 folder you created earlier as the repository location. Fork will show your empty repository with no commits or branches, and the repository will be in a detached head state. That's what's going on. Now it's time for us to add a Git submodule for JUCE. To do that, open up your browser for GitHub, and we are going to navigate to, let's just search for it the easy way, GitHub JUCE repository. All right, that's this guy right here. Okay, click on the code button, click on this button right here to copy the URL, go back to fork, and now right click on submodules and add new submodule. And it'll paste all this stuff for us. Now JUCE has no submodules, but out of habit, make sure fetch submodules recursively is checked. Again, it's a good habit to get into. Right. Add submodule, it's going to clone everything now. You can see that going on right here. When it is done cloning, you will see two local changes. All right, here we go. Here's our two local changes. We want to commit this change to the repository. I'm going to write something like added JUCE and there it is. Next, we want to change JUCE versions. So cloning a repository will always check out the master branch of that repository. And sometimes we want to check out a different branch or commit. We're going to do that here in case the master branch of JUCE is on the wrong version of JUCE that we will be using for this tutorial. Right click on the submodule for JUCE and select Open JUCE. Now doing so will reveal the JUCE commit history. Now open tags and navigate to 7.0.5. That's the version we're going to use. Notice that in this view, the master branch is currently tagged with 8.0.6. In the future, commits that are on the develop branch, that's this branch way up here at the top, all these commits, these are all going to get merged into the master branch. And the master branch will be tagged with the next version of JUCE. So go back to commit version, commit that is tagged 7.0.5, right click on that and check out right here, 7.0.5, and check out commit. It's going to warn us that we'll be in a detached head state. That's fine. We're not going to be on the master branch anymore after. If you notice up here, the branch name is now detached head. The repository is in a detached state. If we were to make changes to the JUCE repository and try to commit those changes, we would not be able to. You can only commit changes to a branch, and head is not really a branch. It's just like you can tell which commit is checked out because the commit message is white and in bold. So now we can close the tab showing the JUCE submodule. And we see we've got one local change. In the Project 13 repository, if JUCE has newer commits than the commit that we're currently on, shown on the master branch, then fork will report a local change. That is what is happening here. All these commits, and we are way back. We're way back here on 7.0. So let's commit this change. We're going to stage this guy by double clicking on it. And I'm going to say something like checked out JUCE 7.0.5. Now that JUCE has been added as a submodule to our project, we can build ProJuicer and then create the project. So navigate to the submodules folder. That's over here. Go to Project 13, go to JUCE, go to Extras, then to ProJuicer, then to Builds. Look for your particular operating system. I am on Mac, so I'm going to go to Mac OS X, and then I'm going to open that project file. Once loaded, click the Build or Run button in your IDE to compile and build ProJuicer. This button usually looks like a play button. It could be under a product menu, Run, or Build for, or Build, or something like that. Let's wait for this to finish compiling. Build succeeded. All right. Once the build has finished, we need to launch ProJuicer. So we can either do it from here, or in our file browser, we can actually go to the build folder, debug, and then there will be the application if you're on Mac. If you're on Windows, it's going to be nested a little bit further. Just look for producer.exe. Okay. All right, let's run this. I had another version running. That's why that didn't launch already. Okay. Go to go to New Project, Plugin, Basic. Now we need to give it a name. We want the name Project 13. Change anything else except where it says Path to Modules. We want to change that to the JUCE Submodules folder. So Project 13, go to JUCE, go to Modules. Now you can click Create. And ProJuicer will ask you where you want to save the project. Now, ProJuicer wants to create a folder wherever you save the project, so you must navigate to the folder that Project 13 exists within and choose that folder. So in my case, I'm going to select the programming folder. I'm not going to choose Project 13 because if I did that, it would then create a folder called Project 13 here next to JUCE. So I choose the programming folder because that owns the Project 13 folder. ProJuicer is going to warn us about overriding existing files with the same name if any are automatically generated. Once saving is completed, you will see over here, you will see, there we are. Okay. You'll see your builds folder, you'll see your JUCE library code folder, you'll see your source folder, and you will see your project 13.juicer file in this. We need to add a git ignore file to ignore all of this stuff that was just automatically generated. So if you skip this step of forgetting the git ignore file, you're going to end up with a whole bunch of source code changes every time in ProJuicer you hit this button, because it's going to regenerate all of this stuff. It's going to regenerate everything in the JUCE library code folder, and it's going to regenerate everything in the Xcode proj folder, as well as, if you're on Windows, it's going to regenerate all of that stuff as well. Same for on Linux. So go to local changes and fork right here, right click on this builds folder and click ignore custom pattern. And then we're going to enter the following. We go */ builds with the capital B, */ JUCE library code, and then we're going to do */ .ds_store because I'm on Mac. This ds store file is the file that tells the operating system how to display everything in the folder. If we're doing column view, icon view, all that stuff, the way it's sorted, and we don't care about that, so we don't want to include it. Okay. So now if we click add to git ignore, notice this list gets really small, and all of the files in the builds directory and JUCE library code directory, they will all disappear from the unstaged changes list. And we are left with 4 source files, a git ignore file, and the juicer file as unstaged local change. Let's stage and commit these 4 files and write something in the commit field, added initial plugin project as the commit site. Our final step for this chapter is to navigate to github.com, sign in, and create a new repository. So I'm already signed in. I'm going to click this plus button to create a new repository. And you should use Project 13 as the name. Skip adding a README, license, or git ignore file. Now, it is your choice if you're going to make the repository public or private. I'm creating a public repository because this will be the finished repository for the freeCodeCamp tutorial. And I want people who are following along with that video to be able to consult this code base when their project doesn't work as expected. So I'm going to call this Project 13 freeCodeCamp. All right, create repository. We'll add a license file later. After the repository is created, connect it to your local repository by copying the HTTPS URL right here, or SSH if you know how to do that stuff. Copy it, add it to fork as a remote. So go over to fork, click on remotes, add new remote, paste it there. Be sure to test your connection. And if the connection test fails, you're going to need to add or check your GitHub credentials in fork. We'll go here. To set up your GitHub credentials, just go to the fork, go to accounts, and then this is where you can set up GitHub, Bitbucket, and it'll take you through OAuth to do the authorization system. All right. Okay, the next thing to do is right click on this guy and choose Push Master to Origin. Now go back to GitHub, refresh your page, and you'll see there's your project. So you can clone your repository on any computer. You can then build ProJuicer from the JUCE submodule folder, and then open your project and get to coding without worrying about if the computer has other versions of JUCE installed. Project 13 is now all set up and ready for us to begin. In the next chapter, we will add Simple Multiband Compressor as a submodule. The Simple Multiband Compressor project has a few classes we will reuse later in this project. Welcome to Chapter 2. Our next task is to change C++ versions. And pull a ProJuicer. Change C++ versions to C++ 20 and add the Simple Multiband Compressor as a submodule. The Simple MB Comp submodule will provide the GUI widgets for this project. Simple EQ, Simple MB Comp, and this project all have a similar aesthetic. To change C++ versions, navigate to the following page in ProJuicer by clicking this little gear icon right here. Now scroll down until you see C++ language standard. That's right here, and change it to C++ 20. If you are on Xcode 9 or newer, you will need to add a compiler flag to enable C++ 20 usage. So navigate to this page over here under Exporters, Xcode, Debug, and go to Configuration Specific Compiler Flags. And here you're going to type in -std equals C++2a. Do this for both the debug and release versions. Okay. If you are on Windows, you need to add a different compiler flag. That flag, again, go to Debug, scroll down to Configuration Specific Compiler Flags. That flag is /std:/C++20. Do this for both debug and release. All right, go ahead and save that. Next, we need to add the Simple Multiband Comp project as a submodule. This repository will give us the code for the rotary sliders, some DSP helpers, the FIFO class, and the spectrum analyzer. Here is the URL. It's github.com/macapmusic/simple-multiband-comp. So visit that URL page, and then click the code button, click the copy to clipboard button, go back to fork, and then add this as a submodule. Right click on submodules, add new submodule. It's going to paste the URL automatically for you. Be sure to check fetch submodules recursively, and then click add submodule. That's going to clone it. Once added, you're going to commit these changes that we just made to the repository, adding a new submodule and changing the C++ version. So I'm going to add that here. Added Simple MB Comp submodule, and then change to C++ 20. All right, so go ahead and commit that. We will add files from this Simple Multiband Compressor repository later when it's time to use them. Go back to ProJuicer and click the Save and Open in button. Click the Save and Open in IDE button. It's this guy right here. And we're going to start coding next. Our first job is to add some basic DSP. We'll figure out how to change the order that they are processed in later. Let's go to pluginprocessor.h and add the following enumeration. Let's see, let's get rid of this part. Let's make this bigger. Okay. Add the following enumeration below set state information, right here in the public section. Enum class DSP underscore option. And our choices are going to be phase, chorus, overdrive, LadderFilter, and then end of list. I always like to do end of list because it makes it easy to know how many elements are in the enumeration. Next, we need to create DSP instances of each of these classes. The JUCE DSP module provides classes for us that can perform the signal processing for us. To use them, we must add the JUCE DSP module to our project. So go to ProJuicer, then go to Modules, then click the plus button and add the DSP module. Global JUCE modules path. Now if we go to it, we'll see our path is JUCE/modules, just like all the others. All right, save and open in IDE. Now you should see the DSP folder here on the side. These are all the JUCE DSP stuff. All right, let's add the following code to the private section in Plugin Processor. Let's move this up here. Okay, JUCE DSP Phaser, and it's going to process floats. It's called a phaser. Same thing here, JUCE DSP Chorus, float, chorus. Now we've got our overdrive and our ladder filter. Those will both use the ladder filter object. JUCE DSP ladder filter, float, overdrive, ladder filter. Okay, so we've got our phaser object, our chorus object, our overdrive object, and our ladder filter object. Compile the project to make sure that there are no build errors. Oh, build failed. Cycle inside a single target building could produce on. What an odd error message. All right, we've got a build error. I spent some time in the background figuring out how to solve it, so I'm just going to take you through that process very quickly. What needs to happen is we have to switch to the latest version of JUCE. When I originally made this tutorial in 2023, this issue with the cycling thing did not happen, but now we are in 2025. Xcode is at a new version. I'm sure Visual Studio has had a bunch of updates as well. Anyway, let me take you through this process. It's pretty simple. Okay, first things first, go to fork. First things first, quit ProJuicer, because we're on 7.0.5. All right. Open up your JUCE submodule right here, open JUCE. Okay. You want to navigate to 8.0.6 right there. You want to check out 8.0.6. Next step is to build ProJuicer again. Okay. So go to your builds folder. I'm sorry, this is in the JUCE folder, extras, ProJuicer, builds. For me, it's Mac OS X. For you, it might be Visual Studio 2019, 2022. Not sure which version. And then open up ProJuicer.xcode. Okay, now we need to compile it. This is going to build version 8.0.6. Okay, we're currently compiling this version of ProJuicer. All right, that has compiled, so we can close the project. All right, now go back to our juicer file for project 13. Open it up. Now we can see we're on 8.0.6. Now you may get a warning here that your global paths are not correct, in which case you need to change the path to JUCE to point to the version of JUCE you're currently using. In our case, we're using 8.0.6. I have another version on this hard drive, and that's what this was currently pointing to. That's what the global path was. So I'm going to just click this button right there. I'm going to navigate to my project. I'm going to navigate to my JUCE folder. I'm going to navigate to the, I'm going to navigate to the JUCE folder, choose open. That's where the path to JUCE is. And then for JUCE modules, I'm going to do the same thing. Navigate to my project, project 13, navigate to JUCE, navigate to the modules folder. All right, that will clear that warning. That warning will appear right down here in this corner here. Okay. Save and open in IDE. Okay, it's going to complain about that, but then just do save and open one more time. All right, now this is fine. Do a clean, full project clean. Now try to compile. It's still saying build failed because we didn't change the compiler arguments. So go back to ProJuicer, go to your debug exporter target, get rid of that compilation flag, do the same for release. And for Visual Studio, I don't know if you have to do that, but give it a shot, maybe. Save and reopen. All right, now try compiling. And let's go here. oops, this one here. And it's currently building the audio unit version. And actually, let's stop that and let's do build all. This is going to build the AU, the VST3, the standalone version, and then any shared code. All right, let's do that. Linking. All right, build succeeded. Okay, great. So now that that's compiled, we can commit our change. So let's go back to fork. Let's go back to our project, and we can see that we've got a change to the juicer file. We can see that we've got a change to JUCE as well. So let's do that first. This will be the first thing. I'm interrupting my process a little bit because at this point in the repository, when I found this error, I had to discard everything, including those changes we made to the code. So that's why those are not showing up here. So let me just commit this stuff and say change to JUCE v 8.0.6 and commit these two files. And now let me restore the code that got discarded. Waiting for this to compile. All right, build succeeded. Let's commit that. This is where we will start from in the next chapter. And my commit message is going to be added basic DSP, not prepared or used, as in we haven't used the prepare to play function to initialize our objects, and we're not using any of those objects in the process block function. Before we write any more code, we need to set the run target. We're not going to be feeding any audio into our plugin until later in the project. For the next few chapters, we're going to be implementing some basic stuff that doesn't require running audio through the plugin. So for that, we just need to use the standalone version. In Xcode, you change it here. You just click this thing and then go to standalone plugin. In Visual Studio, the project defaults to launching the standalone version. I have a screenshot here showing this thing. It's taken from the simple multiband compressor tutorial. But you don't have to do anything if you're on Windows. With that said, let's dive in. Now, all choices in the enumeration we just created, that's this thing right here, they will be available as DSP choices in the signal processing. Since there will be a fixed number of choices and the only thing that will change will be the order of them, we can store the order in a fixed sized array, where the size is defined by the number of items in the enumeration. We get this size value for free when we stick something like end of list at the end of the enumeration. After the enumeration declaration, add an array alias as follows. Using DSP Order equals std array DSP option, and then we cast to DSP end of list and template off. All right, now we've got our alias. We will leverage how enumeration elements can be converted into numeric values to provide the size for us. More information can be found here. Take a look. I am using this alias because it makes the code shorter and cleaner than having this exist in the code base. So next, let's declare an instance in the private section. We'll put that before our DSP objects. So DSP Order. Now we have an object that we can interact with in process block that will tell us the order that the effects will be processed in. Let's write a class that will have a unified interface for all of our DSP instances. This class will be a wrapper class. This class is going to inherit from JUCE DSP processor base. We will need to implement the 3 virtual functions, and this class will also be templated so we can use it with any type that we want. Let's take a look at this class, this processor base class. So you can see it acts as a polymorphic base class for all processors. This exposes the same set of methods that a processor must implement as virtual methods so that you can use the processor wrapper class to wrap an instance of a subclass and then pass that around using the processor base as a base class. So we've got our prepare function, our process function, and our reset function. Let's punch that in over here. Let's see, we're going to just put this in the private section. All right. Here is the basic templated class with no implementation. Let's make sure this is in the private section of the audio processor below the DSP order declaration. And the next thing we have to do is add a DSP instance to the templated class and interact with that instance in each of the member functions. As a starting point, we will simply call the same named function on our DSP instance in each of these member functions. That looks like this. So DSP, DSP, there's our DSP instance. And then now in each of these functions, we just call the function with the same name. So DSP.reset. For this one, it's also just DSP.process, context. And then for prepare, same thing here, DSP.prepare spec for the process spec. The beauty of this approach is that we can create custom DSP types and also customize what happens inside each of these member functions if needed. And when it's time to use these classes, we can stick pointers to them in an array, which is explained further down in the tutorial, and loop over the array to call the member functions easily. For example, let me just go to a listing. I'll just do that here. So for example, we could say for auto pointer DSP instances, we can then do like pointer reset. This will reset all of the DSP instances. And then, or we could do pointer process with our context if we make one, or we could do pointer prepare with our spec like that. This is what this approach over here, creating this generalized base class, gives us. We can stick a bunch, we can make this DSP choice wrap around these guys and then stick all of these in an array, and then we can just process them as needed. Back over here. Now that we have a consistent interface, we can update our DSP instances to use this class. So delete the old instances and replace them with the following. All right, so we've got our DSP choice, and the template parameter is going to be the previous object. Before it was just JUCE DSP Phaser, and now we're wrapping it in a DSP choice. And we've also added a delay line as well. Finally, we want to add an array of pointers that is the same size as our DSP order object. This array will store pointers to each DSP instance and also store them in the same order that the DSP order object is storing them. We'll write the synchronization a few steps from now. This array type will have a long name, so to keep the code concise, we will write an alias. Let's do this down here. Using DSP pointers equals std array JUCE DSP processor base pointer, and then static. It's this same thing here. We're doing this same size again, and close it off and semicolon. Let's compile everything to make sure there are no build errors. All right, during compilation, you'll notice that there's a warning about an unused variable in process block. Let's go take a look at that. This loop in process block is meant to be a starting place for new users of JUCE. You can delete this chunk of code completely. If after you do that, if you then try to compile it again, and if your build succeeds and the warning is gone, go ahead and commit the changes. Here we go, project 13. There we go. All right, project 13. We can say created base class for all DSP to provide unified inter. All right, stage that guy and stage that. Commit. All right, in the next chapter, we are going to set up the FIFO that will allow us to customize the signal processing order. All right, this step is going to be short. We are going to be incorporating the FIFO class from the simple multiband compressor project into this project. So let's go over to Producer. Our first job is to add the necessary header file from simple multiband compressor into Producer. So step one is to create a new group in source, add new group called DSP. Next, right click on that folder and select add existing files. All right, now navigate to the simple multiband compressor, source, DSP, FIFO, and choose the FIFO.h. You should see this now in Producer where you've got the DSP folder and then FIFO.h. Next, we want to make these files easily accessible without having to type the relative path whenever we need to include them. To accomplish this, we need to add the simple multiband comp source, GUI, and DSP folders to the header search path. It might take you a moment to type the right path into this field, but when it's done correctly, the whole point, let me show you, let me just demo the whole point of this. Okay, right now, if we want to use that FIFO, we have to do it this way. Include, remember where that file is actually stored. The file is actually stored relative to this folder. We go up a level, then go into source, then go into DSP, then go into there. And that's annoying. We have to go .. Do we have anything there? Let's see, loading completions. Right. We have to go to simple multiband comp. Then we got to go to source. Then we got to go to DSP. Then we got to go to FIFO. That is annoying. We don't want to have to remember to type all of this. That's super annoying. So instead, what we want to do is the following. And it might take you a couple times to get this right. You'll have to just build accordingly. Where is Producer? Okay. In Producer's export settings, you're doing this in the header search path for both debug and release. This is where you want to put .. Maybe you got to do it one more time, because the reason is that the export path is actually built from the builds folder. And for me, it's on Mac OS X, so we got to go up one level. Yeah, we're actually in this directory. We go up one level to Mac OS X, up one more level to builds, and now we're in this directory. And that puts us in simple multiband comp. That's what we got to do .. twice. So then we do simple simple multiband comp, and then the source folder, and then do it again for the GUI and DSP. GUI? Okay. You'll do that in the same place in your Visual Studio. You may have to adjust the number of dots and slashes. Each .. corresponds to one directory up higher. As in, if I'm in, if I'm here in the build folder, to go build and then .. takes me to this folder, the builds folder. And if I go .. again, then I'm in this folder, which has all of this stuff. So just keep in mind on that when you're figuring it out. Also on Windows, they use / going in the other direction, as in .. like that. So just be aware of that stuff. Experiment with it to find out what works. Once you've done this, save and reopen in Producer. Save and reopen in IDE, and now try to include your FIFO. Include FIFO.h. Try to compile. And if the header search paths are correct, the project will compile successfully. All right, build succeeded for me. Awesome. Once you have a successful compilation, it's time to add a FIFO instance to our audio processor. Now, most of the classes in the Simple Multiband Comp project are inside of the Simple MB Comp namespace, so you'll need to type Simple MB Comp first, followed by 2 colons, before you'll see the autocomplete pop up for the FIFO. And do this after the DSP order instance, and it needs to be public as well. So declare an instance of the FIFO, Simple MB Comp : This is going to give us all this stuff. Let's see. Loading completions. There's our FIFO. Okay, and the type that we want to use is DSP Order, and we're going to call it DSP Order FIFO. Now try to compile. If the compilation succeeds, commit the changes that were made to Producer and plugin processor. All right, and my commit message is added DSP Order FIFO. Next, we are going to add sorting and processing of the DSP pointers in process block.
Hey, if you like this tutorial that you've been following along with and have been wishing for a written version, check out the link below. You'll find this course as well as my other courses, all available in written format. They're full of detailed explanations, code snippets, and more. Each chapter is crafted to be easy to read and easy to follow. Complex features and ideas are turned into simple concepts with clear code snippets. You'll progress quickly as you elevate your app and plugin making skills by working through these projects. Programming isn't hard, it's just taught wrong. All right, let's get back to making this plugin.
All right, in this step, we will convert our DSP order instances pulled from the FIFO into an array of pointers that we can then process in process block.
All of the code that we will be editing in this step will occur in process block, which is found in pluginprocessor.cpp. Our first step in this is to declare a function local instance of the DSP order that the FIFO can pull into, and then actually pull into it. Okay, so do this after this for loop. So auto new DSP order equals DSP order. Thank you, alias. Awesome. And then now try to pull it into it. Try to pull while DSP order FIFO dot pull new DSP order. If we succeeded in pulling, we need to refresh DSP order with this new instance. That goes here. If you pulled, replace DSP order. Again, we're just doing state management at this point. If new DSP order does not equal the old one, or if it doesn't equal the default one, then we can say DSP order equals new DSP order. The reason we're doing that is because here is where we create a default instance. If our DSP order did not change because we failed to pull, then there is no need to update the member variable. Now our job is to convert the enumeration values in this DSP order object into pointers to our DSP objects. So first declare an instance of the DSP pointers object, DSP pointers, DSP pointers. Let's just add a comment. Now convert DSP order into an array of pointers. All right. Next, loop through the individual elements. DSP pointers and DSP order have the same size, which makes looping possible. And depending on the value of DSP order at index I, assign the address of the appropriate DSP choice instance to that same index in the DSP pointers array. That looks like this. For switch on it, DSP order. Let's wait for autocomplete and fix that indentation. All right, if it's a phase, then we want to say DSP pointers equals the phaser. If it's a chorus, same thing, DSP pointers. All right, we can copy and paste this. And then JAssert false for this one. All right, if it's overdrive, then we got our overdrive. And if it's ladder filter, then it's the ladder filter. Okay. Now that we have our DSP pointers list, we can create an audio block and a context and process them. Let's add that here. Now process. Scroll this up. Okay. Auto block equals JUCE DSP. Audio block. Float. And this is created from the buffer. Then we've got our context. DSP. Process context replacing. Audio block type is going to be that. So this is a float type, and our block type is going to be our block. Now we can loop through our DSP pointers. For size ti equals 0, I is less than our DSP pointers size. Now, if we always got to make sure that our pointer is not null, DSP pointers is not null pointer. Oops. Now we can do our processing. DSP pointers process with our context. Now try to compile. Build succeeded. All right, if your build succeeded, commit those changes. All right, and my commit message for this is added sorting and processing of DSP pointers. Next, we will add TODOs and begin setting up the APVTS so we can control our DSP with audio parameters. let's create a list of things to implement in the plugin. I'm going to add these as comments prepended with // to do : in process block. Now, they could be placed anywhere in the code base though. Xcode shows comments in the function list of a source file if you prepend the comment with // to do, which is helpful. Now here's the list that I have come up with here. All right, before our additional code, I'm gonna put that right here. So to do, add the APVTS, create audio parameters for all DSP choices, update the DSP here from audio parameters, that's here in process block. We needed to save and load our settings. We need to save and load the DSP order. We want to have a drag-to-reorder GUI. The GUI designed for each DSP instance. Metering, we need to prepare all of our DSP. In the bonus version of this course, I do wet, dry knobs. I do mono and stereo versions. The mono version is the bonus. This version we're building here is stereo. We will have modulators for all of the DSP. We're going to have thread safe filter updating in the bonus content, and then pre and post filtering in the bonus content, and then a delay module in the bonus content. All right, so some of these items will be saved for the bonus section of this tutorial. This list does give us a good starting point to figure out what to implement first and what to wait to implement, because it depends on other features being implemented first. So here's an example of what Xcode's function list in the source editor shows when these to-dos are added. You can see that they're all added here now. All right, like I said, it's a pretty useful feature to put, // to do : and then write the thing you want to have, because it means it shows up here in your actual function list of stuff to work on. Let's commit this list of to-dos to the repository once you get it added. And we'll say this is added to-dos. Like you can see, our project is coming along. We've got a pretty decent supply of things that we've done. All right. Now that we've got a to-do list, let's tackle the first item, add the APVTS. Let's go look for that. Okay, here is the header file for the audio processor value tree state. Let's just take a look at what this thing says that it does. As a general overview, the JUCE audio processor value tree state class is used to store audio parameters for the audio plugin, and henceforth I'm going to be referring to it as APVTS. Let's take a look at this documentation. This class contains a value tree that is used to manage an audio processor's entire state. It has its own internal class of parameter object that is linked to values within its value tree, and which are each identified by a string ID. You can get access to the underlying value tree object via the state member variable, so you can add extra properties to it if necessary. It also provides some utility child classes for connecting parameters directly to GUI controls like sliders. We're going to make use of that. The favored constructor of this class takes a collection of ranged audio parameters or audio processor parameter groups of ranged audio parameters and adds them to the attached audio processor directly. All right, so as you can see, this is a pretty handy class for our audio processor, handling a lot of parameter management tasks for us. And per the class declaration, we need to declare a function that produces a collection of JUCE ranged audio parameters and use that function to provide the collection of parameters to the favored constructor. The favored constructor is, where is that? That is this guy right here. So since this function is not going to use any member variables of our audio processor, it can be static. Let's get this guy going. This function is going to return a JUCE APVTS parameter layout instance, and we're going to call it create parameter layout. Let's do that here. Static JUCE audio processor value tree state parameter layout, create parameter layout. Okay, there's our static function. Now we can declare an instance and call this create parameter layout function in the constructor argument list. So we go JUCE audio processor value tree state APVTS, and it needs to be instantiated with a reference to the audio processor we want to use. So that's going to be this. Then it's going to be the undo manager we want to use. We currently do not have one, and it wants a pointer, so we can just pass null pointer. It wants the value tree type, and I have no real thoughts about that, so I'm just going to call it settings. And then we need to pass it our parameter layout. So we pass it a call to this function. Call this function here because the output of that thing is going to provide the parameter layout that it's looking for. All right, now we need to implement create parameter layout. So go to plugin processor.cpp. And in order to make this work for right now, we just need to create an implementation that declares an instance of parameter layout and returns it. I'm going to put this right above process block because that's where my cursor is. So we go JUCE audio processor value tree state parameter layout, and then the name of our guy, which is Project 13 audio processor, create parameter layout. Now we're just going to declare one of these guys called layout and return it. We'll fill in this later. Try to compile. If compilation succeeds, we can mark our first to-do item as done. And sure enough, it's gone from our to-do list. Let's commit this change. Added APVTS. Commit. All right, our next task will be to start adding audio parameters to enable control of the DSP units. We're going to start with the phaser parameters. All right, let's dive in to the next part. We're going to add some audio parameters for the phaser class. So let's take a look at that in the documentation. Phaser. There it is. All right. Okay, so let's take a look at some of the parameter choices we got. Number one, we've got the rate, which is in hertz. We've got the depth from 0 and 1. We've got the center frequency, which is also in hertz. And then we have the feedback amount between -1 and +1. And then we have a mix control from 0 to 1. All right, so let's create some cached audio parameter pointers for these parameters. Caching them like this allows us to have easy access to the actual audio parameter. And the audio parameter is normally accessed via name lookup using APVTS get parameter with the param name, which is kind of slow. We will need to use them when we create our GUI, so put them in the public section of your audio processor class. I'm gonna put them right below the, I'm putting them right above the private keyword. So let's see, we've got our, let's look at this list right here. Let's just make a note of what we can do. We can do, so we've got our phaser, and this is the rate. This is in hertz. We've got our depth from 0 to 1. We've got our center freak. This is also in hertz. We've got our feedback from -1 to +1. And then we've got our mix from 0 to 1. All right. Here we go. Let's create cached audio parameter pointers for each of these parameters. And we're going to use JUCE audio parameter float for all of these. So JUCE audio parameter has a capital P, float. There's our pointer. And then phaser rate and the unit, just to make it easy to remember. We'll initialize it to a null pointer. Let's do this again for all of the others. 2, 3, 4, 5. All right, this one, oops, capital H. We'll do center freak hertz. Let's see, what do we want to do next? Let's do our depth percent, because it's from 0 to 1. Let's do our feedback percent, and then we can do our mix percent. All right, so We have our rate in hertz, we have our center frequency in hertz, then we've got our depth from 0 to 100%, feedback from negative 100% to positive 100%, and then our mix from 0% wet to 100% wet. If you're an audio person, you know what the wet-dry percentage amount is referring to. If it's 100% wet, you're getting nothing but the affected signal. If it's 100% dry, you're getting nothing but the unaffected effect signal. All right. Next, we need to create and add audio parameters to the APVTS, and then initialize these cached audio parameters from the real audio parameters that were just added to the APVTS. Our first step is to create some functions that produce parameter name strings for us. And then each function needs to return a string that represents the parameter name. Let's stick these at the top below our include definitions in pluginprocessor.cpp. Let's go all the way up to the top. We'll stick all these guys right here. All right, there's our rate name, Phaser rate hertz. Each of these is just returning a JUCE string. We got our center freq name. We got our depth name, percentage, feedback, amount, mix name. Okay. Next, we can declare parameters in our create parameter layout. Let's jump to that guy. Parameter layout. Here is the pattern that I'm going to be using. Let me just put this pattern here. I'll just get this pattern on screen. It's going to be in pseudocode. But this is going to be a pattern. It's going to be, here's the name we're going to use. Here's the name function that's going to provide the name. And then we're going to add the parameter to the layout using the name. We're going to have a parameter range. We're going to have a default value. We're going to have a unit suffix. Version hint is going to be the version number associated with the parameters that we're creating. This is related to some stuff that Apple is requesting that plugin developers apply for the purpose of legacy audio unit compatibility. There's more info right here in the comment explaining version hint in this paragraph. Let's see where that is. That is in parameter ID. That would be here. JUCE parameter ID. Let's see, where is that? We want JUCE parameter ID, actual source file. You know what? Let's just search. Is it audio basics? Audio processor parameter with ID. So I know it's related to this. Class parameter ID. Here we go. All right. Version hint influences parameter ordering in audio unit plugins used to provide backward compatibility with audio unit plugins in Logic and GarageBand. Okay. That was a huge tangent. That was totally unnecessary. All right. With this pattern in mind, let's add 5 audio parameters to the APVTS parameter layout inside of create parameter layout, 1 for each of the parameters. I'll do the first one, then I'm going to copy and paste the rest. So we go auto name. First of all, let's do const int version hint equals 1. All right. Now let's do our phaser. And we can go back over here, copy this list down. Let's cut that. All right, here's our phaser. Okay, we'll do our LFO rate first. So auto name equals get phaser rate name layout dot add, and then we'll do we're gonna do this thing. std make unique JUCE audio parameter float. Oh wait, let me do that again. We want our parameter ID, normalizable range. Yeah, we'll do this. Okay, now let's put these all on their own line. All right. Okay. Let's begin with, oh, you know what? This is missing the suffix. We want that thing. Yeah, let's see. We got our, all right. Let's make this first. Here's our JUCE parameter ID. And this begins with the name and the version hint. I'm going to put this over here and just indent this because I know my face is over here in this lower right hand corner covering up this stuff. All right, parameter name. Now let's build our normalizable range. JUCE normalizable range. We got our range start, range end, interval value, and skew factor. It's way to the left so we can see all the pieces of it. All right, this is going to be a float. Range start. It's going to be 0.01 float. Range end 2.f because we want it to go from 0.01 hertz up to 2 hertz. Usually phasers, they have pretty slow phasing of the signal. All right, our interval value will be 0.01f, meaning we can go from 0.01, 0.02, 0.03, all the way up to 2 hertz. And our skew factor, we're just going to keep it right in the center and do 1. Our default value will have a default of 0.2 hertz. And then there is the last thing, the unit suffix. So we'll add that as the last parameter way over here. And we're going to do hertz like that. All right, this is our first one. Okay, so this is our LFO hertz right here. I'm going to copy and paste the next ones for the sake of time. This is going to be phaser depth, then center frequency, then feedback, then mix. Here's phaser depth. Put these way over here. This one has the default value of 5% or 5/100ths. So the phaser, it's not 100% wet. It's not super phasey, that sort of thing. All right, that's phaser depth. This goes over one more. All right, let's do our phaser center frequency. All right, let's do our phaser feedback. This has a default value of 0, as in no feedback. A range of -100%, +100%, in steps of 1%, a default value of 0. All right, and then finally we've got our mix. How much phaser sound do we actually want to hear? All right, so we've got from 0.01 to 1% to 100% in steps of 1% with a default value of 5%. Okay, let's try to compile, make sure we don't have any build errors. If we do, be sure to fix them before proceeding with the next part of the tutorial. All right, build succeeded for me, hopefully as well for you. Our next task is to initialize those cached audio parameters here. That's these guys. So we are going to initialize them in the audio processor constructor. Let's go up to that. I'm going to use an array of pointers to these variables and an array of pointers to their associated name creation functions. These two arrays will be the same size, which will allow us to loop over each of these arrays and streamline the initialization process. The first array will contain pointers to the cached audio parameters. That looks like this. Auto params equals std array. Whoops. And then here's where we go. Phaser rate hertz, and we'll do the rest of them. All right. The second array is going to contain function pointers to the name functions for each of these guys. Auto phaser funcs equals std array, colon that, get phaser rate name, center freq, phaser depth name, phaser feedback name, get phaser mix name. Okay. Oh, be sure to not call them invoking those functions. We want the address of the function itself. Okay. Finally, we're going to loop over them to extract the audio param pointer from the APVTS and initialize our cached pointer value. That looks like this. Make our loop. Auto pointer to param pointer equals phaser params I. All right, now we're going to call apvts.getParameter, and our name is going to be the phaser func. We're calling the appropriate phaser func, executing it. Give some space so we can see what we're doing. Then this parameter here, this is going to return a parameter, and we are going to cast it to a JUCE audio parameter float. So dynamic cast audio parameter float. This guy here, it's a pointer. All right, and now that we've got this, we're going to assign this to our pointer to param pointer like this. PTR to param pointer equals this. And then the last thing we want to make sure is that our name lookup and retrieval actually worked, and we do that by saying that jassert PTR to param pointer is not equal null pointer. All right, the loop works like this. First, we get one pointer to an audio parameter from the container. That's what this line does right here. Next, we use one of the phaser functions, one of the phaser name functions, to produce the name of the audio parameter. That's this part right here. Then we pass that name to the APVTS get parameter function, and then we dynamically cast the returned pointer to an audio parameter float and assign it to the cached audio parameter. That's what this does. That's what all this dereferencing is doing. And then finally, we confirm that the cached audio parameter is pointing to a valid audio parameter. Remember, we took a pointer to these cached audio params. We're dereferencing that to get the cached audio param, and we are making sure that that cached audio param is not a null pointer. Now, it's very important to make sure that the parameter being initialized is not a null pointer, hence the JAssert at the end of this loop. All right, so be sure to compile this to make sure that you don't have any errors, and then if it builds, run it. And if it runs without hitting this JAssert, we don't care about any other JAsserts, we just care about this one in the constructor. If we succeed in that test, then we can commit these changes. We only care about this one being hit. All right, awesome. So it didn't hit that constructor JAssert, so we can go ahead and commit this. For me, it's hitting this JAssert in the Phaser class because I haven't prepared the Phaser instance in the prepare to play function. We're going to initialize a few more audio parameters for some more of the DSP class instances that we've got before we start preparing the DSP, so get used to hitting these JAsserts in the DSP classes whenever we run our project. The whole point of running them is just to make sure that this check in the constructor is not being triggered. All right, see you in the next chapter. All right. Chapter 9, we are going to follow the same pattern that we used when creating the Phaser Params. We're going to create functions that generate the parameter names. We're going to create the audio parameters. We're going to create cached pointers to those audio parameters, and then we're going to initialize those cached parameters. Let's begin with some recon about the Chorus class itself. Let's go to JUCE Phaser here. Let's go look for this to JUCE Chorus. All right. Now let's see what our types are. Okay, we've got our rate in hertz. We've got our depth between 0 and 1. We've got our center delay between 1 and 100. Feedback from -1 to 100. And then we've got, from -1 to +1. And then we've got our mix from 0 to 1. All right, so let's do that same thing we did in create parameter layout for the Phaser. Let's go to the function here. We're going to do something really similar to this. Okay, let me go ahead and turn off, kill the plugin as it's running. Hide this. All right, we'll go down here below the Phaser stuff. All right, we'll change this to say chorus. So our rate is again in hertz. Our depth is from 0 to 1. We don't have a center frequency, we have a center delay. And this is going to be in milliseconds, 1 to 100. And then we have a feedback from -1 to +1 and a mix from 0 to 1. All right, let's create some functions that produce names for each of those parameters. Go way back up to the top, stick these below the Phaser function names. We know we've got our rate, we've got our depth, we've got our center delay, our feedback, and our mix. So let's just copy this and make some edits to that. All right, so this is going to be get chorus rate name. Chorus rate hertz. All of these that say that, we're going to change that to chorus. All right, so instead of chorus center frequency name, let's put that down here. We've got our depth name. We'll change that to be chorus depth. We've got our chorus center delay. That'll be this one, chorus center delay name. Center delay in milliseconds. And that should be our third parameter because it's the third. That is the third choice here, center delay. All right, then we've got our chorus feedback name, and then we've got our chorus mix name. All right, those take care of the name generation functions. Next, let's declare pointers to the parameters. So head to plugin processor.h. We go up to these guys right here. We're gonna duplicate this and paste it right below it, and first of all, change all of these that say Phaser to chorus. And then we just need to change, let's see, center frequency is the one that needs to be delay milliseconds. And we also want this one to be in the same order as the functions that we had over here. So rate, depth, delay, feedback, mix. So rate, depth, delay, feedback, mix. All right, these are in the same order as the naming functions. All right, let's compile just to make sure we don't have any errors. All right, build succeeded. So let's commit this change very briefly. Oh, I'm sorry, I forgot to commit this change here for the phaser stuff. Let's do the phaser ones. Just stage only that. Here's the phaser ones here. Stage that, and stage this stuff, not that part. All right, so this is added Phaser Params. I may have shown that in the previous chapter. Could be a little continuity error, we're not sure. It's fine. All right, so those are the Phaser Params. Now let's do this part. These are the Chorus Params. Okay, so added cached params and name funcs for Chorus Params. All right, let's make a minor change to the names of the array variables in the constructor that are initializing the cached params. All of the phaser variables currently being initialized are JUCE audio parameter float instances. The Chorus params are also JUCE audio parameter float params. So let's change the name of the arrays and functions to reflect this, indicating to the code reader that these are generic arrays that hold float-related pointers. Specifically, instead of phaser cached params, we're actually going to call them just cached params, or just float params, like that. And these are just going to be name funcs, or float name funcs, like that. And then we update our loop here. So let's do float params there, float params there. Then our float name funcs, we change phaser funcs here to that. Let's compile to make sure there are no build errors. All right, build succeeded. All right, let's commit this little refactor. Revised how cached float params are initialized to include all existing float params. It's a super long message, but that's all right. All right, now we can amend our array lists and create our parameters and initialize our chorus cached audio parameters correctly. So we'll do the cached audio parameters first. We'll do this initialization process, and then we will just work our way down plugin processor.cpp. So starting up here in the constructor, let's add our chorus, our chorus params here. I'm just going to copy this code, paste it here, hold down Option, delete that, delete all of this, add commas, and add the ampersand to get the address. And for the name function, I'm going to do the exact same thing. I'm going to go up here, I'm going to copy all this. Oh, I forgot a comma right there. Copy all that, paste that here. Now I can do my Option Shift to delete, go across to the end of the line, and just, block delete all this stuff. All right, now I can clean it up. Remember, we're not calling them. We're just getting the address of them. Let's add a comma at the end of all of these and the address. Okay, let's compile that to make sure we did everything correctly. All right, build succeeded. Okay, it's time to create audio parameters for each of the chorus properties. So go to your create parameter layout. Now each of these right here are audio parameter float instances. So the only adjustment I'm actually making to the parameter ranges for the chorus params is to limit the chorus rate to be less than 100%, 100 hertz. Other than that, the param ranges follow the original snippet written earlier in this chapter. So just pick some reasonable default values. The default values that I chose are written above the parameter unit suffix line for each of these guys. All right, here is what this looks like. Here's the hertz one. Let's fix that indentation. Okay, we can see I did a hertz rate of 0.2 hertz. We'll do depth next. You can see I did a depth of 5%. Here's my center delay. I did a center delay default of 7 milliseconds. Then the feedback amount, I did a default amount of 0% feedback, as in no feedback. And then for the mix, I did 5% mix. So just a tiny little bit of chorus once it's finally in there. All right, let's compile that and see if it builds. All right, build succeeded. If you get a build succeeded, then go ahead and commit. And this is added Chorus Params, all this stuff. All right. All right, that wraps up the parameters for the Chorus DSP module. We still need to do audio parameters for the following DSP modules: the Overdrive, the Ladder Filter, and then the General Filter. Let's set up the Overdrive Params in the next chapter. The Overdrive feature of this plugin will be implemented by leveraging the JUCE DSP Ladder Filter class. This class has a great overdrive saturation sound, and by locking the cutoff to 20 kilohertz and the resonance to 0, we will have a really nice sounding overdrive processor as opposed to a ladder filter with overdrive. The overdrive parameter has a valid range of 1 to 100, and remember this when it's time to create the audio parameter. We need to create cached param pointers, functions to generate the parameter names, and then the parameters themselves, just like we did with the Chorus and Phaser modules. Let's get started. Head over to pluginprocessor.cpp, and let's create the function to generate the parameter name, and we'll put it with the rest of the name creation functions after the get chorus mix name. Overdrive section name, string, overdrive section. Let's use this function and create our audio parameter next. Head on down to the create parameter layout. Let's make our comment for our self overdrive. This is the drive portion of the ladder filter class for now, with a drive range of name equals get overdrive saturation name. And then we'll just copy our layout from another one. And this range is going to be from 1 to 100, and we'll do a step size of 0.1 and a default value of, and it doesn't have a unit. So okay, let's declare a cached pointer in pluginprocessor.cpp, for this overdrive parameter. Declare it after the chorus mix %. We used an audio parameter float when we created it, so it's the same type here. This line, and we're just going to call it overdrive saturation equals 0. And then finally, let's initialize it by adding it to the list of pointers being initialized, overdrive. And then we also need to use the name creation function. We got to add that name creation function to this array as well. Overdrive set. Remember, we're not calling it, we're just getting that. And let's try to compile. If you have no build errors, commit to that change. All right, here we added overdrive set param. Okay. At this point, we are still just adding audio parameters. We haven't prepared any of our DSP units, and we haven't even tested if processing works at all. That's okay. We are still wiring up the basic infrastructure. And once all of that is in place, we can start seeing what works and what doesn't work and add the necessary code to get everything working. Our next task will be to add parameters for the ladder filter module. All right, our next job is to set up the params of the ladder filter. We already have that open. The ladder filter has the following settings that can be customized by the user. Let's see, we've got our cutoff frequency, we've got our resonance, and as we know from the previous one, our drive. Okay, so let's go to plugin processor, let's go to create parameter layout, and way down at the end, we'll add this stuff here. There's a little note to ourselves. Okay, oh, and we also have a mode. That was the other thing. Where's that? Yeah, set mode. And here are the different modes. We'll take a look at that in a moment. All right, let's go back to here. Okay, the ladder filter has several modes represented by the ladder filter mode enumeration. This guy right here. We're going to use a JUCE audio parameter choice for this audio parameter, and the JUCE audio parameter choice class requires a JUCE string array to be passed to it whenever it is constructed, which contains the list of choices. So we're going to create a function to provide this list of choices in addition to the functions that produce the parameter name. Add the following below let's see, add the following below our get overdrive saturation name. We go right here. We're going to need our mode name, our cutoff name, our resonance name, and our drive name, as well as our choices array. All right, so let's add those guys in there now. And all of these are get ladder filter and then the thing and then the word name. So we've got ladder filter mode name, ladder filter mode, get filter cutoff name in hertz, so that's ladder filter cutoff hertz, filter resonance, get ladder filter resonance, and filter drive name, ladder filter drive name. Now for the ladder filter choices, we've got this list here. So I think the easiest thing to do is just copy it with the curly braces and then do auto get ladder filter choices return JUCE string array, no parentheses there because we're not calling it, and just paste it and then put all of these in quotes like that. Now we've got our string array being returned from that. Now that we have our functions to create the parameter names, let's go do that. Head over to create parameter layout. We're going to go to the end of it, so just go to the process block and then scroll up. And now we need to get our name. For the first one, this is going to be our choices, our filter mode. So name equals get ladder filter mode name. Auto choices equals get ladder filter choices. And then layout.add. For this, we're going to do std make unique. And this is going to be JUCE audio parameter choice. And we want this one here. This is the one that has the parameter name, the parameter ID, the choices, and then the default index. Okay. Now here is the closing angle bracket for the template. We want that to be here. The args thing, that's all of this stuff, so we can get rid of that. Get rid of that one, and now we can close the parentheses off like that. Now we can fill this in. Our parameter ID is going to be the same thing we did for every other one. This thing right here. Let's put that on its own line and indent it way over here. Our name, this is going to be the name. And then our choices is our list of choices. And our default index is going to be 0. All right. Now for the cutoff, we have other things up here that we can borrow from. This guy right here, here's our cutoff, so we can just copy this. We'll just change our parameter range and our default value, but this will be the exact same. Name equals get ladder filter cutoff name. Just paste that guy there. So we've got our name and our version hint. Our name is the next parameter, and now we just need to adjust this range. Let me just scoot this stuff over so it's easier to read. I have a giant font size on the screen so that way this tutorial looks decent on a mobile phone. All right, our range. Our lowest frequency value is going to be 20 hertz, and our max value is going to be 20,000 hertz. Our step size for the filter is going to be 0.1. Our skew is going to be 1. Now our default value, we want this filter to be all the way open, so our default value is going to be 20,000. Okay, we should have a unit of hertz right there. And then for our resonance, let's do that guy next. Name equals get ladder filter resonance name. We can just borrow a 0 to 100. So let's borrow this guy. Adjust the things a little bit. All right, so here's our version hint and our name. So our normalizable range for the resonance needs to be from 0 all the way to 1 with a step size of 0.1 and a skew of 1 and a default value of 0. So 0 resonance when this thing first turns on, and there's no unit for that. Finally, we got our drive. We can just copy the same drive settings we used for the overdrive saturation. Copy that. And we just need to go name equals get ladder filter drive name. Paste that guy there. It's the same range, minimum 1, maximum 100, default value of 0, our step size of 0.1 and a default value of 1. All right. Let's try to compile. You should have no error messages. All right, build succeeded, cool. As with the other DSP parameters, we need to create cached instances and initialize those. So head over to the plugin processor.h. Now for this one, there are 4 parameters. 3 of them are audio parameter float, and 1 of them is audio parameter choice. So let's declare them here. Let's just grab 4 of these guys, paste it, make this one choice. All right, and then we'll change this to be LadderFilter mode. Let's see, who's got cutoff? Is there a cutoff? No, there's no cutoff. I was trying to save some time. We'll just type it again. LadderFilter cutoff hertz. LadderFilter resonance. LadderFilter drop. Okay, now we need to initialize them. So let's add the audio parameter floats to the array of other audio parameter floats being initialized in the constructor, way up here. Do this after the overdrive saturation. So let's copy the 3 float instances, copy those guys, paste them here, remove what we don't need, add the ampersand to take the address of them. Then we need our 3 functions, the cutoff drive and name, constructor. So let's get rid of auto, get that. All right, and get rid of this return stuff. Oh, and sure, you're not calling them, you're just taking the address of them. Now it's very important that this order matches the order of these guys. So make sure it's cutoff, then resonance, then drive. Make sure this order matches. Okay, so this takes care of initializing the 3 cached audio parameter floats. But because we do not know how many other audio parameter choices this project will have, we're just going to initialize the audio parameter choice for the LadderFilter mode directly. So just put that down here after the loop. We'll go LadderFilter mode equals, and then it's this line just modified a little bit. So paste that line there, change this to audio parameter choice, and then our get parameter name is going to be get LadderFilter mode name, like that. And then let's just make sure that it's not a null pointer. JAssert LadderFilter mode is not a null pointer. All right, try to compile. And you'll notice that we're not running it to make sure that we're not hitting these JAsserts. We're gonna do that after we get the rest of the audio parameters initialized. All right, if you have no build errors, then make a commit. Added LadderFilter Params. In the next chapter, we are going to add params for the general filter. We don't have an enum for that yet, but we'll take care of that in just a moment. Okay, our next task will be the final step in adding all of the audio parameters for the DSP. We will be configuring the audio parameters for the general filter. The general filter will be a single instance of the JUCE DSP IIR. Let's go find that. Where is that guy found? Let's see. That's this guy right here, the IIR filter. Okay, the general filter is going to be an instance of this IIR class. Let's go find out where that is. Here it is. Here's the filter. All right. Okay, the IIR coefficients class has helper functions to produce. That's all this stuff right here. First order low pass, high pass, band pass, notch, all pass, shelf, peak, all that stuff. It has helper functions to produce coefficients for this filter. We will use several of these functions and allow the user to switch filter types based on the list of available functions. All right, so the following snippet shows the properties that our filter will have. Let's go put that at the end of create parameter layout and take a look at what we got going on. All right, here's our link to this guy. So we've got peak mode, band pass, notch, and all pass. Our frequency range is 20 to 20,000 hertz in 1 hertz increments. Our quality value is going to be from 0.1 to 10 in 0.05 sized increments. And our gain value is going to be from -24 to +24 in half decibel increments. All right, let's create some functions that produce names for these properties. We'll also need a function to produce the list of names for the filter mode parameter. All right, so head on up to where we are creating all of our free functions with the names right up here. Put this after get ladder filter choices. Okay, we've got our filter mode name, get our filter frequency, get our filter quality, and get our filter gain. All right, and they all return general filter mode, frequency, quality, gain. All right. Now it's time to create the parameters, and every parameter will be an audio parameter float except for the filter mode. That we will use audio parameter choice for that. So I'm just going to copy and paste this. You already know the format that we're using. Where did this go? Process block. There it is. Oh, go to the end of create parameter layout, and let's put this stuff here. Oh, we have one more function to add that we forgot about, and that is the get the general filter choices. Let's go back up to the top. We'll put that guy first here. Auto get general filter choices. This is also going to return a JUCE string array. So return JUCE string. Geez Louise, I keep typing that one with an extra capitalized letter. All right, return JUCE string array. And let's go back to our list here to see what choices we said. Oh, we're going to do peak, bandpass, notch, and all pass. So let's throw that in. Get filter choices. All right, so let's add that in here. And we'll just put each of these, put quotes around each of these. And put them on their own line. All right. Okay, go back to create parameter layout. Go to process block for me, and then just scroll up a little bit. Okay, let's define our mode. Name equals get general filter mode name. Choices equals get general filter mode choices, get general filter choices. And then we'll do our layout.add. Now, we did that up here, so let's just do that same thing here. We can just copy that one because that's layout.add audio parameter choice using the parameter ID that we know with the name and the version hint, our name, and then our list of choices, and then the 0th index is going to be the default choice, which in this case will be peak. Now let's do our frequency. We've got another one up here that's already doing that, 20 to 20,000, so let's just copy that. We just need to change the name. Name equals get general filter frequency name, and then paste the layout. So 20 to 20,000 hertz in 1 hertz steps, 1 hertz. And let's make our default value for this 750 instead of 20,000. So this way it's like right in the middle of the frequency plot. Okay, now we've got our quality from 0.1 to 10. Again, this is also a audio parameter float, so we can literally just duplicate that. Let me just make a comment here. This is mode freak 20 to 20k hertz in 1 hertz steps. Quality 0.1 to 10 in 0.05 steps. Name equals get general filter quality name. And let's just duplicate this. Our range is going to be 0.1 to 10 with a step size of 0.05 and a default value of, what did I put here? I put a default value of 1, and this has no unit size. And then finally we have our gain level, negative 24 dB to plus 24 dB in 0.5 dB increments. Name equals get general filter gain. And then let's see, we can again just duplicate this and edit our normalizable range. This is negative 24, positive 24, step size of 0.5, and then a default value of 0. And this will be in dB. All right, now that we have our parameters, let's declare cached versions of them. We need 3 audio parameter floats and 1 audio parameter choice, just like with the ladder filter. Copy this and paste it there. It's going to be general filter mode, general filter cutoff. We'll change this from cutoff to frequency because some of these are not cutoffs. Some of them are just the center frequency. We don't have resonance. We have quality. So general filter quality and then general filter gain. Okay, let's initialize them next. We will use the same process that we've been using, sticking all of the audio processor floats in the array in our constructor. All of these guys right here, doing the exact same thing we did here. Pointers to the cached parameters in the float params array, pointers to the name functions in the name function array, and then the choice param we're either going to do it this way by name, or we'll create a loop. I'm not sure yet. Let's see. Let's duplicate this though. And this will be general filter. Let's see, general filter frequency hertz, general filter, let's do quality, general filter gain. Okay, so frequency quality gain, get ladder frequency, so there's the cutoff, get ladder, what did I put here? Quality is next. Get ladder quality, filter quality. Oh, I'm doing the wrong one. This should be general filter. Get general filter frequency name. Get general filter quality name. Get general filter gain name. All right. General filter frequency quality gain. General filter frequency quality gain. All right. Okay, so it makes sense to do a choice array. It makes sense to follow this same pattern that we did here with the 2 separate arrays. So let's do that. Let's get rid of this and do auto choice params equals std array. Why did it do that? That was weird. All right, so the first one is ladder filter mode. Then we've got our general filter mode. Then we've got our array of choice name functions. This is going to be get ladder filter mode name, and then get general filter mode name. All right, and then we need our loop, and the difference here is that instead of doing audio parameter float for the cast, we are going to do audio parameter choice. Just copy and paste this, put it down here. Change float params to choice params. Change the usage of choice params down here as well. Change the choice name functions. Where it says float name funcs, change that to be choice name funcs. And then change this from audio parameter float to be audio parameter choice. Okay. Now be sure to compile to make sure that this works. All right, build succeeded. Cool. Our final task is to update the DSP processing to support this general filter. To do that, we need a DSP instance and enum entry and an updated DSP processing. So let's go back to our plugin processor.h. Let's go to our enumeration of choices, and after the ladder filter, add general filter. Next, we need to add an instance of the DSP IIR filter class. So put that after our ladder filter right here. Make a DSP choice, JUCE, DSP IIR filter, float. Oh, sure to spell float correctly. Call it general filter. All right, and if you compile now, you're going to see some warnings about missing switch cases. We'll take care of that next. Yep, right here. Enumeration value general filter not handled in switch. So add that case after the ladder filter. Right there, let's fix this indentation. This will be DSP Pointers I equals our general filter. And let's compile one more time and make sure that we have no more warnings or errors. All right, build succeeded. So now that that is done, we can check off that we have created our audio parameters for all DSP choices. All right, now we can make a commit. Added general filter params. Boom. All right, next we will prepare all of the DSP. Preparing the DSP is very easy. All of our DSP instances inherit from a common base class, so we just need to declare an array of base class pointers, populate that array, and then loop through that array. So first, we need to get a DSP process spec instance. First of all, we need to go to prepare to play. That's the important thing. Go to prepare to play. All right, let's get rid of this comment here. All right, we'll just put this after it. Okay, JUCE DSP process spec. All right, spec.sampleRate. This is going to be the function parameter, sample rate. Spec.maximum block size equals samples per block. And then spec.num channels equals the total number of input channels that we have. Get total num input channels. Okay, now we just need to declare an instance of std vector processor base, call it the DSP, and then initialize it with pointers to each of our DSP choices. That looks like this. Okay, and then finally we just create a range-based for loop and use the spec to prepare and reset each instance. So for auto p in our DSP instance, and we go p prepare with our spec, and then p, and that's it. Super simple because of that design choice that we made in the very beginning to use a wrapper class around each of these DSP instances. Super, super simple. All right, let's build that. And if you have no errors, we can mark the following to do as done. Update DSP here from audio parameters. Oh, I'm sorry, the prepare all DSP is the one that we get to. And then we can make a commit. So there's our process of preparing. Prepared all DSP. Stage, commit. All right, awesome. Our next job will be to implement state saving and loading functionality and test that it works. This is where we're actually going to run our plugin and get some sliders to appear and start dragging them around and seeing if it remembers all that stuff. Remembers where we left the slider position. Welcome to chapter 13. We will accomplish 2 steps in this chapter. Number 1, saving and loading the plugin state to and from the disk. And then number 2, updating all of the DSP components from the audio parameters. Let's start with the saving and loading functionality. That's this part right here. We're going to do that. Okay. The APVTS class can be serialized to disk using its JUCE value tree member. Let's go take a look at that. Let's see, plugin processor.h right there. Up to that definition. Okay, this has a JUCE value tree instance somewhere in here. Oops. Let's go find that. Copy state. There it is right there. The state of the whole processor. This must be initialized after all calls to create and parameter layout. You can replace this with your own value tree object and can add properties and children to the tree. This class will automatically add children for each parameter objects that are created by create and add parameter. Okay. The JUCE value tree class features one member function that we will use to save the value tree to a memory block provided by the host plugin. Let's go look for that. That is going to be the, let's see, where is that? What is that called? That's way down here in this write to stream, all this stuff down here. Okay. Stores this tree in a binary format. Once written, the state can be read back from read to stream. It's much faster to store your tree in binary form than as XML, but obviously isn't human readable. Okay, this is the member function I'm talking about in the tutorial. It also features one static member function to convert a chunk of memory into a JUCE value tree instance. That's this function right here, or this one right here. We are going to use this static function to restore our plugin state from the host. Now the audio processor features 2 member functions for saving and loading. That's going to be get state information and set state information. So you notice this one takes a memory block to write to, and then this one is providing us with a pointer to some data and the size of the data. So in JUCE value tree, we can see we've got our pointer to data and then the size of that data. All right. And then we can wrap our memory block in an input stream to be able to write to it. Okay. Let's go over to the get state information function here in pluginprocessor.cpp and add the following: JUCE memory output stream. I'm just going to call this MOS, and the memory block to write to is destination data, and we don't care about appending to existing content. All right, we're writing to this block of memory that gets passed in. And then now we can do apvts.state, that's that value tree I was talking about, and write to stream our memory output stream. That's it. Okay. This code works by creating a memory output stream that allows writing to the destination memory block. And then we use the write to stream function to write the state of the plugin to that memory block. Next, we will load the state from a chunk of memory, which is represented as a pointer to data and as a size argument, telling us how many bytes of memory we can read. This is handled in set state information. So first, we call the static function mentioned earlier, JUCE value tree read from data. We pass it our data and our size in bytes. And that's going to give us a tree back. And we want to then check if that tree that was returned from that function is valid. If tree.is valid. If it is, then we can do apvts.replace state. That's it. Super simple. All right. The final step is to make sure that all of this works. And we do that by changing the editor that is shown when the plugin is launched. So above get state information is a function called create editor. This function is what spawns the editor that we actually see on the screen when the plugin is loaded into a host. So let's change this to return an instance of the JUCE generic editor. Return new JUCE generic, let me spell generic correctly, audio processor editor, and it needs to get a reference to an audio processor, which is this. All right. Now, when you launch the standalone version, you should see a whole bunch of sliders and combo boxes representing each of the audio parameters that we created earlier. And if you modify one of these sliders and then quit and then relaunch, your slider should return to the same value you changed it to before quitting. So I'm going to adjust this phaser rate hertz from 0.2 all the way up to 1.38. I'm going to quit. I'm going to relaunch and it should be at 1.38. Oh, it's doing that thing again. Let's just comment out this code really quickly. That one more time. Again, 1.38 is what we should see for phaser rate hertz. That's all we're looking for. That's how we know the state was saved between quitting and loading. All right, if that is what you see when you launch the plugin, then go ahead and go to your list of to-dos, save and load settings, mark that as done, and make a commit. Added save load state ability. Added save load state. Bam. We're not going to commit that this was commented out. We're just committing that we changed the editor, that we did our save and load. Okay, commit. All right, awesome. Our next task is to update the DSP with the most recent audio parameter values. The basic principle is to call the get function for each audio parameter. Let me just give a quick demo of what that looks like. So for the phaser, if we're setting the rate, we would do phaser.dsp.setRate, and then we would do phaser rate hertz get, like this, okay? So the basic principle is to call the get function of each cached audio parameter and call the set function for the appropriate DSP instance. So let's do this for each cached audio parameter. The only gotcha is the LadderFilter mode. For this, we actually need to cast the params index to the LadderFilter mode enumeration type. Let's get rid of this line here. Now, I'm just going to paste the full code snippet and we'll talk through it. We're going to do this after the to-do list, but we're going to do it before this line right here. So this is all going to go here. All right, let me fix that indentation. Okay, let's perform a clean and then a rebuild. And then run the plugin. Oops, build is already running. All right, this is currently compiling. So let me talk through what this is actually doing. We have all of our cached audio parameters. We've got our phaser rate. We're setting our rate, our center frequency, our depth, and our feedback, as well as our mix. And then we're doing our chorus as well. Getting the rate, the depth percentage, center delay in milliseconds, the feedback percent, and then the mix percent. Now, something that was really important was that when we created all of these parameters, way back in create parameter layout, we made sure that our ranges that we used for these guys all matched the descriptions that we found in, all the descriptions that we found in the DSP processor's code. For example, let's go to, widgets, there it is. All right, so for example, in the chorus, we've got our center delay. We set this between 1 and 100. This was the range that we defined when we, chorus, where's this? Yeah, our center delay range. When we created our audio parameter, we set it to have a range from 0. Oh wait, is this incorrect? No, that's the rate, I'm sorry. The center delay milliseconds, that's this right here. We set it to make sure that it was from a range of 1 to 100, just like the documentation says to do for the chorus. And in doing so, when we actually update our process block for the chorus, we don't have to do any kind of conversion when we call this delay function. The values we are passing to the delay function are within the allowed range. And that makes this code super simple to look at and read. All right. So if you got your stuff running and everything looks normal, aside from it hitting that one JAssert occasionally, then you can go ahead and make a commit of this. And we can mark off that we updated all the DSP here, here referring to process block. All right. Now we need to add two to-dos. Let's just do them right below this. Update DSP from here. To do, update general filter coefficients, and then to do, add smoothers for all param updates. The purpose of the smoothers is so when you're staring at the screen, when you are staring at your plugin and you make your phaser depth go from here to there and just super fast. If you're doing things with filter frequency or feedback or a couple other parameters, you can get a zippering effect, which does not sound good. Reason for that is that you're changing the values of the parameter too quickly. So using a smoother will fix that. Basically, we're going to say when you change from one value to another, you're going to take X amount of time to do it. In this case, I probably use 5 or 10 milliseconds to do it. We're not going to notice it. The response is still going to feel fast when we drag that slider back and forth. But sonically, we're not going to hear that zippering anymore, and that's the important part. All right, let's make a commit of this. Again, we're not going to commit this part where we disabled that code, updated to-dos. All right, so let's update this and say updated DSP from Params. Awesome. Okay, in our next chapter, we're going to tackle a big thing. This is adding serialization of the DSP order to and from the save load functions, as well as editor functionality for testing save and load. Okay, our task in this chapter is to implement saving and loading of the DSP order. That's this one right here. This plugin will support dynamically changing the DSP order, and when the user closes the GUI and reopens it, or quits their session in the DAW and then launches it later, that DSP order needs to be preserved. This is what we're going to tackle now. And the first thing we need is a default DSP order to test with. We will leave out the general filter from the order for now. So add the following snippet to the top of the audio processor constructor. We'll go way up here. All right, DSP order equals, now we're going to initialize an array. So our first thing is going to do DSP option. We're going to do a phase. Actually, that should be phaser. I don't know why it's not. Okay, and then we're going to do chorus, then overdrive, then ladder filter. We're going to ignore the general filter for right now. Phase, chorus, overdrive, ladder filter. Now, just as a note, let me pull up this guy right here. Where is this? All right, the DSP option. So we have a DSP order array. Where's that guy? That's right here. And remember, this is an alias to std array DSP option with a specific size, the number of elements in this array. So the DSP order array has more elements than the initializer list we're passing right here. The reason this works is because arrays are initialized with the default value of whatever type they are designed to fill. In our case, this array is meant to hold DSP option instances. And enumerations decay to integers, and the default integer value is 0. Therefore, the DSP order is filled with DSP option phase by default. And if you add a breakpoint in the debugger on the creation of the float params array and run this, when we inspect the DSP order instance, we will see that. All right, let's look at this DSP order. Where are you? You're right there. Zoom in on that, show me the elements, and we can see 1 through 4 matches, phase, chorus, overdrive, ladder filter, and then the final element is phase. All right. Let's implement saving and loading our DSP order instance to and from the APVTS via the JUCE variant converter type. Let's take a look at that. Variant converter, struct variant converter. Let's see if we can find a template. Here it is. All right. A helper type that can be used to implement specializations of variant converter that use from var_convert and to var_convert internally. So here's an example of that. Let's see. Here's an example for the string where it converts from a string. It converts a string into a var object, and then it converts a var object back into a string. So we're going to make one of those to convert our DSP order into a JUCE var instance. Okay, here's our variant converter that uses generic casting to do the thing. All right, this template overloaded class can be used to convert between var and custom types. If not specialized, which is what we're going to do, the variant converter will attempt to use serialization functions if they are detected for a given type. For details on what this entails, see the docs for serialization traits. In short, the constant marshmallowing version and either the single function serialize or the function pair load and save must be defined for the type. These may be defined as public members of the type itself or as public members of JUCE serialization traits, the template, which is a specialization of the serialization traits template struct for the type T. Okay, that's a lot of words. What does that mean for us? The purpose of this class is to convert instances of a class type to and from JUCE var instances. Right there and right there. The JUCE var class can store lots of different types internally: int, float, double. Let's go look at that real quick. This one, the var can store ints, bools, doubles, strings, arrays, memory blocks, that sort of stuff. Okay. In our case, we are going to make the JUCE var instance store a block of memory. To convert our DSP order object into a JUCE var, we need to convert it into a format that can be stored in a JUCE memory block, and then use that JUCE memory block to construct a JUCE var. To construct a JUCE var into a DSP order object, we need to get the memory block from the var and then convert that memory block to the format we used when converting to the var, and then convert each element in that format into a value from the DSP order enumeration. And as I said previously, the JUCE, let's see, where did I go? The JUCE variant converter class is a templated class. We are going to specialize it for the type that we are going to convert to and from JUCE var. And if you want to learn more about class template specialization, you can do that right here. Maybe I'm putting the link right there. I'm not sure. Yeah, I think I'm putting it there, or maybe I'm putting it there. Either way, take a look at that link. Our first step is to declare a template specialization in plugin processor.cpp before the set get state information functions. So let's go to where those are. Let's put those here. So we need to provide rough outlines of the two static functions defined in that variant converter documentation. We've got our static type from var and our static type to var. Okay. So let's begin on that. Template, it's going to be a specialization, JUCE variant converter, and this is going to be project 13 audio processor DSP order. Okay, this is the start of our specialization. Now we need to provide converter. Make sure you spell that right. Now we need to provide the from var and to var functions, and they're going to return, let's see, static. The first one is going to return a DSP order instance from var const juice var v. Let's make that blank for right now. And then we need to do our to var function, static juice var to var, and we're going to pass it one of these guys, const reference T. All right, next we need to fill in each of these functions. The first one that we will implement is the to var function. As stated earlier, we will be converting our DSP order instance into a JUCE memory block and then converting that JUCE memory block into a JUCE var. So we can write to a JUCE memory block using JUCE memory output stream. Let's go look at that. JUCE core, I think we want JUCE memory for that. Let's see, memory. Is this where we do all this stuff? Let's see, memory output stream is what we want. Let's see, we can find that over here. Memory output stream, go to there, jump to definition. So yes, right here, memory block to write to. So we just need to pass in the block and then it'll add to it and whatnot. Okay. So as you can see here, this class has a very handy constructor that takes a memory block that makes writing to a memory block super easy, super convenient. The only gotcha is that we have to remember that the cleanup of writing to a memory block is handled when the MOS instance goes out of scope, meaning this thing doesn't actually get fully written to, the destination data doesn't get fully written to until this curly brace is hit. So we need to make sure we do something with that. We need to make sure that we write to our stream in a closed scope. Okay, so what does that look like for us? Let's declare our memory block, JUCE memory block MB. And then I'm just going to note to myself, JUCE MOS uses scoping to complete writing to the memory block correctly. All right, so let's add some scoping and then do JUCE memory output stream. Block to write to is going to be MB, and then this is going to be false. And then finally, we can just return our MB because the JUCE var class can be constructed a JUCE memory block, making life easy. Now we just need to use this memory output stream right here. Oh, I forgot to give it a name. Now we just need to use this memory output stream to write each value of the DSP order instance to the memory block. And if you remember, enumerations decay to integers, so we can just cast each value to an int and then use memory output stream write int to write to the memory block. Super simple. For const auto v our array, we can just go mos.write int and then static cast int our value. Ta-da! Super simple, nice and logical. Now we need to implement the reverse. Reading an integer from the memory block stored inside the JUCE var, and then casting that int to a DSP order enumeration value. So first we need to extract the memory block from the JUCE var, but we can only do that if our var is holding binary data. If it's not, then we can't do anything with the var, so we need to return a DSP order instance filled with something other than garbage values. So to begin, let's declare an instance of the type that we will be returning. Let's see, using t equals this super long thing, because I don't want to have to type that. And let's declare one t DSP order. All right, now let's make sure that we have binary data, jassert v.is binary data. And then now we can do our check if v is binary data. If this is false, then we can fill our DSP order with the end of list option. DSP order.fill project 13 audio processor DSP option end of list. And the whole point of filling it with this is so that in our process block loop, we end up hitting this right here. We hit this JAssert and we tell ourselves that that's happening, because this kind of stuff is what happens during the debugging process. So we'll catch it before we actually release the plugin to the end user. All right. Else, we know we can try to read everything, and once we're done with that, we can return our DSP order. Okay. If the var is holding binary data, then we need to extract the binary data, read each int from it, and then convert those ints into DSP order instances, and then populate the DSP order variable. So we can use a JUCE memory input stream to read from the memory block extracted from the JUCE var. Let's take a look at that. So we go to memory output stream, and then change this to memory input stream. And we can see that we can construct this from a memory block to read from. So we're going to use this constructor. All right. Let's see. Auto mb equals v.get binary data. That returns a pointer. So we want to get the actual object. This is going to make a copy. It's small. We don't care about the cost of that. Okay, so let's make a memory input stream now. JUCE memory input stream, memory block. Give it a name, MIS. Our memory block is going to be MB. We don't want to keep an internal copy. That would just create a duplicate. Next, we need to read each integer from this stream. I found it super simple to create an std vector of integers to write into. We don't know how long the stream is, so vector will provide us with a container that can accept any number of elements. We can read from the stream as long as it's not exhausted, so let's do that. Std vector int. Here's our array, and then we can do while, whoops, spell that correctly, while our memory input stream is not exhausted. We can do ar.pushback mis.read int. Once we have read every integer, we should confirm that we have the same number of integers as there are elements in the DSP order instance. We can do that with the JAssert. JAssert ar.size equals DSP order.size. Put the semicolon in the correct side. Awesome. All right, now we can convert by casting each element in the array into a DSP order instance and populate our DSP order object with them. For this, we just need to use index-based looping instead of a range-based loop, since we will be reading from one container and writing into the other. So do a simple for loop for that. For size ti equals 0, I is less than DSP order size plus I. And then we just go DSP order, the index we care about equals, and then we do our cast. Our cast to DSP option. Do I have that written? Yes. I don't want to type it, so I'm just going to copy and paste it from somewhere else. And then we are reading from ARR at index I. Okay, with that, our to from implementations are now complete. Take a look at that. There's our from var. Let's truncate this a little bit. Maybe I should make the font just a little bit smaller. There we go. Okay, there is our from var function, and here is our to var function. So let's compile and fix any warnings that appear, and then we'll need to make use of our variant class. All right, build succeeded for me. It's just warning about that context from that code we commented out in process block. Okay, now we can go to get state information, and we want to add our DSP order to the APVTS state. This is where we get to make use of our variant converter class. To do this, we need to convert our DSP order into a var and then add that var to the apvts state. That's this right here, apvts.state via set property. That is going to look like this. And we do this before we do our writing to the stream. So we go apvts.state.set property. Let's wait for autocomplete to give me all the stuff. Set property. Our name is going to be DSP Order. Our value, let's see. We're not going to use our undo manager, so null pointer on that. Our value is going to be JUCE variant converter. Our type name is going to be the project 13 audio processor DSP order. And then let's see, ::2 var. And then we're passing it our DSP order. Okay, that's all we need to do. This is gonna just magically write it into the apvts. Okay, and then next we need to do the reverse of this. We've got our apvts.replace state. So next, what we do is get this DSP order property, this one right here that we set. We need to get it. Then we need to convert it to the DSP order. Then we need to pass it to the audio processor side of things using that FIFO. This is where we get our cross-threaded synchronization, because this is happening on some background thread, maybe the GUI thread, whereas process block, where we are actually reading from here, is happening on the audio thread. This is where we start making use of the FIFO. Okay, that looks like this. If apvts.state.has property DSP order. It's very important to make sure you spell this the same as you spell this. Then let's get the order. Auto order equals JUCE variant converter. Spell it right, variant converter. All right, we need our long name here. And then we want from var. And this is where we go apvts.state.get property. And we want the name of that property, DSP order. And then finally, since we got something, now we do DSP Order FIFO dot push order. And just to make sure everything is looking right, let's just do debug. Let's just debug print out apvts.state.toXML string. And this is just going to print out the apvts state as XML formatting. Let's run this and let's take a look at the output that gets printed. Let's move that. All right. So we can see right here, we've got all of our parameters. Actually, what we need to do first, we have to quit because we haven't, it's loading the previous state. So let's quit this, and then we rerun, and now we should see that at the very top. And sure enough, there it is. There is our DSP order. So if you see this line right here, your plugin is working as expected. Let's add the ability to randomly change the DSP order so we can test if the SaveLoad functionality is working correctly. Let's change the create editor function. First of all, let's close the plugin. Hide this. Okay. Let's go to that create editor function. Where are you, create editor? All right. Okay, go back to using your actual editor. All right. Now let's go to the plugin editor class itself, plugin editor.h. Down at the bottom, after the audio processor, let's add a DSP order button. So JUCE text button, DSP order button, DSP order. Let's make that all lowercase. All right. In plugin editor.cpp, we need to add the button to the GUI, give it some bounds, and then make the button create a random DSP order and push it into the audio processor whenever it is clicked. And then after we click the button, when we save and quit and launch, we should see a different output for that first line of the setting output. Okay, so let's go to the resized function. Throw this in here real quick. Let's see, DSP order button dot set bounds. And we want to do get local bounds. Oops, spell that right. And then reduce it a lot, 100. We don't care how big or this is. There's nothing on the GUI right now. And then we need to add the button to the constructor. We need to add the thing to our class. So add and make visible DSP order button. Then we need to define the on-click function of the button. As stated earlier, we need to create a random DSP order and push it to the audio processor. We can use an instance of the JUCE random class to produce values. The random class can produce values limited to a range, so we will use that as well, setting up a JUCE range integer object where the starting value is the first DSP option and the ending value is end of list. That is going to look like this. We will do this all before we add it and make it visible. All right, so let's do this. This is all going to happen inside of the onClick lambda. So DSP order onClick equals lambda, lambda, lambda. All right, we're all going to put all that stuff in here. So first we need our JUCE random R. Then we need our DSP order, project 13, audio processor, DSP order. And let's make our range equals JUCE range with our start value and our end value. This is going to be integer. Our first starting value is going to be DSP option phase. Okay, so static cast int. This is going to be this thing. Then the DSP option, oops, not order, option type. Our first instance 0, and then our end of list static cast int project 13 audio processor DSP option end of list. Okay, then we've got our range. Now we can go for auto, and we are modifying each element in the DSP order. Auto V in DSP order. Auto entry equals next equals r.next int with the range, and then V equals static cast to DSP option. We're casting from integer to DSP option the entry value. Before we send this DSP order instance to the audio thread, it's useful to print out whatever was generated and inspect the DSP order object itself. So as shown earlier, the JUCE var is printed out as base 64 text, so we are going to do that here. So debug JUCE base 64 to base 64. This, as you can see down here, it returns a string, and our input for the source data is going to be DSP order get data data, and then our size is going to be DSP order size. And we'll add a JAssert false so we can actually see it. This is going to break the program. It's going to pop up in the debugger, and we'll be able to look at the console output. And I like to add JAsserts after debug lines like this so that execution pauses automatically and gives me a chance to look at the console output before continuing the program execution. So finally, let's send this to our audio processor by capturing this, and now we can access it. Audio processor.FIFO push DSP. Okay, so we should be able to run the program, see our boring GUI with a single button, and then click that button and take a look at the console output. All right, so we got triple A's right here. Let's look at our DSP order object here. And we can see we got phase, chorus, overdrive, ladder filter. All right, so remember that phase, chorus, overdrive, ladder filter. Okay, we'll press continue, and we'll go back to this. We will quit, and we will relaunch. And in order to confirm that that worked, let's add a breakpoint in plugin processor process block right after we do the pull right here on the DSP pointers. We'll run. Process block doesn't load up until after this stuff gets until after the state is loaded. So now we can take a look at our DSP order instance here and see if it had phase, chorus, overdrive, ladder filter. And sure enough, it does. And that's awesome. So that is working correctly. If you see the same contents in the DSP order object as you saw when you clicked that button and inspected it from the editor, you have successfully implemented save and load. And as a final safety check, fill the DSP order pointers with null pointer in process block. So DSP pointers dot fill null pointer. So that way If it's ever filled with garbage and the switch is not for one of these cases, then the DSP pointer will still be filled with null pointers, which means this will work normally. Let's run that and test. All right. This should still be the same. Phase, chorus, overdrive, ladder filter. All right, let's move that breakpoint. Okay, so do some more testing. Click that button a few times. See what happens. It's going to hit an assertion sometimes, so you can look at this. Let's see what this says. So we got overdrive, chorus, general filter, ladder filter. Let's see what that does. Press continue. All right. If you find that after testing, you hit a JAssert whenever the general filter becomes part of the DSP order, that is because the JUCE DSP IIR filter class is a mono filter, and the context being processed is a stereo context. So we need to add a to-do for this. And you'll notice here in this call stack that that's what's happening right now. We're currently inside the code for the IIR filter, and it's expecting to have only a mono channel. So first of all, let's go back to plugin processor.cpp. Let's go to our to-do list, and we can mark off that saving and loading the DSP order is done. And then we need to add another thing here that says to-do filters are mono, not stereo. All right. With all that said, go ahead and kill the plugin and make a commit. Kill that process. All right. All right. So our commit message is added serializing of DSP order to from SaveLoad and editor functionality for testing. No need for a period there. All right. That was a big one. Our next job will be to add and implement bypass parameters for each DSP object.
Hey, if you like this tutorial that you've been following along with and have been wishing for a written version, check out the link below. You'll find this course as well as my other courses, all available in written format. They're full of detailed explanations, code snippets, and more. Each chapter is crafted to be easy to read and easy to follow. Complex features and ideas are turned into simple concepts with clear code snippets. You'll progress quickly as you elevate your app and plugin making skills by working through these projects. Programming isn't hard, it's just taught wrong. All right, let's get back to making this plugin.
Our next job is to add the ability to bypass individual effect instances to the plugin. This is important if you want to be able to hear the difference between when an effect is active and when it is not. We'll follow the same pattern we have used for the other DSP instances in this project. Create a name creation function, create audio parameters, create cached audio parameter instances, initialize the cached audio parameters, and then implement the DSP that uses the cached audio parameters. So we need to create bypass params for each of the DSP instances we currently have implemented. Our phaser, chorus, overdrive, ladder filter, general filter, these 5 guys here. So head over to pluginprocessor.cpp and go up to your naming functions. And at the end of the list, add one bypass name creation function for each of these effects. I recommend placing them with their related name creation functions, as in put the get phaser bypass name function with the other phaser functions. Here is the list. I'm going to just paste them here at the end and then move them around. So here's the phaser one. Let's move that up with the phaser section. I'll put it at the end. Let's do chorus next. All right, we got our overdrive bypass. You know, let me just copy and paste it. It's easier than holding that key command down to move it. Ladder filter and filter bypass. Whoops. Command option open brace. All right. Next, we need to create audio parameters. All of these will be instances of JUCE audio parameter bool, and their default value will be false, meaning the effect is not bypassed, as in it is active. So use each name creation function to provide the name for the audio parameter. Again, I recommend putting all of these with the related effect parameter creation. All right, so here's the full list. I'm just going to stick these here at the top, and then we'll just move them to the right place. Put them right after version hint. So phaser bypass name. Let's cut and paste that guy. That goes with the phaser section at the end of that. Right there. All right, next we've got chorus bypass name. Put that at the end of the list, right there. Next, we've got our overdrive bypass. Put that right there. And we've got our ladder filter bypass. It goes right there. And then finally, our general filter bypass, way down at the end. All right, let's clean this up at the top. We don't need any of this, all these blank snip lines. Okay, now we need to create cached param instances. These will all be instances of JUCE audio parameter bool pointer. Let's see, why is this complaining about that? Why is it complaining about that? All right, build succeeded. Okay, cool. All right, cached param instances. We need to add audio parameter bools for all these, and they need to default to null pointer. So let's just do that quickly. JUCE audio parameter bool pointer equals null pointer. Okay, we need 5 of these. We need phaser bypass. Let's just duplicate this 5 times. Got this. All right. Phaser needs 1. Chorus needs 1. Overdrive needs 1. Ladder filter needs 1. General filter needs 1. Okay, the name, general filter bypass, ladder filter, oops, spell ladder filter right, overdrive bypass, chorus bypass, phaser bypass. Okay, next we need to initialize these cached parameters. We're going to replicate the pattern that we used in the constructor for the float and the choice params. We will create an array of pointers to the parameters. We will create an array of pointers to the name creation functions, and then we will use a for loop. All right, so that's pretty easy. Let's do that here. All right, here's my bypass arrays. Here are my bypass name functions. And then here's the loop to make sure that they are all initialized correctly. Let's try to build that, make sure everything compiles. All right, build succeeded, good times. One thing that we forgot to do is add a to-do for adding bypass params. And if you want, you can add one now. I always think it's a good idea to add that stuff just so you have a list of what you have done and haven't done. All right, so let's mark it as done. Add, bypass params for each. If the project compiled without issue, go ahead and make a commit. Added bypass params. Next, we will configure the DSP to make use of these bypass parameters. Our first step is to enable access to this bypass param in the DSP pointers array by changing the data type stored in the array to a type that contains the bypass value. So we do that over in plugin processor. Where is our DSP pointers object? That's this thing right here. Okay, DSP pointers. All right. We are going to create a struct called process state. Struct process state. Now it's going to have a pointer to the processor. JUCE DSP processor base. Processor equals null pointer. And it's going to have a bool bypassed equals false. And now our DSP pointers object is going to be an instance of process state. Okay, this is going to cause some error messages in plugin processor.cpp. So let's go fix that. Plugin processor, if we build it, we'll see that right away. Okay, first of all, we're not filling it with null pointer. We need to fill it with default instances of this new class. So let's comment that out. Oops, let's comment that out. Say DSP pointers.fill, and we're filling it with default instances of that, and say this was previously that. Next, for all of these, they need to say that the processor is this. The processor is this thing. Okay. And then finally, we need to set the bypass param, the bypass value on it. DSP pointers bypassed equals, and then this is where we use the cached bypass thing. All right, do that for the remaining ones. Chorus bypassed gets the chorus bypass cached value. Overdrive overdrive bypass, ladder filter bypass, general filter bypass. All right, the final error code that we need to revise is this, and we just need to check if the processor is not null pointer. Okay. Next, we need to bypass the context. We also need to make this be .processor. Finally, we need to bypass this context whenever the bypass param for a particular DSP pointer instance is true. When a DSP instance is bypassed, we want to make sure that the next iteration of the for loop resets the context bypass state to unbypassed. And to do this, we can use a JUCE scoped value setter, which will change the bypass property of the context to whatever we want, and then change it back when the scoped value setter goes out of scope, which happens at the end of the closing curly brace here. So let's do that. JUCE scoped value setter bool. I'm going to call this SVS, and the value to set is context.isBypassed, and the value is going to be DSP pointers bypassed. Okay, let me just explain what that's doing once again. This function, this object right here, scoped value setter, is going to change this member variable inside of this block from whatever it currently is now to whatever this variable's value is. And then when it gets destroyed, it's going to return it back to its previous value. So if this is true right now and this is set to false, it's going to set this to false. And then when it hits this curly brace and gets destroyed, it's going to set it back to true. It's kind of it's a pretty handy tool to limit the scope changes of something to be within a block of code. All right, so try to compile. And if it builds without errors, you can change back to using the generic editor again. All right, build succeeded. Let's go to using the generic editor. Create editor. Let's switch back to the generic editor. And let's run the plugin so we can see our bypass parameters. And there we are, phaser bypass. Awesome. So if that is what you see, go ahead and make a commit. Implemented bypass DSP. All right, so finally we will add a test that confirms we can bypass individual DSP elements correctly. Let's create a macro to enable and disable this test code easily. Let's put this macro at the end of the audio processor's class definition, way down at the end. We'll do this before our leak detector guy. Define, verify bypass functionality and set it to false. No semicolon. All right, here's how we are going to use this macro. First of all, it's very difficult to set breakpoints that can be tested easily in process block because of how fast the audio callback happens. We will programmatically define a DSP order and push it into the DSP Order FIFO after we programmatically set one of the bypass params to true. We will do this in set state information after the state is loaded. We will use a JUCE timer call after delay to do the following 1 second after the state is loaded. So 1 second after this function gets called and we push our order into the process block, so it's got a fixed DSP order, we are going to do the following 1 second after all that happens. We're going to create a DSP order instance. We're going to fill it with some DSP type. We're going to set the first element to a different type. We're going to set the bypass param of that first element to true, and then we're going to push that DSP order instance into the DSP order FIFO. So here is the snippet that we're going to do that. This is going to happen after we print out this thing. If verify bypass functionality. And so we're going to go JUCE. First of all, let's close it off. And if JUCE timer, you know what? We have to turn this on so that way autocomplete works. We'll leave it off just a second, but we'll leave it on for right now so we actually see this code. JUCE timer call after delay. So give me the autocomplete. All right. 1,000 milliseconds later, we're going to do this thing right here. Let me put that back on this line. All right. This curly braces come next. All right. Step one, we're going to create a DSP order instance. we are going to fill it with ladder filters. Order.fill DSP option ladder filter. Then we're going to change the very first one, 0, equals, we're going to make this a chorus param. DSP option chorus. Then we are going to bypass the chorus bypass, set value notifying host on, and then finally we're going to go DSP order, DSP order FIFO dot push our new order. All right. Next, add a JAssert in the code that pulls. Let's see, where did that go? That's this right here. All right, next, add a JAssert in the code that pulls DSP order instances out of the DSP order FIFO and wrap this in the macro. If verify bypass functionality and if JAssert false. All right, finally, make use of the macro in the code that actually processes the context. So after setting the scoped value setter state, we can go like this. Verify bypass functionality. If context.is bypassed, JAssert false. And then also we can get rid of those JAsserts about the general filter by just saying if DSP Pointers if the processor is the general filter, then just skip. Don't do this process thing. That'll fix that. All right. Okay, let's go back here. Let's disable this to make sure that our macro doesn't do anything when we don't want it to. All right, so notice we're not hitting any of those JAsserts. This is good. This is because we did not enable the macro. So let's close this out. And now let's turn the macro back on. You should hit the JAssert in the FIFO twice. The first time you're going to hit the FIFO is when the state is loaded. If you remember in set state information, this is where we pull it in and we push an instance in here. And this is what enables us to actually pull a DSP order instance out of the FIFO. And then the second time is 1 second later when we push this customized one in there. All right, before you run this, I would recommend doing a clean and then do a rebuild. And then run the plugin and you should hit that JAssert twice. Each time just inspect it. For me, my output was showing, that phase, chorus, ladder filter for the very first time. That's what got stored to disk. And then the second time, it should show all ladder filters with the very first index being chorus. All right, so that's what you should expect to see. All right, so our very first time. Oh, did that get written to disk? That did get written to disk. All right, so I need to actually change this. Let me bypass this. If you find yourself in this situation, here's what you do. Change this to false. Go back to plugin processor, go to your create editor, and switch back to your editor. Run this, and then push that DSP order button to generate a random order. There's our random DSP order here. That's fine. Okay, that's fine. Oh, this is also going to be fine. Oh, it's going to keep doing this. It's going to keep doing this for a long time. So actually what needs to happen now is in process block, this thing right here, this actually needs to not be part of that bypass functionality. Let's just move that downward so it is there and so we don't hit that JAssert. Let's do this one more time. We'll move it back in just a moment. We'll move this check back in here in just a moment. Okay, so change the DSP order. See what this is. So phase, ladder filter, fine. All right, good enough for our needs. Go ahead and quit that to save it to disk. Go back to plugin processor. We can move this back up here. We can turn this back on. And now when we run it, we should be able to inspect those two things. If you remember, it had ladder filter, general filter, ladder filter, general filter for indexes 3 and 4. All right, ladder filter, general filter, ladder filter, general filter. Good. Okay, continue. And it hits it again, and now we see chorus, ladder filter, and all the ladder filters. So the bypass functionality is currently working. Good. So now, if we press continue again, it's going to jump down here and hit this JAssert. And there it goes. And if we notice that I is currently set to 0, that is the chorus DSP element. And if you remember, when we set up our test right here, where did that go? This thing right here, we set the chorus, which was at index 0 in our DSP pointers, to be bypassed. All right. So with this test, we now know that our bypass parameter is working correctly, controlling the context bypassed state. Let's step over this iteration. Let's go back to here. Let's step over this iteration until it shows that we are on I equals 1. All right, and step on in here. And we can see that our context state, if we look at that, context is currently not bypassed right now. We step over the scoped value setter and see what that does. Again, it is still false, so that is still doing the right thing. All right, so we have finished our test. You can go ahead and stop the program, click that stop button or whatever key command you use. Go to pluginprocessor.h, you can disable your macro. And we forgot to add a to-do for this guy, so let's do that and mark it as complete. Process block. Let's do this right here. Done. Bypass DSP. Awesome. Go ahead and make a commit. That was a big one. It didn't seem like we wrote a lot of code, but we did have to make some, it's a pretty important test. Okay, there's that, and then that. And let's stay on the generic audio processor. So discard this change to the regular one. All right. Added, verify, bypass, test macro. Commit. All right. Our next task will be to refactor how cached parameters are initialized. If we go take a look at that, way up here, hide this guy. There is an opportunity for some DRY refactoring. Don't repeat yourself. After we do that, we'll tackle the general filter issue of requiring mono channels to process audio by converting all DSP choice objects into mono processors. All right, that'll be a fun one to knock out. In this chapter, we're going to tackle two issues. The first one is DRY refactoring the constructor. That means don't repeat yourself. We're doing a lot of repetitive stuff in the constructor, so there's a definite pattern, and we're going to try to turn that, going to make it less repetitive. The next thing will be to add mono channel support for the DSP instances so the general filter can begin to be used. Let's begin with refactoring the constructor. Now each of these for loops is using the same pattern. Loop through the array of parameters, call APVTS get parameter, and then try to cast and initialize the cached parameter, and then JAssert if it fails. They're all using that same thing. So we can use a templated function to do that for us. Let's put this in the header file in the audio processor class declaration. Anywhere, it could be the private section, public section, doesn't matter. I'm just going to stick it down at the bottom. After this macro. Let's take this function. We're just going to copy this loop. Copy this. Let's make a templated function. Void init cached params. Fill in our argument list in just a second. Here's the body of it. All right, so let's template this guy. Template type name param type, and then type name params, and then type name funcs. Okay. So now we've got our function argument is going to be the params array. And then we've got our funcs array. Now our params array is going to be params array. Replace all of these float params thing with params array. And then finally for the function, float name functions gets replaced with funcs array. And then for the type that we are casting to, it's param type. Like that. Okay. All right, now replace each of the loops in the constructor with calls to this templated function. So comment this guy out for right now. And let's just call init cached params. Our params array is going to be the float params. Our functions array is going to be the float name funcs. And our param type is going to be audio parameter float, the star meaning a pointer. All right. Now let's do that again for the choice params. Init cached params. This is going to be the choice params is the first parameter. Our functions is going to be the choice name funcs. And then our template type is going to be JUCE audio parameter choice pointer. Let's do the same thing for the Boolean. Comment this out. Init cached params. This is going to be audio parameter bool pointer. Our params array is going to be the bypass params, and our functions array is going to be the bypass name functions. All right, compile that and run it. Everything should work exactly the way it did before. Let's see, let's make sure. All right, build succeeded, currently attaching. We got our usual J assertion in one of the filter functions. It's fine, it's in the IIR filter. All right, that's totally fine. Okay, so let's just clean this up and get rid of our big loops, make our code a little bit more concise. All right, let's make a commit of that. And this will be refactored how cached params are initialized. All right. Our next job is to make each DSP processor mono and give the audio processor 2 instances of each per channel. 1 per channel. So we go over here and take a look at these guys. Our DSP choice instances, some of these work with stereo, some of these work with mono, and that's what we're going to take care of. This job is pretty easy. The gist of it is mainly refactoring all of the code that prepares and reads the params and sets DSP states and processes each DSP instance into class member functions of a new class that owns the DSP instances, and then giving the audio processor 2 instances of this new class, 1 for each audio channel. Let's start by wrapping those DSP instances into a class and adding 3 member functions that prepare, update the DSP from the parameters, and then process. Now I chose to put this class inside of the audio processor class, and the update DSP from params function requires access to the audio processor instance, which means this class will need a reference to the audio processor. I'm going to put this before, so we're basically wrapping all of this stuff. These guys are going to get wrapped up inside of a class. All right. So let's create our class that owns these guys. Struct mono channel DSP, curly brace right there to own it. Now we need to add a private reference to the audio processor. So private project 13 audio processor reference P. Okay. All right. We need our 3 member functions. Okay, now we need to add a constructor. So mono, let's add that. Yeah, mono channel DSP. And this needs to initialize this guy right here. So it needs to take an instance of that. And it needs to initialize it. All right, next we need those 3 functions, the prepare function, the update the DSP from parameters, and then the process function, which is going to take a an audio block instance and the DSP order. All right, let's do that first. Void prepare. JUCE DSP process spec. Then we need our update function. This function is what's going to interact with this guy and update all of these. Then we need our process function. Void process. Block, and then our DSP order. All right, Let's declare 2 instances of this class right below the class declaration. So mono channel DSP, left channel, initialize it with a reference to ourself. Do the same thing again with another reference to our audio processor. Okay, this, if you build it, this should produce a ton of build errors, which is fine. We're going to start fixing all of those. We have a lot more refactoring to do first. Our next job is to implement these 3 member functions. Let's go to plugin processor.cpp. So the first thing we'll do is the prepare function. So go to prepare to play. We'll put it near that. We can move all this stuff later. We need to move the code that prepared all of the previous DSP instances into this new member function. So let's do that now. Void project 13 audio processor, mono channel DSP, prepare. All right, we can just cut and paste this. Now we just need to make sure that our channel is 1. So let's add a JSR for that. Num channels equals 1. All right, then we need to change prepare to play to do that as well. Let's change our spec.num channels to be 1, and then we can do left channel.prepare with our spec, and then right channel.prepare with our spec as well. All right, that takes care of that. Next, we need to move the code that updates the DSP instances with the latest parameter values into a function. So let's do that above process block. And we can move these so they're not just in the middle of the code base, like how this mono channel DSP member function is in the middle of all of this audio processor code. We can move it later. The point is just get it working and then make it look pretty. All right, so we're in process block. I'm gonna just put this code above it. Void project 13 audio processor, mono channel DSP, and we want the update DSP from params function here. And here's where we take all of this code. We're just gonna cut all of this, paste it here, and let's add a to-do, update general filter coefficients here. We'll do that later. These are all public members in the audio processor, so we need to access them that way. And we have our instance called P within our class, so we use that. P dot, then the member variable we're interested in. So add that to all of these. All right, that'll clear all of those error messages. Now we need to change process block to call this function for each mono channel instance instead of calling the previous code that updated all of the DSP instances from the params. So left channel dot update DSP from params, right channel dot update DSP from params. Excellent. All right, the final spot to update is the code that does the processing. That's down here. So let's move all of this code starting from DSP pointers. That's from right here. Move all of this code until the end of this for loop. And we're going to move all of that into a function. Take all of this. The only change that we need to make of the code that was moved is that we don't need to create a block from the buffer argument of process block inside of this function. And that's because this was done, my mistake. We're actually going all the way down to here. So we're taking all of this code. The only thing that we don't need to do is create this audio block. We're actually going to do that separately before we call all this stuff. So I'm going to put that function down here. Void, let's see, project 13 audio processor, mono channel DSP, and then process. That's fine. All right. Then we're going to grab all this DSP pointers all the way down to here. Cut that, and paste that there. All right. So same fix as before. We need to access the audio processor member for each of these guys. And this is the other part. We're going to get rid of that because we're passing in a block right there. All right. So let's go up to this function right here. This is where we actually call it. So first we need to create an audio block of our buffer. Auto block equals JUCE DSP audio block, and we want a float one, and it's being created from the buffer being passed into this function. So this is float, and our buffer is this buffer, the function argument. And now we can do left channel dot process. We're going to pass in our DSP order, and then for the block we want to get channel 0 because 0 is left, channel 1 is right. So block.get single channel block, we want channel 0. And then do that again for the right side. We go right channel, process, block.get, oops, spell that right, get single channel, channel 1, and we're passing it our DSP order. Okay, now try to compile that, and if you get no build errors, then try to run it. Let's see what happens. All right, build succeeded. If we run it, we should not get any JAsserts or experience any crashes. All right, look at that. Everything is working as before. 101, rerun, just make sure the save state functionality works. Okay, awesome. All right, so let's mark the to-do as done. Filters are mono, not stereo. Let's make a commit. Refactored DSP into mono instances. Awesome. Our next job will be to update the general filters coefficients. After that, we will add parameter value smoothers, and then we get started on the GUI. And when we do that, that's when we start running audio through this thing. Our job in this chapter is to get the general filter functional. We've got a bunch of other stuff working, but the general filter is different from the other DSP classes because it doesn't have member functions to adjust the various filter settings. Instead, we have to replace the coefficients member variable with a new coefficients object that is configured with these filter settings that we want. There are static functions that generate these coefficients, coefficient objects that we want to use. So here is the plugin processor, but over in IIRFilter, this is where we have all of these member functions like make first order low pass, make high pass, all that kind of stuff. These are what we are gonna make use of. All right. Our first order, let's close the plugin. Our first step is to do some work in plugin processor. In plugin processor.h, we need to add an enumeration that matches the list of general filter choices. So over in plugin processor.cpp, way at the top, we got our general filter choices. We need to make an enumeration that matches this. And the reason is because we're going to use this enumeration later to switch based on whichever filter type the user selects. So let's add the following enumeration that replicates this in here in plugin processor. Let's see, let's go to our public section. We'll call this enum class general filter mode. And we're going to paste this here. We're going to get rid of these. All these need to not be in quotes. Peak. We want bandpass to be in caps. Notch to be in caps. All pass to also be in caps. All right, there's our enumeration. Awesome. Next, we need to store the filter settings in the monochannel DSP instance. And why? Because every time process block is called, we are going to query the audio parameters for the latest values and update the DSP. Now, changing the filter coefficients is not a cheap operation. If the audio parameters value did not change, then there is no reason to change the filter coefficients. So how can we determine if the values didn't change? We store the previous value and we compare them with the current value. that is what these member variables that we're going to add to this class are going to store. I'm going to make all these private. So first of all, we got a general filter mode, and that's going to be end of list. Oh, we forgot to add that. It's always good to have. End of list. That's right here. Next, we need a float filter freak. That's going to default to 0. Filter Q, also going to default to 0. And then filter gain is going to default to -100. Those are our default values. Now, when deciding which default values to use, the only thing that matters is that the value chosen is outside the range of the respective audio parameter. Our filter frequency range is 20 to 20,000. Our filter Q range is, I think it's 0.1 to 10. And then the filter gain had a range of -24 to +24. So that's the only thing we care about. When we implement the code that checks if the previous value is different, this will guarantee that the first call to process block will produce coefficients for the filter, because these previous values, the default ones, are different from the parameter values. We are all done with plugin processor.h. Let's move to plugin processor.cpp. All right. Let's initialize the default DSP order with all DSP options. Go to the constructor. We're going to get rid of our fixed loop here. And instead, we're going to go for size t I equals 0. I is less than our DSP list. Let's see. Do it this way. We can go DSP order I equals static cast DSP option single one. And if I'm not sure about this, what I can do is static cast size t, do DSP option end of list. I can do that as well. And our next job is to compute the correct coefficients for the filter. Now, all of this code is going to go in the mono channel update from DSP Params function. Our first step is to query the general filter audio params here. So let's start with our sample rate. Auto sample rate equals our processor, get sample rate. And our first thing is update general filter coefficients. Our choices are peak, band pass, notch, and all pass. So let's figure out our mode. We do auto gen mode equals p.general filter mode, get index, because it's an audio choice param. Next, we've got our hertz value. So auto gen hertz equals p.gen freak hertz. Then we've got our quality. And then finally, we've got our gain, like that. Okay, next, we need to compare these values with the previous values. And the most efficient way that I've found is to use bitwise or equals for that. So bool filter changed equals false. Now we can do filter changed or equals. Now we can do a comparison. So let's compare our filter freak does not equal gen hz. And let's do this for the rest of them. Filter changed or equals filter q does not equal. Okay, so we got to do gain next. Filter gain does not equal gen. And then our updated mode, this is the last one, auto updated mode equals static cast to general filter mode, gen mode. And we can say filter changed or equals filter mode does not equal the updated. All right, here, now we know if the filter settings have changed. If the filter settings have changed, we will update the previous values, then generate the coefficients, and then update the filter with the new coefficients. So if filter changed, and we're going to do a bunch of stuff. So first things first, let's update our mode. Filter mode equals updated mode. Oops. Filter freak equals gen. Filter q equals gen. And then filter gain equals gen gain. Okay. Now, Filter coefficients are stored in JUCE DSP IIR coefficients. Let's see. Yes, right there. This guy right here. Now this class has a lot of static functions that produce instances depending on the type we need to create. Now we only have 4 types. We've got our, we've got our peak filter right here. We've got our band pass. Is that on here? Yep, there's band pass. Then we've got our notch and our all pass. Okay, so we're going to use the switch statement to figure out which filter type the user wants and then call these static functions to create coefficients. Now it's important to note that these are stored in reference counted pointer instances. Just remember that. All right, let's go back over here. We need to declare an instance of that guy. So JUCE DSP IIR coefficients. We want this one, float, and then pointer coefficient. And then let's switch on our filter mode. Give us choices, 5 enumeration choices, add missing cases. All right, for each of these, let's just get rid of our code for right now because we're going to fill it all in later, and we don't want these placeholders. Let's add curly braces around all of this stuff too. Okay. Now the static functions that produce coefficients require a sample rate. So let's get that. Or did we already get that? We already did get that. That's up here. We already got that. So we don't need to do that. All right. If we're in peak mode, we want to call the make peak filter function. So let's call that coefficients equals JUCE DSP IIR coefficients float make peak filter. All right. Our sample rate. Our frequency is going to be filter freak. Our quality value is going to be filter Q. And our gain factor needs to be converted from decibels, which is what the parameter is being stored in, into normalized gain values. So we go JUCE decibels to gain. And this is where we do filter gain. All right, that takes care of if it's a peak mode. Now, what is happening here? Did I spell this wrong? I did. All right, so let's fix that. Rename. Think for a moment. Band pass with a capital D. All right. All right, for band pass, we want to do coefficients equals JUCE DSP IIR coefficients float make band pass. We've got our sample rate, our frequency, and our quality. Sample rate, frequency, our own line. Okay, for notch, repeat the same process. Coefficient, we can just copy this whole line right here. Make notch, okay, sample rate, frequency, and quality. Awesome. And for all pass, same thing again, copy this, all pass, and copy this. Sample rate, frequency, quality. And then for the end of list, let's just add a JAssert. All right. Okay, at the end of our switch statement, I'm just going to collapse that so it's easy to see on screen. Okay, after the switch, 1 second. The JAssert false at the end of list case is important. If this case is hit, it means there's something wrong with the audio parameter or with the GUI widget that set the parameter value or with the settings file. This should never be hit, but if it ever is, that is the reason. So I'm going to condense this so I can add something here. Coefficient pointer instances have a default value of null pointer. So if the instance being populated in the switch is not null pointer, that means we can update the filter's coefficients. If coefficients is not null pointer, then we can do our thing. Now, one way to check if the coefficient update worked is to compare the size of the coefficients that were generated with the size of the coefficients currently assigned to the filter. So I'm going to just throw this in here just so that it makes, just to have it. If general filter DSP coefficients size, this is the actual array of coefficient values, does not equal coefficients size, or false. I'm going to comment this out later as needed. I'm doing this check to make sure that the filter coefficients are actually being generated, and I'm going to just get rid of this after I finally get this test the very first time. So coefficient objects are pointers and they must be dereferenced to be copied. And then finally, the filter must be reset after changing coefficients. So we do that here. General filter DSP coefficients equals our new coefficients, and then general filter. That wraps up the code needed to update the general filter with the latest parameter values. If you run the project, the very first time you run it, you should hit this JAssert. Watch this guy and see what happens. There it is. Okay. So just press continue a few times until you actually see the GUI pop up on screen. There's the GUI. Awesome. So now scroll down to the general filter parameters. And now is, go ahead and you can tweak some stuff. And each time you tweak it, we should see some of this code change. Now, I don't know off the top of my head if, peak coefficients are a different size than notch, but let's just try changing it from peak to notch and see what happened. Do anything? What about if we change this? Oh, that's fine. Okay. So now is a good time, if we kill this, if we close this out, now is a good time to change the project settings so that audio plugin host is actually launched instead of the standalone version. So I'm going to pause the video here. I'm going to insert the video that shows how to spin up audio plugin host as well as audio file player so you can feed audio through your plugin. And then once that is done, we're going to jump back in here and we'll get this set up. All right. The process for loading up audio plugin host and audio file player is going to be the same if you're on Mac or Windows. So I'm just going to do it here on Mac. The process for building them is actually going to be the same. That's what I mean. Okay. So first of all, go to your Project 13 folder, go to your JUCE repository, go to Extras, Audio Plugin Host, then find your juicer file, and you're going to open this. You're going to save and open in IDE. It's going to launch it here. And now you need to compile it. So just go ahead and build that. It's going to take a couple moments to compile. All right, build succeeded. Okay, that takes care of that. The next thing we have to do is download the repository for audio file player. So go ahead and close the plugin host project. All right, go to your GitHub. It's down here. All right, under my GitHub account, there is a repository called audio file player. This is the one you want. We're going to clone this, copy the URL to clipboard, go to fork, let's see, file, clone. We want to clone this guy, test your connection. All right, go ahead and clone that. Oh, looks like I've already done that. So let me just delete it so that way it's not on here, so you get the fresh experience. All right, let's try that one more time. Clone. Awesome. All right, that's currently cloning. All right, there's audio file player. Let's open this in Finder. Now this is currently using 7.0.5. I may need to update it to 8.0.6. I'm not sure yet. We'll find out. It's currently using the 7.0.5 modules that are bundled with it, which is fine. Let's see what happens when we try to build it. Okay, let's build this. Let's see what we get. Build input cannot be found. Yes, so this is going to want me to either change to 7.0.5 in ProJuicer or upgrade this project to use 8. So let me pause and figure out what I'm going to do there. All right, build succeeded. So for this guy, it actually does make sense to switch it to 8.0.6. So I'm going to update the repository to do that. It's a very simple change. Update it to v8.0.6. Commit and push that. All right. We've currently got audio file player loaded. So this plugin is compiled. Audio plugin host is also compiled. So now all we need to do is make it so that we've got a project. We have audio plugin host loaded whenever we want to launch the VST3 version. All right, so let's get that set up now. You can close audio file player. And we can go to here. We're not going to use the standalone version anymore. We're going to change this to launch audio plugin host. Now I'm going to insert a clip here for how to do this on Windows after I finish showing how to do it on Mac. On Mac, you switch to the VST3 target. You go to Edit Scheme, And then under info for the executable to launch, this is where you go look for the audio plugin host. Select other, and now we go look for audio plugin host. Let's see, where are you? Programming, project 13, JUCE, extras, audio plugin host, builds, and then the operating system I'm currently using, which is Mac, debug, audio plugin host, choose. All right. Okay, now when I run this, it's going to spin up audio plugin host. Running audio plugin host. All right. Audio plugin host, would you like to access files on your desktop? That's fine. Yep, all this is fine. Okay. All right, we've got a lot of stuff going on here. Let me create a new template. All right, this is what you'll see when you first start it. You may not have as many audio inputs and outputs. This is just because I have an Apogee Symphony, which has 16 channels of I/O and then some. That's all that is. Okay, let me pause right here and show what to do for Windows users. Be right back. Let's go set up audio plugin host. Navigate to your JUCE directory. Navigate to extras, navigate to audio plugin host. Navigate to the juicer file and open it up in ProJuicer. Save and open in IDE. Build it. Build the solution. Okay, build. 1 succeeded, 0 failed. Awesome. All right, we're done with audio plugin host. Okay, we can close the juicer file as well. All right, let's configure audio plugin host to launch whenever we have the VST3 as the startup project. Right click on the VST3 target, go down to properties, navigate to where it says debugging. We're going to change this command. So click on this arrow, go to browse, and we're going to look for audio plugin host. Build simple ME-comp. Navigate to the JUCE folder, navigate to the extras folder, audio plugin host, builds, Visual Studio 2019, x64, debug, app, and now audio plugin host.exe. Click apply and OK. Now we need to change the target from standalone to VST3. Change that to the startup project. And now if we build and run, it's going to fail on that copy step like we saw earlier. Let's do it anyway. All right, copy step failed. It's trying to copy to common programs wherever this thing is. Okay, so what we need to do is change the permissions of this folder to allow the current user, which is whoever we are logged in as, we need to give them write permission to this folder. So open up Explorer. This is located in the C drive, program files, common files. This is where Visual Studio is trying to copy this file to. So right click, create a folder, call it VST3. And then the second part of this is to change the permissions so that the logged in user can write to this folder, because Visual Studio is being run under that user's settings. Okay, so right click on this, go to properties, go to security, click on edit to change the permissions. And then we need to change the permissions for the user to be able to modify. Apply, okay, okay. All right, let's try this one more time. Let's see if it throws an error or not. Okay, cool, copy step completed. If we go back over here, let's see, where was that? Let's just press stop real quick. If we go to the build and scroll up to the top, we can see that one file was copied correctly. All right, let's go ahead and launch this. All right, our first step is to scan for plugins. Go to the options menu, edit list of available plugins. And here's where we are going to scan for new or updated VST3s. This is going to look in library audio plugins VST3. Now the important thing that makes this actually work is over in ProJuicer, there is a plugin copy step that we have to enable. Let me see, it's under the gear. Could be mistaken. It could be under the exporters. There it is. All right, so for Visual Studio, you want to make sure that enable plugin step is turned on. Click on your exporter to do that. Same for release, enable plugin copy step. Same thing on Mac, enable plugin copy step. It defaults to being enabled, but just make sure. Now, the default place is it's going to put it in your, where did that go? It's going to put it in this folder right here, the home folder. If you have a ton of plugins here, I recommend getting rid of that. The other thing you can do is go into your file browser, go to where all of your plugins are. So in my case, let's turn on hidden files. We go to library, audio, plugins. It's going to be looking for the VST3 in here. You can see I've got a bunch of other plugins. And if I don't want those to be scanned, I should just move them all out. So let me just do that right now. Let me move Simple EQ. Let me move audio. Let's leave audio file player. We're going to move this guy and project 12. Okay, so now the only things it's going to scan are project 13 and audio file player. There it goes. That was super quick. There's audio file player. And then way down here is project 13. And if we remove any plugins whose files no longer exist, we'll see project 12 disappear and a few others disappear. Project 12 just disappeared, as did Simple EQ is still there. Oh, because it's an audio unit. All right, that makes sense. Okay, cool. So the next thing to do is instantiate audio file player. It's going to be under Matcat Music. All right, let's take a look at that. That's what that looks like. Okay, then we need to instantiate project 13. That's going to be under your company if you didn't provide a name. If you did, it'll show up under that name, project 13. We're hitting a JAssert because it's creating it for the first time. Oh, because I forgot to comment this out. Just press continue a few times. There's project 13. Now we need to wire them up. So click from this node to that node and this node to that node, and then wire these up to the outputs of your audio interface. And then now, if you load a file into audio file player, you'll be able to run sound through your GUI and adjust everything. Let's see, I'm going to go find an audio file and I'll get that loaded up in just a second. All right, I've got a piece of music loaded up. Everybody's favorite, the intro song I use for all of the tutorials that I make. Let's get this guy turned down a little bit. And if we push play, we will hear it running through our plugin. Let's get that GUI up. Let's see, what does this say next? All right, if we push play, we probably won't hear anything. Let's see. Yeah, that's super muddled. The reason is because the overdrive filter does not have its cutoff set. So let's go to the overdrive and just bypass it. And now we get all the frequencies back. Okay, so let's leave that guy bypassed, and then let's start tweaking our general filter to hear the effects. So we'll adjust our Q on this thing, make a big notch. Peek it out a little bit. All right, cool. That's working. Let's add our ladder filter. Let's make this guy get in there. Let's add some drive. See, it gets crunchy real quick. All right, you get the point. Okay, that's working. So you might notice that there are some audible artifacts when adjusting the filter settings. These issues are solved in the bonus content, specifically the section on thread safe filter updating. If everything works as expected, excluding those audio artifacts that you hear when dragging the sliders, we can clear this to do and make a commit. Let's go to here. Let's go to our to-do. Let's comment this out first of all. Then let's go to our to-do. This was update general filter. This should be coefficients, not corrections. Update general filter coefficients. That is done. Awesome. All right, let's make that a commit. Not audio file player. This would be not for that. This would be for project 13. All right, this commit message is implemented. Update filter DSP from update general filter coefficients. Close that. Did we do all that? Yes, we did. Okay. All right. Commit. Awesome. All right, in the next chapter, we'll add smoothers for all of the smoothable audio parameters. All right, so the basic DSP that we've built works correctly. However, drastic parameter changes can cause audio artifacts, and the solution is to smooth all of those changes to the parameter values with a class that JUCE has called JUCE Smoothed Value. Let's go look for that. Take a quick glance at what's in it. Let's see, smoothed value, here we go. Okay, smoothed value.h. All right, so it's got a pretty simple interface. You can get the current value, you can get the target value, you can set the current and target value, and then it also has stuff for applying it to audio. All right, so pretty simple to use. This is the smoothed value base class, and then there's two different smoothing types. There's linear smoothing and then multiplicative smoothing. Here's the smoothed value class itself, which just builds on top of that other class. Set it to our ideal initial value that we want, reset it to a specific duration to take to smooth from one value to another, and then we can set our target value. We can get the next value. We can skip, and then this is the old set value. Okay, all right, so we need to initialize one of these for every single one of these audio parameter floats. All right, so we're going to add the following declarations to plugin processor.h after all of the cached parameters and before the private keyword. So we'll put them above our general filter. So we've got our phaser rate, center frequency, hertz, our depth, and our feedback and our mix. That takes care of the 5 phaser params. Those guys right here. Then we've got our chorus, let's see, rate, depth, center, feedback, mix. So chorus, rate, depth, center delay, feedback, and mix. We've got our overdrive saturation level, that's here. Then we have our ladder filter, cutoff, resonance, and drive. That's here, cutoff, resonance, and drive. And then finally our general filter, frequency, quality, and gain. General filter, frequency smoother, quality smoother, and gain smoother. Okay. Now, smoothed value instances need to be prepared and updated with target values. We will want to do this every process block, and instead of updating each one by name, let's create a function that will return all of them in an array of pointers. Let's add the following declaration to the end of the audio processor class. Put this way down here. std vector JUCE smoothed value float type pointer, because we're returning an array of pointers to all of these, get smoothers. This is going to allow us to loop through them. Now, smoothed value instances have their current and target value set in one of two ways: forced and transitioned. Now, forced means that the current value is also set to the target value, resulting in no value smoothing. Transitioned means that the current value is left as it is and the target value is changed, and all of the smooth value member variables that control how many steps it takes to go from this point to this point are recalculated. Now, there are two ways of setting the target value. These two ways of setting the target value are represented by this function up here. Set current and target value. This is the these guys right here. There's this one, and then there is set target value, which is set target value down here. So set target value is the transitioned version, and set current and target value is the forced version. Set current and target value is used when you are initializing the smoothed value, and set target value is used in process block to constantly adjust the target value that the smoothed value is smoothing towards. We want to be able to configure our smoothers easily, so let's create an enum defining the two ways that the smoother can be updated, and then create a function that uses that enum to decide which of the two smoothed value member functions to call to set that smoothers target value. Let's put the following after this get smoothers function, way down here. Enum class smoother update mode, and we've got initialize, and then live in real time. All right, and let's add a function after this. Void update smoothers from params. This will be int num samples to skip, and then smoother update mode. We want to include the number of samples to skip because we'll be updating the DSP from the params once per process block as opposed to once per sample. Therefore, we need to skip the number of samples that the buffer passed into process block has each time we update the smoothers. And this wraps up our work in the header file. Let's switch to plugin processor.cpp next. Let's go implement get smoothers. What do you want? What do you want? Come back and say hi to everybody. We have a guest on the video right now. All right, let's go create a function somewhere. Maybe right here. Okay. We are going to create a function that internally declares an std vector of pointers to smoothed values. It initializes that vector with pointers to each smoothed value member, and then it returns the vector. Here's what that looks like. Actually, I'm going to put this after prepared. So here is the vector that is initialized with all of the addresses of all of the smoother members. Next, let's use this function to prepare all of the smoothers. Smoothers are prepared by setting their transition time and setting the sample rate that they'll be operating under. At the end of preparative play, add the following loop. Myself a little bit more space. For auto smoother in get smoothers. Smoother reset our sample rate and our ramp length in seconds. I want to have a 5 millisecond smoothing time, so that's going to be 0.005. That's it. Now our smoothers are all prepared. Next, we need to set the target value for all of these smoothers. We will do that in the update smoothers from params function next. Now this function's job is to read all of the parameters that need smoothing and update the target value and possibly the current value of their associated smoother. The easiest way to do this is to create an array of params that is in the same order as the vector returned from get smoothers, same order as this, and then loop over that list and update accordingly. All right, so I'm just going to put that right here. Void project 13 audio update smoothers from params. All right, so this needs to be in the same order as, so the easiest thing to do is go auto params needing smoothing, and then all of these parameter names are the parameter name with the word smoother attached to it. So we just, and boom, that takes care of that problem. Very convenient. Just if you didn't follow your names exactly, just be very careful when you create this array. If you're not careful, it is easy to accidentally update the phaser depth from, say, the phaser rate smoother because the two lists didn't maintain the same. Next, let's get the smoothers and make sure the lists are the same size. Auto smoothers equals get smoothers, and then jassert smoothers.size equals params needing smoothing.size. This way we can always, if we ever hit this, it means that our lists are out of date. Next, we need to loop through the list, or size t I equals 0, I is less than .size. We need to get a smoother and a parameter, and depending on the smoother update mode, we need to call one of those two member functions initialize. Auto smoother, smoothers, auto param equals params needing smoothing, and then if init equals smoother update mode initialize, then we can go smoother, set current and target value, be param else smoother, set target value. Super simple. What is happening here? I think I need get value. These don't need to be pointers. That's why, because they are already pointers. We don't need to take that. My mistake. Now we need to get. So be very careful of that. You're not taking the address of those member variables because the member variables themselves are already pointers. We're just taking a copy of them. Finally, since we are updating our params once per process block, the smoothers need to skip ahead the same number of samples that the buffer passed into the process block has. So we go smoother, skip, num samples. There's the full function. Super simple. Let's go back to prepare to play and call this function. at the end after we reset all of our guys. Update smoothers from params. We're going to skip one sample and we're going to put it in initialize mode. Smoother update. So the current value and the target value of each smoother is identical. So telling each smoother to skip one sample shouldn't have any effect on the smoother's internal state. 2 more jobs left before this chapter is over. We have to update the DSP settings from the smoothers, and then we have to update the processing loop to operate on blocks of at most 64 samples. Let's do the first job. Every DSP instance is currently updated from its associated audio parameter. Let's go to that function from params. Replace the code in the parentheses with a call to the smoothers get current value function. Rate hertz smoother at current value. So do that for every single one of these guys. Do that for every single one of these. All right, here is what your final implementation should look like after you. Now, while you're here, comment out the JAssert in the code that updates the filter coefficients, if it's not already commented out. We tested it last time to prove that the coefficients were being updated, and we no longer need this code, so we can just. Our last step is to update process blocks so that it operates on blocks of at most 64 samples at a time. Let's go to process block and think about this for a moment. Here is how this will work. Number 1, we will get the number of samples that need processing. Number 2, we will compute the maximum number of samples to process at a time with a maximum of 64. And then number 3, we will do the following with the current block as long as there are samples to process. Compute the number of samples to process during this sub-block, update the smoothers from the parameters, update the mono channels from the smoothers, create a sub-block that holds max samples of audio from the original block, process each of those channels, and then increment the number of samples processed and decrement the number of samples remaining. We will also need a counter to keep track of the start sample for a particular subblock. Here is what that implementation looks like. All right. So, per the instructions, number 1 is get the number of samples that need processing. Number 2 is compute the maximum number of samples to process at a time by finding out if there are more or less than 64 and capping it at 64. Then we need to get that current block, and we need to compute the number of samples to process during this subblock. So that's the first thing we do. And the example I'm giving here is you might have a buffer size of 72. The first time through this loop, we need to process 64 because max samples to process is set to 64 and samples remaining is 72. The second time you run this loop, samples to process will be 8 because the previous loop consumed 64 of those 72. All right, so step number 4, compute the number of samples to process inside of this sub block. And then for number 5, we want to update the smoothers from the parameters using that amount of samples to process. Then for step 6, we want to update the mono channels from the smoothers. Number 7, we want to create a sub block that holds the maximum number of samples that we're going to process. That's what this part is right here. Starting at some index in the, we're going to process each channel. That's this part right here. And then we're going to increment the number of samples processed, and we're going to decrement the number of samples remaining. And here is our counter for keeping track of how to start at for our sub block. All right. You should be able to run and test your plugin with Audio Plugin Host. Oh, and it's probably going to say, hey, do you want to save this? So it'd be a good idea to save that. Let's put this in Project 13 and go Project 13 filter graph. This way, all right. Go ahead and run and test your plugin. You should be able to make drastic slider changes and still hear smooth changes with no audible artifacts. So I'm going to test this out with the phaser. All right, so we'll go to phaser. I'm going to set my phaser depth. Let's see, I'm going to bypass everything else. Chorus bypass, ladder filter bypass, general filter bypass. Yes, cool. All right, I'm going to set my phaser depth at like 35%. All right, had to break out the headphones for this. So I'm going to set this back to the beginning. Again, 35% phaser depth, even though it says 0.35, because the parameter range is from 0 to 1, not 0 to 100. I'm going to set my phaser mix down. Let's turn this on. Check out how this sounds. can hear it sounding pretty good. Speed that up. Whoa. All right. All right, that sounds pretty awesome. So I think we can make a commit. Doing what it's supposed to do. All right. If you experienced something similar when you were listening back and messing with the controls, we can mark this to-do as done. Let's go to my to-do list, update, add all smoothers for all param updates, done, and make a commit. Also, we add our filter graph. Added smoothers for all param updates. Awesome. All right. Now here are 2 more to-dos to add to the list. Number 1. Restore tabs in GUI when loading. Save load presets. Let's commit these to-dos as well. Added to. All right, we have finished the majority of the DSP work, and now it's time to get started on the GUI and start working our way towards building this thing here. We're gonna get our spectrum analyzer, we're gonna get our meters on the side. Now this is currently showing all of the stuff that's available in the bonus content. We're gonna be able to drag and drop all of our stuff and reorder all these things, see the different controls, whatnot. That's what we're gonna be working for. Okay, that'll be a good time. So the guys here are the modulator values, so we can modulate all this stuff. All right, we want to modulate our rate. Okay, let's get started on the GUI in the next video. All right, in this chapter, we will get started on producing a GUI that allows us to control each DSP effect. Now, I want to use a tabbed component for the GUI because this will enable the GUI to remain fairly small and repurpose a lot of screen real estate, as opposed to having a static GUI that always shows the controls for each DSP element. And by using a tabbed GUI, it will be very obvious what the DSP order is by the order that the tabs are displayed in. One of our jobs will be to make the tabs draggable so that they can be reordered. This is the way that we will implement the ability to dynamically change the processing order of the effects. In plugin processor.cpp, switch to using the non-generic editor. And the remaining work that we're going to do is entirely in plugineditor.h and plugineditor.cpp. Now, the JUCE forum contains a very helpful hint from Jules himself, the guy who created JUCE, explaining how to make draggable tabs in a tabbed component. Let me see if I can find that. Is this the one? Right here. You can create a subclass of tabbed button bar, which is also a drag and drop target. And you can create custom tab buttons which allow themselves to be dragged. So this is fairly easy to implement if we follow his recommendation verbatim. Let's get started on that. So we need to create a class that inherits from tabbed button bar and drag and drop target. Let's take a look at drag and drop target. Drag and drop container. Let's go to the header file, drag and drop target. Now, drag and drop target contains some virtual functions. This one right here is interested in drag source, drag item enter, drag item move, drag item exit, and item dropped. Okay, so we just need to provide default implementations of that for now. We will figure out what to put in them later. And I have included a link to the post above. All right, okay. So in our plugin editor header file, we need to add a class for this extended tabbed button bar, which is going to be a drag and drop target as well as a tabbed button bar. So let's put that here. Oops, I'm typing in the wrong place. All right. Struct extended. Okay, I'm also putting the quote in the I'm putting the quote from the forum link as part of the comment, just so I have access to it. All right. Again, we've got our default implementations and blank implementations for the two that we actually really care about. Is interested in drag source and item dropped. Okay. Now you'll notice at the end of this snippet that I am starting the custom tab bar buttons, which allow themselves to be dragged but have not added anything to it. We will make the tabs draggable in the future. Now the last thing we need to do in this header file is to give ourselves an instance of this class in the editor. So let's do this below our DSP order button. We're going to go JUCE tabbed button. Oh, I'm sorry. We're going to go extended tabbed button bar and tabbed component. And that's because when I was developing this, I was messing around with the JUCE tabbed component. Okay, let's move to plugineditor.cpp. And for this chapter, we're going to make use of the DSP order button.onClick lambda to populate the tabbed component with tabs. Every time we click the button, we will get a new DSP order. We will update the tabbed component, and we will push the order to the audio processor. While we won't be able to control each DSP element, we will be able to add breakpoints in process block and verify that the DSP order generated randomly is what is being used in process block. So in the onClick lambda mentioned, our first job will be to clear the tabs. So let's go to our lambda. All right, here's our DSP order. Here's where we create the range. And before we create our loop, this is where we're going to go tabbed component and clear tabs. All right, next, inside the loop, we want to add a tab to the tabbed components. The add tab function expects a string to be passed to it. So this is what we're going to do. Tabbed component.add tab. That it expects a string to be passed to it that sets the tab's name. Let's create a function that converts this entry, which is now a DSP option, into a JUCE string, and put that function at the top of this CPP file. It's going to be a static function. For each of the types, under DSP option, whoops, in each of these, the wrong thing. In each of these options, we're going to return a string. String get name, project, processor. All right, we're going to switch on it, get rid of this part, and wait for autocomplete to give us all the choices. All right, return phase. And I want these to be in all caps, so it's it has a certain look to it. Okay, we fill that in the rest of the way. All right, last but not least, if we, for whatever reason, hit end of list, let's just do a, we already did our JS at false, so now we just need to return no selection. Okay, now we can call that function when creating the tabs inside the loop. Get DSP option name, V. All right, now for color, I'm just gonna go with a white color. Colors white, and my insert index is gonna be -1, meaning put it at the end of the list. Semicolon. Okay. Now we need to add the tabbed component to the editor. Add and make visible tabbed component. And then our last job is to give this tabbed component some bounds. Let's place it below the DSP order. And we'll do this by getting our local bounds. Auto bounds equals get local bounds. Now our DSP order button is going to be bounds.remove from top 30, width, size, keeping center. We'll give it a width of 150 and a height. So we've got our GUI like here. We're ripping off the top 30, and then within this long rectangle, instead of setting the DSP order to go from the far left of the GUI to the far right, we're going to say, you know what, keep it in the center, but keep the width 150 and with the same height of 30. That's what that's doing. All right. And then finally, let's add a little gap. Bounds.remove from top. So we're trimming off the remaining bounds. And now we're going to set the tabbed component to use another row that's 30 tall. Set bounds from that. Bounds.with height 30. I could have also done bounds.remove from top 30 like that. All right, let's run our project and take a look. Oh, you know what? Let's get rid of this JAssert false. If we do hit this JAssert, actually, we'll leave it in. But let's inspect our order and see what this looks like. Okay, so we have no tabs. Let's push the DSP order button. Okay, now we can see general filter, ladder filter, overdrive, overdrive, ladder filter. Cool. So we should now see tabs when we do that. General filter, ladder filter, overdrive, overdrive, ladder filter. Awesome. Okay. Let's do that one more time. I'm just going to halt execution. So this way it doesn't save the changes to disk, because we're going to do one more check to make sure that it's actually doing the thing and passing the correct tab order over to the GUI. This will be the last time we test this. All right, let's go to process block. Well, we'll do it this way. Let's push the button first so we hit that JAssert false. Okay, we got our list, ladder filter, 3 choruses and a phaser. Now let's go to plugin processor, go to our process block. Let's see, where is that being done here? Samples remaining. All right, let's just add our breakpoint right there. And let's press continue now. And we should see, if we inspect DSP order, we should see the exact same thing with 3 chorus instances there. So continue. Now we can look here at DSP order. Where is that? That's way down here. See 3 choruses like that. All right, perfect. Continue. Well, let's get rid of this breakpoint. Now press continue, and we can go look at our GUI, and we can see our 3 chorus instances. Fantastic. All right, let's get rid of our JAssert false back in the GUI. Let's go right here. It's time to make a commit. Get that at our filter graph. Okay, we're gonna commit all this stuff. What did we do in plugin processor? Oh, we switched to the different editor. Okay. All right. Our commit message is, because we're exploring right now, added test to create tabs from DSP options array. All right. Next, let's make these tabs draggable. This is very easy to do. We just simply add a component dragger to the tab itself, activate it in the mouse handler functions, and that's it. So plugin editor, we've got our extended tab bar button. We need to add a constructor, extended tab bar button. It's going to need a name. It's going to need a tabbed owner, because that's who's going to do the dragging. Or I'm sorry, I misspoke on that. So tabbed button bar, we're currently not using it anywhere, but if we look at this class, there it is, tabbed button bar. Okay. So the tabbed button bar, we want the tabbed bar button is what we want. Tabbed button bar. So here it is, tab bar button. Okay, this thing wants a string and a owner bar passed to it. We are currently inheriting from tab bar button, so we need to provide a constructor that does the same thing, because this class only has the one constructor and requires these things passed to it. All right, so let's dig in on this. We've got our constructor that duplicates. It's just going to forward those values to the tab bar button constructor. Now we need our component dragger, JUCE component dragger, called the dragger. And then in our mouse down and mouse drag functions, we need to call those functions, the dragging functions. So let's go look at our component dragger. Component dragger, there it is. That took a really long time to search for. All right. An object to take care of the logic for dragging components around with the mouse. Very easy to use. In your mouse down callback, call start dragging component. And then in your mouse drag, call drag component. And then when starting a drag, you can give it a component bounds constrainer to use to limit the component's position and keep it on screen. We are going to make use of that a little bit later. All right, so here's the example. You know what? We can just copy this. We can just copy this exactly. Just got to change the name a little bit. Like that, and then these are just called my dragger, or these are just called dragger, and then these are JUCE namespace mouse events. Okay, start dragging component in mouse down and drag component in mouse drag. All right, if we want the extended tabbed button bar, this thing, if we want this to use these tab bar buttons, we need to make its create tab button function return instances of this class. Now that function, let's go look at tabbed button bar. Find that, I believe it's virtual. We want create tab. Right there, this creates one of the tabs. If you need to use custom tab components, you can override this method and return your own class instead of the default. So we are gonna implement this. All right, so after our item dropped, we'll add this here. JUCE tab bar button pointer. Let's just grab it from here. JUCE namespace, override, and this needs to namespace like that. Okay, Let's head over to the CPP file and implement the extended tab bar button constructor and the create tab button function. Let's do this up at the top. Let's do the constructor first. Extended tab bar button. Extended tab bar button. And it was a string and an owner. Let's make sure of that. Yeah, we can just copy this. All right, so just call the base class JUCE tab bar button. There it is. So pass the name and the owner. That's it. Okay, there's our constructor. And now in extended tab button bar, we want to implement our create tab function. JUCE tab bar button. And this is going to be extend tabbed. Come on, autocomplete. Let's just copy it from here. Create tab button, colon, then that. All right, return new extended tab bar button. And we're passing it the tab name as well as this, because the extended tabbed button bar is the owner. All right, now run the project. With these two little steps, you should be able to drag the tabs. All right, DSP order. Now you can click and drag them, move them wherever you want. They are not constrained, they don't snap, they're just draggable rectangle components. If that is what you see, then go ahead and make a commit. Awesome. Tab buttons are now draggable, but need constraining. All right. Our next job will be to constrain the dragging to be on the horizontal axis only. Okay, we have two tasks to complete in this chapter. Number one, implement horizontal constraining when dragging the tabs. And then number two, bring the dragged tab to the front of all available tabs. Let's implement the first, horizontal constraining when dragging a tab. Now, horizontal constraining is achieved by adding a component bounds constrainer and passing it to the component dragger. Let's go back here to this thing, component dragger. All right, where it is we find that? Here it is. Okay, an optional constrainer object that should be used to apply limits to the component's position. Pass null if you don't want to constrain the movement. And we can see here in our code that we are passing null pointer. Right there. Okay. So we will need to customize the behavior of this class. So let's begin by declaring a class that inherits from component bounds constrainer right here. Horizontal constrainer. This inherits from JUCE component bounds constrainer. Let's go take a look at the component dragger container and the component bounds constrainer class. All right. With the component bounds constrainer, there is a virtual function that we will override. But if we'll find it, okay, here it is. This is the specific function that we need to customize. And inside this function, we will control the resulting rectangle, this one right here, that our component can be dragged within. The first function argument of this function is a reference to a JUCE rectangle, and this is an in-out parameter, meaning that we are going to modify its value, and the result of our modifications will persist after the function exits. We need to know several properties about our constraining area within this member function. Specifically, we need to know both the bounding box of the tabbed button bar of this thing. We need to know the bounding box of that, as well as the bounding box of our button itself. And the easiest way to pass that information into this function is to use getter lambdas that we set when we construct an instance of our horizontal constrainer. We now know all of the requirements for our derived component bounds constrainer class and can begin implementing it. We know that we need to get bounding boxes from these getter lambdas, so we will make our constructor take lambdas that return JUCE rectangle instances. Let's do that. So horizontal constrainer, and our first thing is going to be std function JUCE rectangle. This thing is going to return a rectangle. It's going to take no parameters. That is our std function. This is going to be the confiner bounds getter. And then we need the thing that is being confined. So std function rectangle, again, confine bounds getter. Okay, we got the thing that is being confined, and the thing that is doing the confining, and the thing that is being confined. Next, we need to implement the check bounds function using our custom implementation. So let's override that. Copy this guy, add it to our declaration. That indentation is fine. Override it. And then finally, we need to have lambdas that we can call inside of this check bounds function. So let's create some member variables that our constructor will initialize. And remember, they must return JUCE rectangle instances because these bounding boxes are stored as JUCE rectangle instances in the... Why is this complaining? Oh, because this needs JUCE. Okay, let's add these in the private section. Now, I'm going to just paste these guys here. I'm going to fix these names. I am going to choose the name bounds to confine getter, and then bounds of confinee. So I pasted these here. I changed these names. I chose the name bounds to confine to getter for the getter function that will return the bounding box of the tabbed bar. That's the component we're confining the dragging range to. And the name bounds of confinee for the bounding box of the tab itself that is being dragged. In order to construct one of these, we need to know the lambdas. We don't know those until after we construct the tabbed button bar, so we must use a unique pointer to store this constrainer object. So let's add that here. std unique pointer, horizontal constrainer. We still have to construct it, but since we were working in the header file, let's make use of this constrainer in the mouse drag function. Let's go right here and go constrainer.get. All right, that's it for the header file. Let's move to the CPP file. All right, let's take care of that constructor first. Let's just put it right here. Horizontal constrainer with our two lambdas, and then initializing the member variables. And ideally we would use move semantics for these, but we're not really doing anything with them. std move. Okay, now for the check bounds function. For the check bounds function, I am going to provide you with my implementation, and in the written tutorial, I'm going to provide comments. I'm going to read those comments here. That they are going to explain the way this is architected. This thrown up on screen so you can see it and read along with me. Okay, so in the horizontal constrainer, bounds, this thing right here, is the bounding box that we are trying to set component to confine. We only want to support horizontal dragging within the tab button bar. So we want to retain the existing Y position given to the tab bar button by the tabbed button bar when the button was created. So the first thing we do is we set the bounds of this constrainer, of this the bounding box we were trying to constrain, to have that Y position. Next, the X position needs to be limited to the left and right side of the owning tabbed button bar. However, to prevent the right side of the tab bar button from being dragged outside the bounds of the tabbed button bar, we must subtract the width of this button from the right side of the tabbed button bar. In order for this to work, we need to know the bounds of both the tabbed button bar and the tab bar button. Hence, loose coupling using lambda getter functions via the constructor parameters, and loose coupling is preferred versus tight coupling. So as long as those two lambdas are not null, we can get the bounding box of the thing we're trying to restrict our movement to and get the bounds of the thing being confined. We want to set our X position to be within that range. So for the JLimit function, we are limiting our movement to be between the left edge of the tabbed bar and the right edge of the tabbed bar minus the width of the tab. If our tab bar is this wide and our tab is this wide, we're saying you can constrain from here to there. So that way when the left edge of the tab hits this point, it won't extend past the right edge of the tab bar itself. Okay, that's what this does. And then otherwise, then we're just within the regular limits that get passed in normally. Our final step is to initialize this constrainer. Remember that the lambdas need to return the bounding boxes of the button bar and the button itself respectively. So in our extended tab bar button, in this constructor, this is where we're going to do constrainer equals std make unique horizontal constrainer. That closing caret removes this stuff, semicolon. All right, now we can provide our two lambdas. Okay, the confiner bounds getter. This is going to be, we're capturing we want to get the bounding box of the owner. So we do first capture the owner, and then there's no arguments to this guy. And we're just going to return owner.get local bounds. That's how we get the bounding box of the owner. And then the bounding box of this tab itself, we want those relative to the tab button bar itself. So we don't use get local bounds for the extended tab bar button. We use the bounds within the owner. So let's capture this guy, no arguments, and then this is going to be return get bounds, not get local bounds, because these bounds are inside of the owner's local. All right, finally, we need to set our constrainers minimum and maximum on-screen amounts, or just the minimum on-screen amounts. And regarding the minimum on-screen amounts, take a look at this function. All right, if you pass a very large number, then the component won't be allowed to overlap that edge at all. What edge are they talking about? Well, this sets the amount by which the component is allowed to go off screen. The values indicate how many pixels must remain on screen when dragged off one of its parent's edges. So if minimum when off the top is set to 10, then when the component goes off the top of the screen, its Y position will be clipped so that there is always at least 10 pixels on screen. If you pass 0 or less, the component is allowed to move beyond that edge completely with no restrictions at all. If you pass very large numbers, then the component won't be allowed to overlap that edge at all. So setting minimum when off to the left to this giant number, that will mean the component will bump into the left side of the screen and go no further. So we want to do that for all of these values. And we do that. Constrainer, set minimum on screen amounts. And we're going to use that value they had, 0x 1, 2, 3, 4, 5, 6, 7, 8. Just a huge integer number for all of these. All right, with all of this in place, let's try running it, and let's try dragging the tabs. And they should be limited to the horizontal direction only, and only within the bounding box of the bar that owns them. So let's create an order. I should not be able to drag them up and down. You can see I'm moving my mouse up and down, but they only move left and right. Let's see, let's grab this ladder filter because it's on top of everybody else. It won't go left, and then it's going to the far right edge and will go no further. So this is doing all of the stuff we want it to do. It's staying within the bounds of the tab bar button. You can only drag it left and right. You can't drag it up and down. And no part of the tab button is actually being clipped off the screen. That's perfect. Awesome. All right, if that is what you experience when you try dragging it yourself on your own version that's running, go ahead and make a commit. Implemented horizontal dragging constraints, C comments. Let's tackle the next thing on our list, moving the tab that is being dragged to the front of all other tabs. This is very simple to do. All we need to do is in the mouse down function, this guy over here under mouse down, we need to move that tab to the front of all the others. And the other thing we need to do is to make sure that we call the base class's mouse down function from inside our mouse down implementation. That looks like this. First of all, to front, true. That's the first step. Then call the base class version, JUCE tab bar button mouse down. That's the next thing to do. And run and test. If you've done this correctly, you should see the tab that is being dragged sitting in front of all of the other tabs when it is clicked and dragged. Tab order. All right, so I'm going to click on phase. We know that overdrive is the very first one. I'm going to click on phase, and we can see that it is on top of all of the others. I'll put that there. All right, let me click on overdrive. That is now on top. All right, that's good times. Okay, cool. All right, let's make a commit. And this is dragged tab is brought to front when dragged. The last thing I want to do is in preparation for the next part of the project, starting to implement drag to reorder. all of these header file implementations will need to be moved to the CPP file. So let's go ahead and do that. Grab these guys. And you know what? These were never marked override, and they should have been. Let's see. The next are these implementations right here. Let's move these over to the constructor right above create tab button. Override keyword. And let's put these curly braces on their own line with no other code. All right, and I like to have this in between my classes. And last one. All right, let's get rid of these from this part. Semicolon, semicolon, and okay. Let's build and test. The plugin should behave exactly as it did before. Oh, what did I forget? Colon there. All right, build succeeded. Let's run this. Create an order, and then let's drag this overdrive to be over here. And we still get all of our same dragging behavior. It keeps recreating the list every time I release the mouse. That's fine. We're gonna implement drag to reorder in the next chapter. Let's make a commit though. And this is moved implementations to CPP file. Okay. The next chapter is going to focus on implementing drag to reorder. Well, let's get to it in just a moment. Welcome to chapter 21. In this chapter, we're going to take our first steps toward implementing drag to reorder. The goal for this step is to accomplish swapping the tabs correctly after they are dragged and dropped. By the end of this chapter, we should be able to do that. Drag to reorder is accomplished by the tab button bar being a drag and drop target and a drag and drop container, and by listening for mouse events on each tab bar button. So drag and drop container and drag and drop, let's go see if we can find those. All right, so we got drag and drop target. This is where you are dropping something, AKA we implement this callback, which is called when the user has dropped something onto this component. And then we also have the drag and drop container. Just start dragging this stuff down here. All we really care about is this part right here. For a component to be able to make or receive drag and drop events, one of its parent components must derive from this class. It's probably best for the top level component to implement it. Then to start a drag operation, any subcomponent can just call the start dragging method, and this object will take over tracking the mouse and sending appropriate callbacks to any child components derived from drag and drop target, which the mouse moves over. All right, so the sequence flow, let's go over here and look at this stuff. The sequence flow will be, number one, we mouse down on a tab. This event starts the drag and drop container responding to mouse drag events. Item drag enter, let's go find that. Is that in here? That is in the drag and drop target. Item drag enter is called when the first mouse event happens inside of the drag and drop container. As the mouse is moved, item drag move is called. The tab bar buttons are constrained to the bounds of the extended tab bar button, so they will never be dragged beyond the bounds. And then item drag move checks the x coordinate of the item being dragged and compares it with its neighbors. And then tab indexes are swapped if a tab crosses over the middle of another tab. Let's just run this real quick and we can just kind of talk through about what it's going to do when I click and drag on something. So with my tabs here, let me put this in the middle. With my overdrive, if I click and drag this, the whole point is when this thing slides past the gen filter block, the index of these two are going to switch places, meaning right now overdrive is in the index 1 and gen filter is in index 2. When we click and drag this over, they're going to switch, meaning gen filter is going to be here in index 1 and overdrive is going to be in index 2. We're going to do that all programmatically. Okay, let's quit this. All right, let's update the extended tabbed button bar, the following snippet of code, and also we've got drag and drop target, but we also need it to be a JUCE drag and drop container. All right, so we've got our is interested in drag source. We've got our item dropped. But now we also need item drag enter, item drag move, and item drag exit. I'm going to put a comment in here, which is the thing I literally just said about how this is going to work, along with the, all right, so there's the drag and drop. There's the drag to reorder and how it is accomplished. Sequence flow is mouse down on a tab. This starts the drag and drop container responding to mouse drag events. Then item drag enter is called, and then the mouse is moved. As the mouse is moved, item drag move is called. And then item drag move checks the X coordinates, and tab indexes are swapped if a tab crosses over the middle of another tab. And we need our mouse down function. So void mouse down mouse event. This is where the dragging thing happens. All right, to make an external component respond to mouse events on separate components, we need to listen to mouse events on those other components. In our case, we want to listen for mouse down events on the tabs themselves, and we want the tab button bar to respond to those events. That means when we create the tabs, we need to start listening to mouse events on those tabs. To do that, we need to start listening before we return the pointer to the tab bar button from the create tab function. So we're going to head over to the CPP file. We are going to revise the create tab button function, this guy right here. All right, so here's what we're going to do. We're going to create an extended tab bar button, then we are going to add a mouse listener to it, and then we are going to return that thing. Now, in the name of pointer and heap object safety, I am going to store this in a unique pointer before I return the pointer by releasing it from the unique pointer. This is because the unique pointer class has internal handlers that deal with correct memory releasing in the extremely rare off chance that the program throws an exception during the allocation stage. There is a note right here, or maybe here. Here's a link, you can go read about that. That explains deletion during an exception. So here's what this is going to look like. Auto ETBB equals std make unique. Oops, let me spell that right. Extended tab bar button, tab name, this. All right, we're getting rid of that, and we just need our closing angle bracket. Okay, now we can go ETBB, add mouse listener, and our extended tabbed button bar is going to listen. And we don't care about mouse events on any child components of the extended tabbed button bar right now. Finally, return etbb.release. Makes the unique pointer no longer own this. All right. For the mouse down function, we want to make sure that the mouse event that occurs is occurring on an extended tab bar button. If it is, we are going to start dragging that item by literally calling drag and drop container start dragging. That is the, let's see, drag and drop container start dragging. It's this thing here. Oh, not that one, this one. We're going to be calling this function. Let's put this below item dropped. That implementation is going to look like this. If the thing being dragged is an extended tabbed bar button, we check that using a dynamic cast. If it is, then we are going to start dragging it. Now that we can click on a tab and start responding to the drag events, let's implement the functions that won't do anything right now. Drag exit and item dropped. We already have item dropped implemented, but let's add item drag exit right above it. So we're not going to do anything in item drag exit. Let's see, what else does this say? Item drag exit is called whenever you drag the cursor outside of the drag and drop container. Extended tabbed button bar, item drag exit. All right, so we're not going to do anything in item drag exit, so just call the base class for right now. We can just add a message. I like to just sometimes do this to figure out when a function gets called in the scheme of things. And just call JUCE drag and drop target item drag exit. Okay. Now, for item dropped, we are going to find the item that was dropped and then lock the position of that item in. We're not going to do that in this chapter, so I'm just going to leave a comment for myself as a reminder of what to do next. So debug, item dropped, and then here's where we find the dropped item and lock the position in. Now we want, let's see, what order did we do these in? Enter, move, and exit. We're going to want these guys next. We'll go up here. For item drag enter, we're not going to do anything specific right now either, so let's just call the base class implementation. Duplicate this and just change it to item drag enter, and that is the exact same. So we're just calling the base class for right now. And before we tackle item drag move, let's update the is interested in drag source and return true if the thing that is being dragged is an extended tab bar button. And we do that by doing this cast again. Very similar cast. All right, let's get rid of this. All right, if the thing being dragged is that thing, and this is actually going to be drag source details or source component. Source component is something. Well, we just want the component. If it is this, then return true. That's all we're checking. We're seeing if the source component being dragged is an extended tab bar button. And if it is, then we are interested in the thing being dragged. All right. All right, let's break down the logic that should happen in item drag move. This is where all the magic is going to happen. So first, we need to get the item being dragged just like we did in is interested in drag source. Or actually, just like we did here. Oh, this is the wrong. That shouldn't be tab bar. That should be tab button. All right. So we're going to do the exact same thing we're doing here, except we're not going to start dragging. We're going to do something else. Okay. Now that we've got a tab button being dragged, we get to think about what is happening here. Oh, and this is not e.original component. It's this thing. Okay. Drag source details, source component, get. Okay. All right. Imagine this is the bar itself, and this is one of the tabs in the tab. Okay. When an item is being dragged, we want to find out if the X position of the tab being dragged has moved before or after another tab. If it has, then we want to switch the position of those tabs. As in, if we've got this one here, then it moves over here, we want to do that switch. I'll just kind of demo what that looks like with the app itself. All right, so we've got our order here. So the overdrive is to the left of the chorus, and we want to detect if it has moved to this side of it. Also notice that we've got this weird, like, we can drag up and down now, so we'll fix that later. But the point is, we want to know if overdrive has changed position with another one. In this case, it's changed position with chorus, and therefore we want the index of the chorus tab to switch places with the overdrive tab. Okay? That's the whole point of this. So if it has, we want to switch the positions of those tabs, and to do that, we need to find the tab being dragged in the tabs array. Now the tabs array is, if we go back to here, that's going to be in the tabbed button bar. I think there's a thing called tabs way at the bottom. Yep, here are the tabs. The problem is tabs is private, so we cannot access them directly. But we can use get tab button instead. Get tab button. This is how we can actually retrieve one of the tabs. Okay, so I found it simplest if we just create our own list of pointers to tabs first and then search for the tab that's being dragged within that list. And here's how to build that list. First, we need to get the number of tabs that we've got. Then we need to create our own array of tabs, resize it, and then the JUCE array class has a function called getReference. Since this is an array of pointers, we're getting a reference to one of those pointers, and then we are assigning to it the tab that is at that particular index within the tabbed button bar. Okay. Now we can search that list for the tab that is being dragged. Auto IDX equals tabs.index of our tab button being dragged. If index does not equals -1, then we got a problem. So let's tell ourselves that. Failed to find tab being dragged in list of tabs. JAssert false and return bailout. Okay. Now that we know that our tab is cool, let's find the tab that the tab button being dragged is colliding with. And it might be on the right side, it might be on the left side. If it's on the right side, we're going to do one thing. If it's on the left side, we're going to do something else. Also, we need to determine if the tab that's on the right even exists, because we may be at the end of the list and this could have been the last, this could have been like the rightmost tab. Or this could have been the leftmost tab and we're butting up against the left edge of the GUI. This is going to tell us whether or not we are the leftmost tab or rightmost tab. Here's how we do that using get tab button. All right, so here's the snippet for this. Let's take a minute and just look at this and read it. All right, previous tab index equals our current index -1. So we're going this way. And then the next tab index is IDX +1. And then we just look up those indexes that way. And then here's the base, here's an idea of the base logic we are gonna implement here. That should be tab button being dragged. All right, if the tab button being dragged, if its X position is greater than the next tab's X position plus half of its width, then they should switch positions. Okay, now we know enough information to make a decision about which tabs to swap positions. The logic that I want to implement is that whenever the tab crosses the middle of the adjacent tab, then their positions should switch. So here are the 3 rules that we will implement using if statements. Number 1, if there is no previous tab, you are in the leftmost position. Else, if there is no next tab, you are in the rightmost position. Otherwise, you are in the middle of all the tabs. If you are in the middle, you might be switching with the tab on your left or the tab on your right. So here's what that logic looks like expressed as code. Let me write that logic down here, just so we have it. Clean that up. Position. If you are in the middle, you might be switching with the tab on your left or the tab on your right. Okay. So remember, the X position of a tab is the left edge of that tab, and the middle position is that X position plus half of the tab's width. There's a couple more details. We only want to swap the leftmost tab with the one on the right if the dragged tab is to the right of the middle of the tab on the right. And we only want to swap the rightmost tab with the one on the left if the dragged tab is to the left of the middle of the tab on the left. All right, so let's punch this logic in. If previous tab equals null pointer, oops, let's fix that. And next tab does not equal null pointer, you're in the 0th position. Else, if previous tab does not equal null pointer and next tab, whoops, geez Louise, does equal null pointer, you're in the last position. 0th, far left. Far, else, you're in the middle. Okay, so we need to do that comparison to see which side of the middle of the tab we're switching it with we are on. If tab button being dragged get X is greater than the next tab's center, the center of the next tab. What's an easier way to do that? Next tab dot get bounds dot get center X. We can do it that way. If we do it that way. Well, I had it one way in the written tutorial. I'm tempted to try this. I'm tempted to not try it. Let's try it out. Maybe I'll update the tutorial. We go move tab. Current index is IDX, and our new index is going to be next tab index. Right. Otherwise, let's do the other direction. If tab button being dragged at X is less than previous tab get bounds get center X, we're going to move tab IDX with the previous tab index. Otherwise, we're in the middle somewhere. So we do the very similar check. It's actually the same one. If we are to the right of the next tab's middle, then we're going to move in that direction. Else, over here, we're going to move tab with the previous one. All right. It's fairly complex, but it's also not that complex. It's kind of simple. We're basically just checking if the left edge of our tab being dragged is to the left or the right of the middle of the tab that's on either side of it. Let's run and test that. We may have some issues, but let's see what happens. This was the first draft of how to get this moving. Let's see what happens. Oh, where did you go? There you are. All right, DSP Order. Let's put this here. Let's try dragging our overdrive past the chorus. Oh, there it goes. Okay. All right, so we have some issues if I let go of this. Okay, we need to snap the positions. Then we also need to hide this dragged image or stop dragging the tab and constrain the image being dragged to the horizontal axis. And we should also be swapping the tab order when the middle of the tabs cross, not the left edge. Because right now they swap when the left edge and the left edge of the overdrive passes over the middle. And we want to actually do it when the middle of the overdrive passes over the chorus. But it's working preliminarily. It's a preliminary draft that is kind of demonstrating the functionality. Okay, so we'll need to do a little bit of digging to figure out how to constrain this dragged image, because that needs to not be doing what it's doing. Let's add some to-dos in a process block. This is a good first step towards implementing Drag-To-Reorder. Let's go here. Let's go to our to-do list in Plugin Processor. Drag-To-Reorder GUI. Let's do this here. To-do, snap dropped tabs to the correct position. And then to-do, hide dragged tab image, or stop dragging the tab and constrain the dragged image to x-axis only. That is a long to-do message. All right, let's make a commit though. We've got some basic functionality going on. All right, first steps towards drag to reorder. See comments and to-dos. Excellent. All right, in the next chapter, we will implement snapping to the position after dragging and dropping.
Hey, if you like this tutorial that you've been following along with and have been wishing for a written version, check out the link below. You'll find this course as well as my other courses, all available in written format. They're full of detailed explanations, code snippets, and more. Each chapter is crafted to be easy to read and easy to follow. Complex features and ideas are turned into simple concepts with clear code snippets. You'll progress quickly as you elevate your app and plugin making skills by working through these projects. Programming isn't hard, it's just taught wrong. All right, let's get back to making this plugin. Okay, in the previous chapter, we built the functionality to allow us to drag the tabs, but not lock in their position after letting the mouse go. In this chapter, we're going to implement snapping the tab to its correct position after we release the mouse. After doing a bit of sleuthing inside of the tabbed button bar class, the solution is to literally just call the resized function. This, doing so, will cause all child components of the tabbed button bar, which is literally all of the tabs, to be repositioned. Let's go look at that. Here we go in the resized function. You can see that all it does is call update tab positions. All right, let's go to our plugin editor.cpp. Let's go to our item dropped function and just call resized. Let's run and test. All right, so let's move this phase right there after gen filter and drop it. And it snaps into place. Put gen filter right there and drop it. They snap into place. All right, you should see the order change, and then they should snap into positions when they are dropped, just like I showed here. Awesome. Okay, that's not enough code change to warrant committing, so let's do some more stuff. Let's do some refactoring now. Now this item, this function right here is pretty long. The item drag move function is quite long. Let's split it up into relevant parts. Number one, getting the tab list, and then number two, finding the tab index in the tab list. And then for completeness, let's just add a function that gets the tab that's being dragged. So in the header file, we'll go over here. We're gonna add 3 private functions to our extended tabbed button bar class.
First one is going to be called get tabs, and this will return the list. The second one is called find dragged item index, and this will return the index in the list. And then the third one is called find dragged item. This will return the tab button itself. Now, since all of the drag and drop container functions are passed a source details object, we'll make find dragged item and find dragged item index also take a source details object as the argument. It'll make it just really convenient for us. Okay, so we'll put those guys there. Here's my get tabs, which returns that array. Here's the find dragged item index, which returns an integer. And then here's the find dragged item, which actually returns a pointer to one of the tab buttons. All right, let's implement. Move to plugineditor.cpp. Now move the code from item drag move that created the tabs array into its own function. Here's an easy way to do that. Curly braces, cut, paste, return tabs. Now we just need to add this. Let's copy that, paste that here, and add the class prefix, colon, colon, get rid of the semicolon. All right, that takes care of that. Now, let's replace the line that sets the IDX, this index right here, with a call to find dragged item index. Find dragged item index with our drag source details. And we'll implement that next. I'm gonna put that down here. Let's see, int extended tabbed button bar, find dragged item index. All right, so here's where we need to do our cast. So this implementation is going to do the cast, and then it's going to do the search, and then it's going to return the found index or return -1. So auto tabs equals get tabs, then auto IDX equals tabs.index of, and the element to look for is our tab button being dragged. And if we find something, well, of course we're going to find something. It could just be a -1. We're going to return that. And as a default, return -1, meaning we didn't find anything because the cast failed. All right. Next, for the find dragged item function, we're just going to call find dragged item index and pass the results to get tab button and return whatever that call returns. So JUCE tab bar button pointer extended tabbed button bar find dragged item, drag source details. Now we just go return get tab button, and the index is find dragged item index with our drag source details. All right, let's test that out, and everything should perform the exact same as before. Let's make an order. All right, overdrive. Let's move the middle overdrive past the ladder filter and let it go. Snaps in place. Awesome. What about phase? Awesome. Okay. What if we make a new order? That's a lot of overdrives. All right, here we go. So let's do gen filter, 2 general filters in a row. All right, awesome. Okay, that works as expected. Let's go clear the to-do and then make a commit. We are clearing the snap dropped tabs to the correct position. Done. All right, let's get these changes. All right, our commit message implemented snapping after snapping to position after dragging and dropping. Commit 3 files. All right, in the next chapter, we will implement pushing the new DSP order from the dragged tabs over to the audio thread. In the 2 previous chapters, we got drag to reorder functionality of the tabs functional at a rudimentary level. The next step is to determine the new DSP processing order from those tabs and then push that into the audio thread. The most effective approach that I found is by using a listener model. What this means is that anytime a drop event occurs, we notify any listeners that are interested in that event about that event. During the notification process, we will pass any relevant information to those listeners. So in this chapter, we will implement that listener approach. Our first job is to create a listener class inside of our extended tabbed button bar, tab right here. We're going to create a listener class in here, And after that, we will make the editor be a listener to the tabbed bar. The listener class will have one callback function. The extended tabbed button bar class needs to store a list of listeners, and it needs a way to add and remove listeners. So let's add the following snippet above the private section that's going to do all of that for us. Here's our listener design, and then ways to add and remove. It's this stuff right here. And then in the private section, we need to add a listener list. So JUCE listener list of listeners called listeners. All right. Next, go to the editor and make it a listener. Extended tabbed button bar listener. And it needs to implement that one virtual function. So copy that, put that down here below resized, override. Okay. All right. So this function gets called whenever we are going to drop the tabs. In order to build the DSP order list, this thing right here, we need to get the DSP option from each tab. This means that each tab needs to store the option that is displayed on the tab. So in the extended tab bar button class, we need to add a private member variable storing the DSP option and a getter function to retrieve it. And then finally update the constructor to allow us to set the DSP option in each tab when it is constructed. So let's revise this constructor. We'll stick that DSP option here at the end. Let's just find a place that has that. Let's see, we'll just go project 13 audio processor, DSP option. Here's our DSP option. And then we need a get function to get that thing. So here's our getter function, get option. It's const because it doesn't change anything, return option. Now let's add our private member option. Okay, super simple. Our next job is to implement all of these declared functions and then wire them all up. Let's tackle the easy ones first. Let's go to the editor. It needs to add itself as a listener to the tabbed component, and it needs to remove itself as a listener when it is being destroyed. So let's go way down to the editor constructor and add ourselves as a listener here. Tabbed component dot add listener this, and then in the destructor, tabbed component dot remove listener. Okay, that's where we start listening for we start listening for changes to the DSP order in the constructor of the editor, and then we stop listening in the destructor. All right, next we need to implement the add remove listener functions in the extended tabbed bar component. This is super simple. Let's just go up to extended tabbed button bar. So the last one, tabbed button bar, create tab button. We'll just put them down here. Void extended tab button bar, add listener, and then we go listeners.add L, and then void extended tabbed button bar, remove listener, listeners.remove L. Super simple. Okay. Next, we need to update the constructor for the extended tab bar button to initialize the option. This is back where we're dealing with the constrainer. Let's see, where did that go? Right here. Okay, this is where we need to add this. Okay, so project 13 audio processor, DSP option. We'll call that DSP option. And then here we're gonna go option. Okay, and let's make this look nice by putting this stuff all in there online. The base class and member initialization. Next, we need to correctly construct the extended tab bar button instance in create tab button. Let's go down to that. Where is that function? Create tab button right here. We need to pass in the option right here. The only way we have of knowing which DSP option is being used is via the tab name function argument. So we need to write a function that gets the DSP option from the tab name. Let's write a reciprocal of this thing right here. It's going to be called get DSP option from name. This can also be static again. Static 13. It's going to make a DSP option, and it's going to be called get DSP option from name. It takes the JUCE string. All right. So now we need to do if phase equal, if the name equals phase, then return this thing. So we're basically just kind of flipping this around. So let's do that quickly. All right, and there's my list. If the name equals phase, then return the phase option. If it's chorus, chorus option, etc., etc. And then finally, if the name doesn't match any of these, then just return end of list. Now let's update the create tab function, create tab button function, to give us that. We can go auto DSP option equals get DSP option from name and pass it our tab name. And then now we've got our DSP option. Now, before we implement how to call the callback, let's implement the callback in the editor. So this is super easy. Let's just go down to the editor after resized, void project 13 audio processor editor, and this was tab order changed. This is super simple. All we are doing is passing in the new order as the function argument. So all we have to do is push that to the DSP order FIFO. So audio processor dot DSP order FIFO dot push our new order. That's it. Super, super simple. That takes care of all the moving parts that are easy to implement. Let's tackle the hard one, getting the tab order from the tabs and converting them into a DSP order instance, and then calling the callback on every listener. The logic itself is pretty simple. We need to get all of the tabs. We need to create a DSP order instance. We then need to populate that instance with the correct option for each index. And then we need to pass that instance to all of the listeners. And let's go make that function. This is going to happen in the resized because that's where dropping happens. Let's see, where is resized? Oh, I'm sorry, place this after the call to resized in item dropped, because that's where we want to update all that stuff. So first thing we got to do is get all of the tabs. All right, after we get our tabs, now we need to notify of the new tab order. So let's make our new order. Project 13 audio processor DSP order, new order. Let's make sure our tab count matches our new order size. It's always important. All right, now we just need to loop over the tabs for size ti equals 0, I is less than tabs, dots plus I. Auto tab, let's get a tab. And this is going to give us a warning because the tabs array, it's a JUCE array and they use integers, not size t, so we need to cast this. Static cast. All right. Now let's see if we can cast it to the extended tab bar button. If you remember, get tabs returns an array of the JUCE. It returns an array of the base class, pointers to the base class, not to the actual type. So let's do that first. If auto etbb equals dynamic cast, spelled dynamic correctly, extended tab bar button pointer tab, then we can do new order I equals etbb get option. All right. Now that we have populated our new order, we can use the listener list call function to pass this new order to each listener. We go listeners.call, and then we provide our callback. And our callback syntax needs to match, where did that go? Needs to match this thing. So we need to pass it in this. Looks like this. Here's our lambda that we're going to capture new order. Then the callback uses listener references. All right, now in here, this is where we go listener.tab order changed, and this is where we pass in the new order. Okay, so for the call function, just take a look at this. It's going to call check excluding, checked excluding. Where's that? Call checked excluding, and what it's looking for is the ability to call the callback with a dereferenced listener. And the listener comes from the local listeners list. This is a pointer, so dereferencing it gives us a reference. This is why the syntax over here is used where it's passed a reference to the listener. If you've ever done any coding with JUCE before using the listener model, you'll know that this looks really familiar. You can do listeners.call, whatever you're capturing, and then a reference to the individual listener. Okay, so before running and testing, let's add a breakpoint in this callback lambda so you can inspect new order and make sure it matches the tab order after dragging and dropping. Let's check that out. All right, let's hit that there. I'm gonna move this over here. And we're gonna move this, let's do another one. I'm gonna move this phase before the ladder filter. Drag and drop right there. So we wanna take a look at this. We wanna take a look at our new order. And we should see phase before ladder filter, and we do. So this is working as expected. When you do this test, if your tab order in the debugger matches the tab order after dragging and dropping, it works as expected, which means you can make a commit. Go ahead and press continue, remove that breakpoint. We can go ahead and close this. All right. Our message is implemented, pushing new DSP order to audio thread. Commit. In the next chapter, we'll fix the issue of the dragged tab showing a duplicate tab image. Awesome. We are slowly improving the drag to reorder functionality of our plugin. In this chapter, we're going to correct the issue of the two images being shown whenever you drag a tab around. We're going to fix this thing right here. Now, this particular issue took me a few hours to solve when I was working on it. My first attempts were to figure out where the dragged image was coming from, and is there a way I can constrain it? Is there a way I can hide it altogether, etc., etc.? And after digging into the implementation of the classes that manage dragging a component, the answer was no, you cannot constrain it. No, you cannot hide the image. So we are going to do a hack and do some graphical trickery to make it seem like there is no image. There is an optional argument to the start dragging function. Got over here. Where is this start dragging? Where did that go? This right here. Start dragging function. There's an optional argument we can pass, this one right here. You can pass it a scaled image instance, and that will be used instead of whatever it will generate for you if you use the default parameter when you drag a component. So here is the solution we will be implementing in plain English. Solving the issue of duplicated images is accomplished by using a 1x1 pixel image as a scaled image that the drag and drop container uses when displaying the item being dragged. By using a transparent color, we don't see the 1x1 image on screen either. The tabs are already being displayed as dragged because of their internal component dragger instance taking care of the dragging. This is a bit of a hack, but it is simpler than to implement than any other solution and gets the job done. So the first thing we need to do is declare an instance of the scaled image class right above our listener list. Let's go for that. Let's close this down. Let's shut down our audio plugin host as well. All right, where is our listener list? Right there. Okay, let's put that right here. JUCE scaled image, drag image. All right. We are going to use it in every single mouse down call. It needs to be a member variable because we don't want to create this scaled image every time the mouse down event occurs. We only want to create it once. All right, so we've got this in our extended tabbed button bar class. Let's add the following snippet to the constructor to initialize the image. Extended tabbed button bar constructor. All right. Auto image equals JUCE image. And we want our JUCE image pixel format, single channel. Image width will be 1 pixel, or point, I guess if they use points in this thing. Image height will be 1 point, and the clear image will be true. Let's make a graphics context. Auto GFX equals JUCE graphics. We're going to write into our image. Let's fill it, gfx.fill all. And the color is going to be transparent black. JUCE colors transparent black. All right, now we can do drag image equals JUCE scaled image. I missed the one, scaled image. And we want our double scale in. So our image in is going to be IMG, and our double scale in is going to be 1.0. So we're not doing any scaling. Now what this code does is create a 1x1 JUCE image instance. The image is filled with the transparent black color, and then a scaled image is created from this JUCE image instance. Now, in our mouse drag function, where did that go? In our mouse down function, pass the drag image to start dragging in the mouse down. Drag image right there. Now let's run and test. You should only see the tab being dragged now and no ghost image being dragged along with it. Get some tabs. All right, clicking and dragging. No more image. Awesome. Oh, that was weird. That goes behind there. That's very strange. All right, either way, we'll figure that out later. That worked as expected. Let's save this and quit. All right. If that is what you see, let's mark the to-do as done. This would be the hide dragged tab image to-do. Let's mark that as done, and let's make a commit. Commit message, fixed issue with tab dragging showing a duplicate tab image attached to cursor. All right, let's make this code a little bit more readable. Let's rename the DSP option name. Let's rename that function. Get DSP option name to get name from DSP option from DSP option. All right, let's make sure that compiles. All right, build succeeded. Let's commit that name change. Improved a function name. And then the last thing we will do is make the tabs occupy the entire width of the editor. The tab bar button class, let's go to that. Tab bar button class. JUCE tab bar button. Jump to definition. Oh, come on, don't do that now. Oh, Xcode. Okay. The tab bar button class has a member function called getBestTabLength. Let's go find that. Right here. If the tab is horizontal, this should return its width, and the depth specifies its height. If it's vertical, it should return the height, and the depth is actually its width. Chooses the best length for the tab given the specified depth. Okay, we're going to override this and use this to compute the ideal width for each tab. Let's copy this, and let's go put it in our extended tab bar button class. Let's put this below our get option function. And then while you're here, if you have any warnings about missing overrides, be sure to add those. They were there earlier and I added them. I don't remember if I mentioned it in the video. Okay. Oh, here we go. No, I'm not overriding this one and I need to override. Okay, cool. All right, in order to figure out the best tab width, we can use either the look and feel get tab button best width function, or the owning tab bar's width divided by the number of tabs. Whichever value is bigger is the one that should be used as the best tab length. So in the plugin editor.cpp, let's implement get best tab length after the constructor. Extended tab bar button, extended tab bar button, get best tab length. All right, so let's get our look and feel and then get the best width from that. Auto best width equals get look and feel and get tab button best width, and we want to check, and then the tab button is ourself as a reference, and then let's get our bar, get tabbed button bar, and now we want these tabs to occupy the entire tab bar width. We want the tabs to occupy the entire tab bar width. So after computing the best width for the button and the depth, we choose whichever value is bigger, the best width, this thing right here, or an equal division of the bar's width based on the number of tabs in the bar. We go return JUCE JMax, and it's either going to be best width or bar.getWidth divided by bar.getNumTabs. All right. Super simple. I'm going to put this comment in here to explain that. All All right, let's run it and test. And hopefully the tabs should extend across the entire tabbed button bar. And there they do. Let's make a few more. All right, so all of our, we can see them like shifting and whatnot. So this would probably be a lot closer together. That's looking good to me. It's extending all the way to the right, almost. It's like, that's probably some integer division issue that's happening there. So probably got to make this float and then cast it to int or something like that. All right, let's make the editor a little bit wider. Okay, go down to your constructor for the editor. And right now it's 400 by 300. Let's make it 600 by 400. And then let's run and test it. Wait for that to pop up. All right. This looks much better. And we can see it's extending almost all the way across. And I'm not seeing that right edge anymore that was appearing sometimes. So this looks good to me. If you experienced the same result when you launched the plugin, go ahead and make a commit. This and quit. Let's make that commit. All right, increased editor size. Fixed issue with tabs not occupying entire width after increasing editor. All right, in the next chapter, we will tackle restoring the DSP order to the GUI so the tab order is remembered whenever we close and open the GUI. That's going to be a cool project part to build. All right, our tabs are draggable and the tab order is pushed to the audio thread. In this chapter, we will add the ability for the DSP order to be restored from the settings file whenever the app is launched. The easiest way to let the GUI know when it loads what DSP order to use is with a FIFO. Let's add another FIFO to the plugin processor and push the DSP order that is loaded in set state information. Go back over here, state information. Talking about this guy right here. The easiest way to let the GUI know when it loads what DSP order to use is with a FIFO. So let's add another FIFO to the plugin processor and push the DSP order that is pushed right here into that new FIFO, and we will set up a timer on the GUI that will check that FIFO regularly. In plugin processor.h, let's go to that FIFO right here. Declare another instance after the DSP order FIFO and call it restore DSP order FIFO. All right, now in plugin processor.cpp, add a push to this new FIFO in the set state information function after the DSP order FIFO push. So restore DSP order FIFO.push order. All right. As stated earlier, let's make the editor inherit from JUCE timer. Let's go here, JUCE timer. Let's put this on its own line as well. And let's add the timer callback over here, void timer callback, override. All right, first let's start our timer in the constructor by calling start timer hertz. Let's do this after we add our listener, but before we set the size. Start timer hertz, and we're gonna do it at 30 frames per second, or 30 times a second. Okay, now for timer callback, we will pull from the restored DSP order FIFO until it is empty. The most recent object that gets retrieved from the FIFO will then be converted into tabs. So in timer callback, we're going to do the following. We're going to check if the FIFO has stuff to pull, and if it doesn't, we're going to exit the function. If it does, we're going to pull all of it, and then we're going to create new tabs from the last thing that was pulled. We'll add some safety as well to make sure something was actually pulled, and here's what checking if the FIFO has stuff looks like and exiting if it doesn't. Let's get this going. Let's do this way at the bottom. Void project 13 audio processor editor timer callback. We go if audio processor dot restore FIFO.get num available for reading equals 0. Get out of there. All right, here's what we do if it does have stuff to pull. I'm adding a bit of safety as well by making a copy of the blank DSP order instance that we can compare with after performing the pull. After performing the pull, this is very similar to what we did in the plugin processor loop. Let's just go take a look at that real quick. We're doing something very similar to that. Yep, before process. Right here. We're doing something very similar to this. We're doing something similar to that in timer callback. Okay, so this goes using T equals project. Why do I spell that wrong? Audio processor DSP order. Let's make a new order. Then let's fill it. We're going to fill it with project 13 audio processor DSP option. End of list. And then we're going to do auto empty equals new order. This is the one we're going to compare with. While audio processor dot restore dot pull new order. We're not going to do anything. Literally do nothing. You'll do something with the most recently pulled order next. Okay, here's the check. If new order does not equal empty, as in if you pulled nothing, new order will be filled with end of list. You got problems if that's what you end up with. Okay, so don't create tabs if new order is filled with end of list. All right, let's declare a function called add tabs from DSP order and call it inside of this if block. Okay, let's go back to our tabbed component declaration. We're going to put it underneath that. Void add tabs from DSP, oops, caps that guy, DSP order. And this is where we want our DSP order. Project 13 audio processor DSP order. Okay, we'll give it a name on the actual implementation side. All right, we will do what is being done in the DSP order button on click Lambda. Let's go take a look at that real quick. So we're going to do all of this stuff minus the random and the range. We're going to clear our tabs. We're going to add new tabs based on the DSP order, and we're going to push that DSP order to the audio processor. All right, here is what that is going to look like. Let's put that down here. Project 13 editor. This thing needs a name. It's going to be called new order. All right, so tabbed component, clear the tabs for auto v new order. We're going to do something. In this case, it's going to be tabbed component dot add tab. Our tab name is going to be get name from DSP option. Our option is B for value. Our background is going to be white, and our insert index is -1. And then finally, we're going to push it to our DSP order FIFO, audio processor dot DSP order FIFO dot push new order. Now here's the gotcha with this one. If the order is identical to the current order used by the audio side, this push will do nothing. And we ensured that way over here when we did our pull, and we checked if where do we do that check? We did that. No. The change will result in doing nothing because the order of DSP pointers here will not change. That's why. Which means that the order that this gets processed in will be the exact same. Okay, that's why it will do nothing if the order has not changed. Let's call this function in the if block at the end of timer callback. Add tabs from DSP order. Here's our new order. All right. Let's run and test by clicking the DSP order button, saving and quitting and then relaunching. All right, let's click this button here. So ladder, chorus, gen overdrive, save and quit. I remember the first two were ladder. Okay. Now I don't know about you, but I have difficulty remembering what the tab order was between launches. So let's add some debug output that prints out the tab order whenever we click the DSP order button. You can also take a screenshot, but I found it's just easier to look at text versus an image. So let's go up to our Lambda and let's change this loop right here after we do our cast. Let's do auto name equals get name from the option. And then we can do debug, creating tab name. And then right here, do name. And let's print this stuff out. See what we get. All right, I'm going to show a trick for what to do here. Okay, so we're going to push this button. Now we can see this. All right, oh, let's get rid of that too. We don't need that. Let's rerun this. Do this one more time. All right, let's push this again. Now let's quit. Oops, I forgot to save it. Last time, promise. Push that button, save, quit. All right, we've got this output here. Let's open a panel on the side. This is going to go over here. We're going to look at our previous launch right here. This is where we've got this output right here. We're going to rerun this, but before we do that, let's add a breakpoint in plugin processor, set state information right before we do this push. And we're going to make sure that what we see down here matches what we see there once it hits that breakpoint. Here's our order. And we can see we've got overdrive, chorus, ladder filter, chorus, chorus. We've got overdrive, chorus, ladder filter, chorus, chorus. Awesome. So let's press continue. And we can see here we've got overdrive, chorus, ladder filter, chorus, chorus. That's awesome. That means that it all works. So we can clear the to-do and make a commit to this tab as well. Let's go up to our to-do, which is going to be restore tabs in GUI when loading settings. This one is done. Awesome. Let's go ahead and make that commit. Implemented restoring DSP order to GUI. I wonder what the diff is here. Well, it doesn't matter. All right, commit 5 files. All right. Before we can close this chapter, let's make sure that the default tab order when the plugin is first loaded is reflected in the GUI. Now remember, when the plugin is first loaded, there is no settings file. This means set state information is not being called. So in the audio processor constructor, let's push the DSP order into the restore DSP order FIFO after it has been filled with the enumeration values. Go way up here. So after we do this, let's put this DSP order in the restore DSP order FIFO. All right, first of all, let's run and test this by deleting the instance of the plugin from audio plugin host and then creating a new instance. All right, let's get rid of this breakpoint. Show all of audio plugin host. We're going to delete project 13. Okay, let's pull up our enumeration. Okay, this guy right here. We're going to instantiate a new instance, and the tabs should be in the same order as this. Open this GUI up. All right, let's see what we got. Phase, chorus, overdrive, ladder filter, general filter. Awesome. If the tabs are in the same order as the enumeration on your side, then it works as expected. Make a commit after we wire this back. The guy right there. Save and quit. And let's make our commit. Hard-coded initial DSP order. And we'll put our method for testing. Delete, then load plugin from APH. That's a reminder to ourselves of how to get this to work. All right, commit, awesome. All right, in the next chapter, we will fix some issues related to the tab dragging experience. In this chapter, we are going to fix a tab dragging issue. Currently, dragged tabs in the current implementation swap positions when the left edge of the dragged tab crosses over the middle of the adjacent tab. Check it out. So the left edge of this overdrive tab is not going to switch places with the ladder filter tab until it passes the middle of the ladder filter tab. We don't want that. So we're going to change this so that the swap happens when the center of the dragged tab crosses over the center of the adjacent tab. Now all of the code edits will occur in the item drag move function. Let's go look at that. Item drag move. Tab down here. All right, so the first thing we need to do is get the center X of the tab being dragged. And let's add this before all of the if statements down here. All right. Auto center X equals tab button being dragged, get bounds, get center X. Okay, now we need to revise each of these if statements that check if the center of the tabs have been crossed over. Change the check for the 0th position from this thing to if center X is greater than just the left edge. And let's change the position from the last tab from center X is less than the left edge as well. And finally, change the first chunk of code that handles the middle position swap from this right here to center X, next tab, get X. And then for this one, it's going to be the same thing. Center X, oops. Oh, I'm sorry, this should be get right. This is the left and this is the right edge. Lastly, add this line at the end of the function, but inside the outermost if block to bring the tab being dragged to the front of the GUI. Let's see. The second curly brace is the one we want. So that's going to go right here. Tab being dragged to front. Okay, if you test it now, you'll see that the tab swap behavior is much more intuitive. So when the middle goes over the left edge, they swap, and it's always on top, which is good. Same for that. All right, let's go all the way to the front. Much better. All right, good times. All right, now while I was developing this, I had the following debugging snippet inside of the item drag move function. Let's put this up here at the top. This comes after we get our tabs. I'll put this right here. Feel free to add this to your code to see the names of the tabs that are that might end up being swapped. This part right here. It's pretty simple. All it does is it gets the name of the previous tab by reading the button's text, and then it just prints it out. Let's check out what that looks like, and then we'll turn it off. So you can see it says on the screen, Chorus is the previous one, LadderFilter is the next one. Switch to here. Now it says LadderFilter is the previous one and GenFilter is next. If I go past GenFilter, it'll say none is next and GenFilter is previous. This was really helpful to me to figure out how are these guys moving? How do I want the behavior when I'm dragging it around? So go ahead and you can put that in your code if you want. No reason to have it though. And for right now, let's just turn that off, false. All right. So tab dragging and swapping is much more intuitive, and now we can finally clear this to-do, which was drag to reorder GUI. That is now done. Let's make a commit of that. All right, fixed drag issues. Tabs swap positions when dragged. Center X crosses adjacent tabs edge. All right. What's this spelling error? All right, good times. Commit. All right. Our plugin has SaveLoad of the tab order. It also has a default tab order that shows all of the available DSP options when the plugin is first launched. That means we no longer need the DSP order button. Let's remove it from plugin editor. See you later. And now we can delete our lambda from the plugin editor constructor. Where are you? That's right here. Let's get rid of this on click. Goodbye. And let's get rid of where we're adding it. And then finally, we can get rid of it from there, which also means we can get rid of it from the resized function as well. We can leave our little gap of 10. That's fine. Let's run it just to make sure that that does what we need it to do. All right, we've just got our tabs. Perfect. Save and quit. All right, let's make a commit of that. Removed DSP order button. Wonder what's going on with that. Oh, it's changing the state. And if you're curious about why this is doing that, it's because every time I change the plugins, I drag the tabs around, it's changing this little bit of text within the state representation, and Git thinks the entire string has changed. This is one single line, so that's why it's saying it's like a massive commit change. Okay, let's commit that. Awesome. All right, in the next chapter, we will stub out the GUI that will be shown for each DSP effect. This will finally allow us to control the effect's parameters again. All right, in this chapter, we are going to start developing the GUI that shows the controls for each DSP effect. This GUI will dynamically change whenever you change the selected tab. This means we need a way to tell it what components are needed. All audio parameters inherit from JUCE ranged audio parameter. And since each, let's see, where did this go? Where are those guys? They're there. Since each DSP effect has a unique set of audio parameters, we can pass a list of JUCE ranged audio parameter pointers to this function and use that list to tell us which type of components to dynamically create. On/off parameters should spawn buttons, float parameters should spawn sliders, and choice parameters should spawn combo boxes. Our GUI will be a JUCE component, and since it will own child components such as sliders and buttons and etc., it will need a resized function and also some containers to own those child components. It will also need a container to own all of the parameter attachments that connect those child components to their associated audio parameters. So we've got our basic parameter requirements now. DSP GUI that inherits from JUCE component. It has a resized function. It has a function that takes a list of ranged audio parameter pointers to dynamically change its child components. It has a container to hold the child components and a container to hold the parameter attachments. So the requirements of dynamically changing the child components and attachments at runtime means we need to use heap memory to store the components and not stack memory. Unique pointer is the preferred tool for this to store any objects on the heap. If you need to store multiple objects of the same type on the heap, then std vector, std unique pointer is the preferred tool. We have our container type. Now we just need a function to change the child components dynamically. We can use std vector of JUCE ranged audio parameter pointers as the function argument to pass the parameter list into this function. And this function's job is to rebuild the interface, which is an appropriate name for this function. You got to name things according to what they are and name functions according to what they do. So since we don't have any child components yet, filling the DSP GUI class with a solid color will make it easy to use. We can do this in a paint function. So we've got a paint function, a resized function, a rebuild interface function, and a vector of unique pointers holding our components, and then a vector of attachments also held under unique pointers. Okay, we have all the pieces needed to put this class together. Let's go to our plugin editor.h and let's do that right above our plugin process editor. Struct DSP GUI JUCE component. All right, we need our constructor. Let's close this off first of all. Constructor. We need our resized function. It's got nothing in it. We need our paint function. We're just going to fill it with red. Void paint JUCE graphics G override G.fill all JUCE colors red semicolon. All right. Then we need our rebuild interface. Void rebuild interface. And this is going to take that std vector of JUCE ranged audio parameter pointer instances called params. Then we need our vector of, we'll just do sliders for right now. std vector sliders. And inside of this will be std unique pointer. This will be JUCE slider. And then we also need our attachments. Same thing, a vector of unique pointers, except we're going to be holding attachments. So std vector, this thing, attachments. And this is where we go std unique pointer. And this will be JUCE audio processor value tree state slider attachment. All right, let's declare an instance of this class in our editor. Put this below our audio processor, DSP GUI. All right, let's add it as a child component in our editor's constructor. Where are you? Paint function right there. Okay, add and make visible DSP GUI. And then let's position it in resized. So it's going to go, let's see, let's change this from bounds width height equals 30 to be bounds remove from top 30. And now, whatever is left in the bounding box, whatever size is left in bounds, we're going to use that for our DSP GUI. Set bounds. All right, let's run it. We should see a big red rectangle. All right, success. We have a starting point for the GUI. Let's make a commit of this. Very simple. Stubbed out the GUI. All right. Our next job is a way to retrieve the list of audio parameters from a particular DSP effect from the audio processor. As in, how do we get this list of stuff when we click on the Chorus tab? How do we get this list when we click on the Phaser tab? How do we get this? Overdrive, ladder filter, general filter, etc., etc. The DSP option value will be used to determine the set of audio parameter pointers to return from this function. So let's go to, this be public, so let's do this at the bottom right above private. Right there. Let's add the following public declaration. First of all, we're going to return a vector of JUCE ranged audio parameter pointer. And it's going to be called get params for option. And this is going to be DSP option. Okay. Now in plugin processor.cpp, let's go start the implementation. Let's just put this, we just put this anywhere. Put it right there. That's a good place for it. And let's add to this part. We have our fully qualified function name. Okay. We are going to use a switch to figure out which list of param pointers to return. Now, pointers are essentially the same as integers, which means they can be passed around by value. We can leverage this fact and use all of the cached params as the value source when creating the list of param pointers. For example, here's an example showing returning all of the Phaser Params as a vector. Okay, so we're going to do the same thing inside of a switch statement. All right, let me clear that out. All right, by using the DSP option function param, this thing right here, as the switch argument, we can produce each list of param pointers to return very easily. Switch option autocomplete will give us the list of options, the enumeration. Thank you for that. And let's fix this formatting. Let's hide this on the bottom. Now, for each of these, we just need to return the list of pointers. All right. So for Phaser, let's see. Let me open this over here. Let me get that list up. That's right here. All right. This stuff here. So we're going to change this to say curly brace, return, and then another set of curly braces. I'm actually just going to duplicate this for each of these cases because I'm just going to fill it in a moment. That'll make this easy to do. And if it's end of list, then we'll actually just say jassert false. And then over here is where we will just say return, and let's put that on its own, on one line like that. Okay. All right. Let's copy our Phaser guys in there. Paste it in here like this. Close this for a second. And now, because these are all the same, we can go like that and then get rid of the equals null pointer, add commas, and then format it. And there we go. Let's just do that for the rest of them. It'll be very easy, very quick. Do that same copy and paste. I'll check back in once I've done that. Okay, I've got my list right there. I'm actually going to move this jassert false down here, and we're just going to break from here instead. That way, if we actually hit the end of this function, we know there's a problem. Okay, so here's my list. I'm returning my vector and all that stuff. Let's try to compile it. And if your build succeeds, let's make a commit. And our commit message is added function to retrieve params for each DSP option. Okay. In the next chapter, we will implement the basic functionality to automatically add components based on the param pointer lists above when the list is passed into the DSP GUI rebuild interface function. Let's get on with that in just a moment. All right, welcome to chapter 28, implementing a rough GUI. By the end of this chapter, we will have implemented a GUI that lets us control the properties of each DSP effect. There will be a lot of sliders and buttons on this GUI. In order to create APVTS parameter attachments correctly, we need access to the APVTS. That is over here. It's a public member right there of our audio processor. Let's go to our DSP GUI. Okay. Now our DSP GUI will need to store a reference to the audio processor so it can access the APVTS every time we change tabs in the editor. Add a reference member to the DSP GUI and then update the constructor to initialize it. Put that above the sliders. All right, and let's make our constructor do that. Processor P. Okay. Then let's update this where the GUI is actually initialized, way down here. Just put curly braces in the new audio processor. All right, let's move the rest of the DSP GUI implementations to the CPP file since they will be fairly long implementations. Grab this stuff, copy it, move to the CPP file, and we'll just stick it above our audio processor constructor. We'll put it here. We'll put this above it. All right, go back here and grab the class name and remove these implementations, semicolon, semicolon. And over here, now we can just put our DSP GUI like that. No override keyword, and no override keyword here either. That goes there. All right, we got curly braces for this function as well. Okay, we've got our 3 stubs all set to go. Let's change this from red to black. We'll fill these in later. Okay. The sequence of events that rebuilds the interface is as follows. The user drops the tab, then the editor callback for tab drops is called. Here is where we add the functionality to rebuild the interface. Okay, first we need to get to the params that should be displayed on the tab. We wrote a function in the last chapter for that. Then we need to tell the DSP GUI to rebuild the interface using this parameter list. So let's go back to our editor header file, way down at the bottom. Let's add a declaration in the editor for a function that will rebuild the DSP interface, void rebuild interface. Okay, we will call this function after we have added the tabs and whenever the tab order changes in the editor. Let's go edit both the tab order changed and add tabs from DSP order functions and call this new function. Find those. All right, tab order changed. Here's the first one. So after the tab order changes, we want to rebuild the interface. We'll do that before we do our push. Then in timer callback, after timer callback, add tabs from DSP order. Let's do this before we do the push. Rebuild interface. Okay. Now the sequence of steps in the editor rebuild interface function is fairly simple. Figure out which tab is the current tab in the tabbed component. Try to get the DSP option from that tab. Get the param vector from the audio processor depending on the tabs option. Make sure the vector isn't empty, and then tell the DSP GUI to rebuild using that param vector. Now let's just stub this function out. Void project 13 audio processor editor, and this is rebuild interface. Move that up. Give ourselves a few lines to work with. Okay, getting the current tab is a 2-step process. You can only get the tab if you know the index of that tab, and thus calling get current tab index first gives us the index of the tab. Auto current tab index equals tabbed component get current tab index. From there, we can get the tab and try to cast the tab to our derived tab type, and then get the DSP option associated with the tab. That looks like this. Auto current tab equals tabbed component get tabbed button from our current tab index. All right, here's where we try to do the cast. If auto etbb equals dynamic cast extended tab bar button pointer current tab. If we get that cast, then we can do auto option equals etbb get option. Auto params equals audio processor dot get param get params for option. Let's make sure it's not empty. JAssert params dot empty equals false. And then finally we can do DSP GUI rebuild interface. All right. Okay, let's write the DSP GUI rebuild interface function next. Let's jump to that guy. All right, as stated in the previous chapter, on-off parameters will be represented by buttons, float parameters will be represented by sliders, and choice parameters will be represented by combo boxes. We need containers to store these different component types. We already have a vector for storing sliders, but we need another vector for storing buttons and combo boxes, and vectors for storing the attachments that go with each of those components. Let's go back to the declaration of this guy. Here's our dude for sliders. Let's add one for combo boxes and buttons. This will be combo boxes, buttons, and let's change these types. This is a combo box. This is a button. All right, now for our attachments, each of them has a different type. So we've got our slider attachment. So let's name this accordingly. This is going to be slider attachment. This is going to be combo box attachments. This is going to be button attachments. And let's change these to match. Combo box attachment. And this is button attachment. And combo box should have a B. Combo box. All right. There are our attachments. Did I spell that wrong? Why isn't that changing color? Oh, there it goes. Okay, cool. All right. Let's go back to the function rebuild interface and provide a high level overview of what this function will do. So first it's going to figure out the derived type of the parameter. Then it's going to create the appropriate component and attachment for that parameter. We can figure out the derived type of the parameter via dynamic cast. That looks like this. If it is able to be cast into a choice, make a combo box. If it's cast into a bool, make a toggle button. Otherwise, it's a float or an integer parameter, and you should make a. The other things that it needs to do is clear out the old child components and then add each new child component. Now remember, attachment containers must be cleared before component containers are cleared. This has to do with how the attachment destructor stops listening to the component for events when the attachment is destructed. If the component has already been destroyed, the remove listener call in the attachment destructor is going to trigger an exe bad access crash. Combo boxes need an item list. This list of choices can be pulled from the parameter directly. JUCE toggle buttons should be used for the buttons. Those are the ones that have a little check mark in them. Sliders should be linear vertical sliders, and then the resized function must be called after all child components have been added. Let's get started on that. This is going to be pretty complex. Let's start up here. Let's clear all of our attachments. Slider attachments.clear, combo attachments, and then button attachments.clear. All right, next let's clear our components themselves. Sliders.clear, combo boxes.clear, and then buttons. All right, now we just loop through our parameters. For size t equals 0, I is less than params dot size, semicolon, plus I. All right, now in this loop, this is where we go auto p equals params I. Now this is where we use this thing. Let's move all of this, put that inside the loop. Let's get rid of that. That needs to go back into the top. and get rid of the end if. Okay. All right. Here's all of this stuff that we're going to fill in. So if it's an audio parameter choice, we need to make a combo box. Let's do that first of all. Combo boxes dot pushback, and we're going to make a combo box. std make unique. So let's get that autocomplete to appear. JUCE combo box. It has no arguments, so this is empty. All right, let's get it. Auto cb equals combo boxes dot back. This is the last one, dereferencing it so we have an actual reference to the object and not the pointer itself. Let's get the item list, cb.add item list, and our list is going to be the choice parameter, the choices. Our index is always 1 for these guys because 0 indicates you cleared the menu or you didn't click anything. All right, let's make our attachment. Combo box attachments, that's pushback, std make unique, spell that correctly. And this is going to be a JUCE audio processor tree value state, audio processor value tree state combo box attachment. JUCE audio processor value tree state combo box attachment. That thing right there. Let's get rid of the args. We need to close off our angle bracket. Now we can fill this in. All right. The state to use is going to be the processor.apvts. Our parameter ID is going to be the name of our parameter. Get name. We want this. It wants a maximum string length, so let's just do 100 and whatnot. And then it wants a combo box, so we'll pass it our combo box. That's pretty verbose. All right, let's do the same thing for the toggle button. Buttons.pushback, std make u. This is going to be a JUCE toggle button. And the button text is going to be bypass. Close that off, semicolon. Let's get the button. All right, and then let's create the attachment. Button attachments.pushback, std make unique. This is going to be a JUCE audio processor value tree state button attachment. Same apvts, processor.apvts. Parameter ID is going to be p, get name, 100 characters of it. It's a shorter name than that. And then the button itself. All right, get rid of that, semicolon, and then closing angle bracket for the template parameter. Okay, last one is the sliders. For this one, we want to set the slider style to be linear vertical. Okay, sliders.pushback, std make unique, JUCE slider, doesn't need a name, doesn't need a type either. Okay, there's our slider. Let's get it. Don't forget to dereference, so you have the actual reference to the slider. Okay, let's set that style. Slider.set slider style. This is going to be JUCE slider style. And our choices are all these. We want linear vertical. Now we make the attachment. Slider attachments.pushback, std make unique, JUCE audio process. Oops, let me do that properly. Audio processor value tree state. Slider attachment. Same thing as here. Processor.apvts. Same way to get the parameter ID. And the slider itself. Rid of this stuff. Semicolon, close off the template parameter. All right. Now, let's add all of our sliders after we're done with our big loop. So for auto slider, sliders. No, we don't need this. We can just do add and make visible slider.get. Do that for the buttons and the combo boxes. For auto cb combo boxes, add and make visible cb.get. For auto btn for buttons, add and make visible btn.get. And then finally, resized. Okay, the resized functionality is going to be fairly straightforward considering the following requirements. We want to have the buttons along the top, combo boxes on the left, and then the sliders take up the rest. So it's pretty easy to dynamically size each component. Let's go to our resized function right here. Even though it's not going to look pretty, just divide the width by the number of components in a container being positioned. This result will tell you the width to use for each component in the container. For our resized function, some of our param lists might not contain a particular type of component, so we must always check that the container is not empty before trying to lay out whatever components might be in the container. Here's what that's going to look like for the buttons. We'll do those guys first. Auto bounds equals get local bounds. And then if buttons.empty equals false, now we can do stuff. Auto button area equals bounds.remove from top. We want to give them a nice row of 30. Okay, let's get our width. Auto w equals button area.get width divided by buttons.size. Then for every button, we just give it this much width. So button set bounds. Oops, I'm sorry. We need to go for auto button in the buttons. Button set bounds. And we want to do the button area. Remove from left W. But W is a size T because that's the size, that's the variable type returned from this, and we want to pass this an integer. So let's cast it. Okay, let's do the same thing for the combo boxes and the sliders. Just duplicate this code, paste it, and rename some stuff. All right, we'll do combo boxes and then sliders. All right, for the combo boxes, we want them on the left, so we should do combo box area dot remove from left. Let's change this to be combo box area. It's going to be combo boxes dot size. This is going to be sliders dot size over here. It's going to be sliders there. This is going to be combo boxes here. And that's not button, that's combo box. And then this is not button, this is slider. And this is not button area, this is slider area. Okay, for the combo boxes, bounds.remove from left will give the rectangle that spans from the top to the bottom with a width of whatever we provide to it. So our combo boxes go on the left. So we would use combo box area remove from top with the height per combo box instead of remove from left like we did with the buttons. And let's see, our GUI is 600 pixels wide. So let's make our combo boxes take up a quarter of that. Let's go back here to the resized function. And let's say our combo box area is going to be bounds.remove from left. We can do bounds.get width divided by, so 25%. Okay, that's our combo box area. And then this combo box area, we're trying to do it based off of the height, not of the width. So what we actually want to do here, first of all, I'll change that from W to H. We want to do combo box area.get height. And then we actually want to have a minimum size of 30 because we want the combo boxes to only be 30 units tall. And right now this is going to give us a huge chunk. So let's jmin this, jmin this thing, and then also 30. Now this is going to complain because it's like, oh, that should be JUCE jmin. It's going to complain because dividing by this right here changes this value from an integer to a size T, and then this is defaulting to an integer. So it's got to complain about that. So we have to cast this. Okay, so now this expression right here, the division, is an integer, and then this 30 is also an integer. All right, now we can do remove from top. So the combo boxes go ding, 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 if there are multiple combo boxes. Okay, let's do the sliders. Sliders are just gonna get the remaining area, so we can just do slider area equals bounds. We don't even need that, we can just do bounds like that. And we don't even need slider area. Okay, now this is gonna be bounds.getWidth divided by the number of sliders. And then this is again gonna be bounds.remove from left. Okay, if we've done everything correctly, we should see sliders laid out as well as buttons on the top for bypass, any combo boxes on the left side, and then sliders on the right side. Let's see what we get. All right. Okay, it's doing something. It's on Overdrive right now. All right, let's click on the Chorus tab and see what it does. Okay, cool. It's giving us all of our stuff. Ladder filter. So why is it doing that? That's interesting. Let's do a clean and rebuild and see if we can get that. See if that flickering goes away. All right. That's much better. All right. So we got our whole menu here. Awesome. It's sometimes helpful to clean and rebuild this stuff when you make a lot of big changes to the code. Okay, cool. All right. Hopefully you see the same thing that I see. Let's go make some to-dos in Plugin Processor to make the GUI look better. All right. So number one, the bypass buttons should be on the tabs themselves. Let me run this so we can see what I'm talking about. Okay, this bypass button, it should be over here on the tab itself, because if I'm listening to the overdrive and I'm tweaking it and the phaser's going nuts, I want to be able to turn the phaser off sometimes. Same for like if my general filter is doing stuff that I don't like, I want to be able to turn it off without having to actually go to the tab, click the bypass button, and then go back to what I was doing. That's annoying. So we're starting to get into ways we can improve the user's workflow when they're using this. So our first to-do is going to be to-do add bypass button to tabs. Okay. Next, it's not obvious which tab is selected. They don't really look any difference because they have a white background and a slightly less white background when they are not selected. So to-do make selected tab more obvious. Next, if I click on a tab and drag it, it doesn't change. This should have changed to the chorus and it didn't. The mouse down on the tab should change the GUI. Right now, we don't experience the change until we actually drop. So that's the whole thing. To-do, mouse down on tab during drag should change DSP. Okay. And then finally, these are ugly sliders. So we want to replace these vertical sliders with the simple multiband compressor rotary sliders. And then we want to, let's see, I'll show you what those look like. These guys here. We want to use these rotary sliders here that have the text in the middle and the name on top and the range on the sides. And then for the combo boxes, let's go to our general filter. I actually went with this thing. Same for the ladder filter. Yeah, we want to use that. And then for the bypass buttons, we want to use these bypass buttons here, like that. That's what we want to end up using. All that stuff is in the simple multiband compressor repository. So get that going. Let's add these guys as to-dos. All right. Let's commit our work. Implemented rough DSP GUI that dynamically changes and added to-dos. Commit. Awesome. All right. In the next chapter, we will replace the rudimentary sliders with the RotarySliderWithLabels class from Simple Multiband Compressor, beginning to improve the visual aspect of the plugin. See you there. Okay, in this chapter, we will improve the visuals by replacing these vertical sliders with these rotary sliders used in the Simple Multiband Comp plugin. The first step is to go to Producer and create a group. Let's see, we're done with audio plugin host. We're done with, okay, go to your file explorer, add a group to the source folder called GUI, GUI. All right, then right click on this and choose add existing files. Navigate to the Simple Multiband Comp subdirectory. Go to the source folder, go to the GUI folder, and select the following pairs of source files. Custom buttons, look and feel, rotary slider with labels, and then utilities. Okay, we need all 8 of these. Open, and then save and open in IDE. Close this down. All right. Try to build. There should be no compilation errors, but just in case, let's see what happens. Build succeeded. All right. If you go look in your Project Explorer, you will see these source files right here now. Let's make a commit that we added those source files. It's only a change to the JUCE file. We say added rotary slider with label source files, added label and related source files to, okay. Now that we've got these files in here, let's start using them. open the editor header file, and let's change the sliders in the DSP GUI. We can use forward declaration to change the slider class, and this only works if all implementations for this class are in a CPP file and not in a header file. This means we got to move this constructor over. So let's change the constructor to be strictly a declaration. Let's head over to the GUI, to the editor CPP file. Now let's insert a constructor. All right, we'll do that in just a moment. Let's go back here. I'm getting ahead of myself. Let's do a forward declaration of the RotarySliderWithLabels class. Struct RotarySliderWithLabels. Okay, and now we can change our sliders to use that as well. Now we need to go to the CPP file, and then way at the top where we include plugineditor.h, this is where we can include, if we set up our header files correctly, we might be able to just go like this. Rotary slider with labels.h. Yes, that is awesome. You can just do that. Now let's implement the constructor. Let's go to that. DSP GUI resized. Let's do it right before DSP GUI resized. Args, initialize something, and then curly braces. All right, we need our project 13 DSP audio processor, the reference P, or proc, however we want to do it. Okay, and then we're going to initialize our processor with that reference. Then finally, we need to update our sliders pushback way down here. Yeah, this thing down here. Now, let's go take a look at this rotary slider. Let's see, rotary slider with labels. Okay, this takes 3 parameters. Let's fix this, close off that thing, get rid of these curly braces. All right, so we need a JUCE ranged audio parameter, a unit suffix, and a title. Okay, now just be aware that we can determine the suffix and the parameter name from the parameter itself, but I don't want to modify the rotary slider with labels constructor to do that, because that could mess up other projects that depend on this repository. So we're just going to keep this rotary slider with labels class as it is, and just do P, and then the suffix is P label, and then the title is our P get name with 100, get a string that's 100 long. That is that process right there. All right, so we should be able to run it, and let's see what we get. All right, let me switch to phase. Okay, cool. They are rotary sliders now. They are missing the labels, and they don't look like this. So let's take care of that next. Let's save and quit, and then make a commit of what we've got. Let's change this to be replaced vertical sliders with rotary slider with labels. Goes there. All right. Now, labels are added to the slider by using a helper function found in the utilities.h file. Let's go look at that real quick. Utilities.h. Let's see, make attachment, get val string, add label pairs, this thing right here. So in order to use this, we need to go include the utility file, way up to the top. Include utilities. Let's go back to our slider.pushback section. That's going to be in the rebuild interfaces. Okay, slider.pushback. Now that we've got the slider, we can do simple mb comp add label pairs. And our labels are going to be these slider.labels. Our param is going to be p dereferenced, and then our suffix is going to be p label. All right, let's run and test. We should see something. Take a look at the phase control, see how that looks. Phase. All right, look at that. We got 0.1 hertz to 2 hertz, 20 hertz, 20 kilohertz, 0.1 to 100. So this is off right there. Same for that. That should be negative 100 to positive 100. This should be 1% to 100%. All right, awesome. But we got labels showing up. We'll fix those range issues in the next chapter. Let's make a commit though. Save and quit. Added labels to slide. Surprisingly quick to do that. That's because we spent all the time doing that work in simple EQ and then in simple multiband compressor, and then refactoring it into its own repository and submodule so we can use it in this one. That saved us a ton of time. All right, in the next chapter, we will tweak the visuals of the sliders and update the to-do list. See you in that chapter. Hey, if you like this tutorial that you've been following along with and have been wishing for a written version, check out the link below. You'll find this course as well as my other courses, all available in written format. They're full of detailed explanations, code snippets, and more. Each chapter is crafted to be easy to read and easy to follow. Complex features and ideas are turned into simple concepts with clear code snippets. You'll progress quickly as you elevate your app and plugin making skills by working through these projects. Programming isn't hard, it's just taught wrong. All right, let's get back to making this plugin. In the previous chapter, we created a basic dynamically changing GUI for each DSP effect. Some of the effect parameter ranges looked incorrect. For example, the mix param on this phaser was showing 0.01 to 1% instead of showing 0 to 100%. We're going to fix that in this chapter. Our first set of changes will occur in create parameter layout. Let's go look at that real quick. Plugin processor.cpp, create parameter layout, right here. Okay, that's all this stuff. All right, any parameters that we initially configured with a range of 0 to 1 or -1 to 1, such as phaser feedback or phaser depth, need to be updated to have a range between 0 and 100 or -100 to 100. We then need to update where the smoothers are updated from these params and scale the param value back to between its original range, which could be 0 to 1 or -1 to +1. The reason is because we originally configured all of the params to align with the effect property ranges described in the effect documentation. Since we just need the visuals to show a different range, it's easier to make this parameter range change where the params are created and scale them when passed to the smoothers versus making the change in all of the RotarySliderWithLabel code that displays the parameter range. In addition to these changes, we also need to update some param ranges and correct some suffixes. Here's the list of parameters that need changing: our phaser depth range and default value, feedback range, and mix range. The chorus rate is just way too fast. The default rate is way too fast. The depth range and unit, this is wrong. The feedback range, this is wrong. And the mix range, also wrong. Then for the ladder filter, let's see. The resonance range and unit is wrong. And then the cutoff, see, the cutoff was missing the unit in the tutorial. Apparently it's not the case here. All right, and then for the general filter, there is no unit for the cutoff in the written tutorial, but we fixed it here, so that's not a problem. So we got cutoff unit, then we have our quality range and the default value, and then our gain unit. That might not actually be a thing. It could be could just be artifacts from the written version that I'm reading. All right. Here's an example of the change to make. Let's go to the phaser depth range. We'll do one of these and then I'll take you through the changes. All right, so phaser depth. Okay, so it's 0 to 1 here, and it should actually be 0 to 100%. So 0, 100, and then we'll go in increments of 1/10. Our default then needs to be 5, and percentage is fine. All right, so now we need to look at our smoother, the list of smoothers that need changing. So our phaser depth smoother would need to be changed. Let's go look at that. That's going to be the update DSP from Params. So this would be the phaser depth right here. And for this, we do, the old one was just get current value, but we need to make this be in a range from 0 to 1, and it's currently from 0 to 100, so we need to scale it by 1/100th. Scale it by 0.01. All right, let's go fix all these guys. Let's go back to our, okay, phaser depth 0 to 1. This should be 1 to 100. All right, Phaser feedback should be negative 100. The thing of 100, that should be there. 0 is fine, percent is fine. Phaser mix should be 0 to 100 with a step size of 0.1, default value of 5.f. Okay, that takes care of the phaser mix and whatnot. Let's do the chorus. Chorus should change from 0 to 1 to be 0 to 100. The step size of 0.1 and a default value of 5%. The center delay is fine. Our feedback should be negative 100 to positive 100. The step size of 0.1, default value of 0, that's fine. Mix should be 0 to 100 with a step size of 0.1, the default value of 5%. Okay, overdrive is fine. All right, ladder filter, what do we got here? What is this? The resonance should be 0 to 100 with a step size of 0.1, a default value of 0. What unit should this have? Let's see. What did I put here in the tutorial? I put a percentage, so let's do percent. From 0 to 100% resonance. All right. And then for the drive, this was fine. It has no unit. Okay, so then our general filter, we just needed a quality. Is that a thing? Did I say that up here in my list of things? Quality range and default value. Let's go look at that. What did I end up coming up with? General filter quality name. I did a range of 0.01 up to 100. Interesting. And then I did it in 0.01 steps. All right. So 0.01, 100, 0.01 for the step size, and the default value is actually the square root of 2, or 0.72, because that makes it have a nice curve to it, I believe. It's like the Butterworth curve, I think. Could be mistaken on that. All right. Okay, let's go to the update DSP from Params function. Okay, our rate was fine. Our depth, our feedback. Feedback needs to be scaled by 100%. Our mix needs to be scaled by 100%. Okay, our depth for the chorus needs to be scaled. Our feedback for the chorus, yes, needs to be scaled, and our mixer for the chorus needs to be scaled. All right, our ladder filter resonance, let's look at that. Does that need to be scaled? Yes, it does. All right, what about drive? No? Okay, just ladder filter resonance. All right. Okay, for the filter, that's where we do the coefficients. Do we do anything with that? No, we don't touch the, we didn't do any scaling for the general filter for these guys. These guys didn't get touched because we just changed the range. We didn't change the actual value of it. We didn't change the unit scaling. All right, let's run it. We should have some good parameter ranges now. Let's take a look at that. We'll figure that out in just a second. Okay, phaser feedback, negative 100 to 100%. Mix 0 to 100. This looks good. Overdrive, we got from 0 to 100. Cool. Chorus, all of this looks good. 0 to 100 for the depth, 1% to 100%. Oh, that's the wrong unit right there for chorus center delay. Let's go to that parameter. Chorus center delay. Chorus rate name, chorus depth, chorus center delay. Yeah, that should be milliseconds, not percent. Let's go back, looking at this. Chorus feedback is percentage, chorus mix is percentage, good. Ladder filter, our cutoff is in hertz, our resonance from 0 to 100%, and our drive from 0 to 100, good. Our general filter, same, quality from 0.1 to 100, negative 24 dB to plus 24 dB. All right, all of this is looking good. Let's run some audio through this. No, oh, I forgot my headphones. All right, it's really muffled, really crunchy, and that is because the overdrive filter is on. Once we bypass it, sounds fine. That is because the overdrive's default cutoff is very low. We need to set the cutoff in prepare to play to, so go to prepare to play. Is this the right prepare to play? No, we're in the wrong one. We want to go to this guy. Over here is where we say, let's do this before we prepare or we can do this after we prepare and reset. Overdrive.ds set cutoff frequency. This needs to be 20,000. Let's try that again. We should be able to bypass the overdrive filter and it shouldn't change the thing, especially if we have the drive up. All right, let's go to the overdrive. Let's press play. Crunchy, but the high end is there. All right, that's working as expected. That song sounds crazy when the drive is up hot. Probably feeding too hot of a signal into here. It's also probably not meant for an entire song to be passed through it. Okay, if the audio sounds clear and the param ranges look correct, go ahead and make a commit. Adjusted param ranges so they display correctly in the GUI. Now, next, you might have noticed that the sliders do not look like these sliders. So we're going to fix that in this next commit. The problem is that we forgot to apply the look and feel to our rotary sliders. This is pretty easy to rectify. Let's close this out. We just needed to give an instance of the look and feel class found in the lookandfeel.h, as right here. We just need to include it somewhere and then give ourselves an instance to it. So let's go do that. Let's include it. Include. Let's give this to the editor, all the way down to the editor, after our audio processor. Go look and then when the editor is constructed, we just need to set the look and feel. Set look and like that. And then in the destructor, we need to set look and feel to be. If we run it and test, we should see everything looking good now. Hey, there they go. And our bypass button is now. Okay, cool. That's doing the thing that it needs to do. We can go ahead and make a commit. If our plugin looks like this on your commit message is applied LNF slider visuals are now correct. All right, let's mark some of these to-dos as done. Plugin processor. We want to replace vertical sliders with simple rotary sliders. That is done. Replace bypass buttons with simple MB comp bypass buttons. Or is it? Well, they were looking different. Let's add some more to-dos. This one's actually going to go away when we add the bypass buttons. This isn't really done, but we're marking it as done because it's using the simple MB comp bypass field. It's using that color scheme. All right. So this new to-do is going to be restore selected tab when window, and then restore tab order when. All right, let's commit these to. Removed some to-dos. Awesome. We made some excellent progress on the visuals of our plugin in this chapter. In the next chapter, we will tackle saving and restoring that'll be a good one to implement. All right, chapter 31, remembering the selected tab. In this chapter, we will implement the ability to remember which tab was selected whenever the GUI is closed and reopened, or when the DAW session file is closed and then reopened. First, we are going to need a selected tab parameter. So head on over to your plugin processor.h and let's declare one here. JUCE audio parameter int selected tab equals null pointer. All right, next, we need to create an audio parameter and initialize the cached parameter. Let's add a function that returns the parameter name. Along with all these guys, do it right up at the top. Auto get selected tab name, return JUCE string, selected tab. All right, and then go to create parameter layout and just stick this guy at the bottom. let's see, name equals get selected tab name, layout.add. Here we want std make unique JUCE audio parameter int, this thing. All right, got a lot of parameters to fill in. Get rid of that. Semicolon. Okay, let's put all this stuff on its own line. All right, our name, we can fill that in. Our parameter ID is going to be this same parameter ID thing we use everywhere. Okay, our minimum value is going to be 0. Our max value is going to be the DSP option end of list -1. So static cast int DSP option end of list -1. And then our default value is going to be the chorus. Let's just do the chorus tab as the default value. Static cast int DSP option. All right. Okay, finally, this is our first int param. So we need to replicate the pattern used by the float, bool, and choice params in the constructor to initialize this. Create an array. Let's go down here. Let's do it at the end. Auto int params equals std array, address of selected tab. Auto int funcs equals std array, get selected tab name, then init cached params, and this is going to be JUCE audio parameter int. This one here with the pointer, and we've got our int params, and then our. All right, cool. Try to build that. Shouldn't get any error messages. And if you got build succeeded, go ahead and make a commit. Added param for selected tab. Okay. And now that we have an audio parameter to store the selected tab, we need to make use of it. Parameter attachment instances are used to connect GUI widgets with audio parameters. The attachment's job is to keep the GUI widget and the audio parameter in sync. There are 2 events that will involve the attachment. Let's run this so we can talk about those 2 events. Whenever the user clicks on a tab, we need to update that parameter value. And then whenever the plugin state is restored from disk, we need to make the GUI show the selected tab. All right, let me close this out. Let me read this comment that I left myself that explains the thought process behind some of the code we're going to write. And I'm going to put this on the screen. We can look at it while we are reading it. And we'll just, where are we going to put this? This is going to go in plugin editor because we're going to be dealing with attachments. All right, here's the comment. All right, selected tab restoration requires a parameter attachment to exist. The attachment is also in charge of setting the selected tab parameter when the user clicks on a tab. When the tab is changed, the interface is also rebuilt. When the audio parameter settings are loaded from disk, the callback for the parameter attachment is called. This callback changes the selected tab and rebuilds the interface. The creation of the attachment can't happen until after tabs have been created. Tabs are created in timer callback whenever the restore DSP Order FIFO has a DSP Order instance to pull. This is why the attachment creation is not in the constructor, but is instead in timer callback after it is determined that the restore DSP Order FIFO has items to pull. Okay, so here's the takeaway from that. Parameter attachment creation won't happen until timer callback is called. Let's take a look at that. Timer callback. It's not going to happen until we get to here. The parameter won't be updated unless the user changes the tab, which means we need to notify listeners when a tab is clicked and make the editor be notified when the tab changes. So let's dig in, head over to plugineditor.h, and after our extended tabbed bar component, let's add an attachment. std unique pointer JUCE parameter attachment. This is selected tab attachment. All right. Next, we need to update the listener class for the, let's see, where's that listener class? Where's that? That's way up here. All right, we need to update this class to have another callback for when the tab is actually changed. Virtual void selected tab changed int new current tab index. All right, let's go put this into Let's go put this in our listener. Tab order change. This goes right here. Override. This is in the editor where we're going to add this. Okay, we will invoke this callback by overriding the virtual tabbed button bar current tab changed function in our extended tabbed button bar class. Let's go look at that. That's under tabbed button bar. Let's just go up here to find that. You can see more code. Tabbed bar button. We want tabbed button bar. Tabbed button bar. Jump to definition. We are looking for what's this function called? Current tab changed. We just look for the word virtual. Virtual current tab changed. Callback method to indicate the selected tab has been changed. Let's add the following declaration below the remove listener call. In editor. Let's see, remove listener. Yeah, add this here and override it. Okay. This thing is called whenever we click on one of the tabs. So let's begin implementing this function. We'll put this below remove listener in our CPP file. Remove listener right here. Void extended tabbed button bar : : then the thing. Let's make sure it's lined up. Curly braces. All right, now we can do, let's see. This needs to have a proper name, which means we may have forgotten that over here. Yup, JUCE string, okay. Let's see, now we need to go listeners.call, and let's see what the autocomplete does. Oops, there it is. Callback, all right. We're gonna grab the new current tab index. Remember, we gotta pass in our listener L. Where did we do that before? That was right here. We got to do this thing. So we'll just copy that. All right. And now instead of doing tab order changed, we're going to do selected tab changed with the new current tab index. And then we don't want to get a warning about this, so we will just call JUCE ignore unused that thing. All right. Next, we need to implement the callback handler in the editor class. So let's go do that. Where did we put that? All right, here's the selected tab changed. Okay, I'm gonna move this comment to be in there for that. Let's go to, let's see, where should we put this? We'll just put this at the very end after rebuild interface. Void project 13 audio processor editor selected tab changed. Let's put this comment in here. All right, so do we have an attachment yet? No. The callback handler's job will be to update the audio parameter by invoking the set value as complete gesture member function of the attachment. Did we add an attachment? We did add an attachment. Okay. So first of all, it's in a unique pointer, so we got to check if it's an if it actually exists. So if selected tab attachment, if it exists, now we can do selected tab attachment, set value as complete gesture, and then we need to cast our new current tab index to a float. Static cast float, new current tab index, and then finally we rebuild the GUI, rebuild interface. Okay. Finally, we need to create the attachment. As we stated earlier in the block comment, this big chunk right here, the attachment will be created in timer callback. Here it is. Okay, the logic will be if the attachment doesn't exist, we will create it. The attachment callback will set the selected tab in the tabbed component. Note the callback is called whenever the parameter's value changes. And then finally, the attachment will send an initial update, which will properly set the selected tab of the tabbed component. Let's dive in on this and build this. Okay. We always do this here. All right. If selected tab attachment equals null pointer, then we got to make one. Selected tab attachment equals std make unique JUCE parameter attachment. All right, let's clear these guys out. Close off that template parameter. Our audio parameter is the audio processor selected tab. That's a pointer, so we got to dereference it to get a reference. And now we've got our lambda to write, which takes a float. Square brackets, parentheses, that takes a float, and then the body. Okay, we're going to capture this because we're going to interact with our member variables. All right, right here we say auto new tab num equals static cast the tab num. That's what's being passed in. And as long as this is lower than the number of tabs in the tabbed component, we can set the tabbed component to this new tab number. So let's make sure that's cool. If JUCE is positive and below, new tab num is going to have to component num tabs. As long as that's fine, then we can do tabbed component, set current tab index, new tab num. Otherwise, you got a problem, JAssert false. And then after we've made our attachment, we do selected, After we have created our attachment, we do selected tab attachment, and then do send initial update. All right, build and run. Okay, in order to test this correctly, you must delete your plugin from audio plugin host and then reinstate it. So delete the filter, right click and reinstantiate it. Then do the following test sequence. Select a tab other than Chorus. I'm going to select LadderFilter. Save the APH. Quit APH. Relaunch APH, and you should still see the same tab open when it launches. All right, look at that. LadderFilter is open again. Fantastic. Let's do it one more time with the Overdrive. So deinstantiate, create a new one. I'm going to set this to Phaser, save and quit, reopen, and I should see the Phaser as the selected tab. And there we go. All right, if the selected tab is remembered between launches, make a commit. Selected tab is restored when app opens from delete, reinstantiate. Okay, let's update our to-dos. Go over here. Which one? What are we updating here? All right, these guys right here. So restore selected tab when window opens. That is done. And then restore tab order when window opens. That is also done. Here are 3 more to-dos that relate to the selected tab and making sure that it works correctly in all scenarios, not just when saving and quitting. Let's add those here. To-do, restore tab order when window opens first time. After to-do, restore tabs when closing, opening the window, no quit. And then to-do, restore selected tab when closing, opening window. These to-dos may or may not require code changes. We'll find out after we just test each one. Let's commit these to-dos. Updated to-dos. In the next chapter, we will tackle these to-dos and also get started on implementing metering. See you in that chapter. All right, chapter 32 of 40, restoring the tabs when reopening the plugin window. In the previous chapter, we implemented the ability to remember the selected tab between DAW or host session loads. Now we will implement the ability to remember the selected tab whenever the plugin window is closed and then reopened without the DAW host session being closed and reopened. After we do that, we will get started on the metering side of things. This is a fairly simple problem to solve. If you remember, the selected tab attachment is only created when tabs have been added to the GUI. Tabs are only added to the GUI when set state information is called currently, and the way the tabs are added is by pushing the current DSP order into the restore DSP Order FIFO. All we need to do is signal from the editor that the current DSP order should be pushed into that restore DSP order for the editor's timer callback to parse. The best way to signal from the editor is with an atomic flag. So that is what we will do. We will add an atomic flag to the audio processor. The editor will modify that flag when it is constructed, because the GUI is only constructed whenever the GUI appears on the screen. Then we will query that atomic flag in process block. If the flag is true, meaning the GUI has been constructed, we will push the DSP order into the Restore DSP Order FIFO, and then all the stuff that happens when there is something in that FIFO to pull out will be executed, restoring the selected tab whenever the GUI is reopened. So let's go to our list of smoothers, and we'll put this right after it. JUCE atomic bool GUI needs latest DSP order with the default value of false. Okay, then we just query it in process block after updating DSP order. Let's go to process block. Okay, here we are. We have updated DSP order right here. We go like this. If GUI needs later DSP order dot compare and set. Let's wait for this autocomplete to pop up. Atomically compares this value with a target value, and if it is equal, sets this value to be equal to a new value. So if this is set to true, then set it to false. And then restore DSP order FIFO dot push the DSP order. All right, and I just want to add an explanatory comment here. When the plugin is first loaded, if the GUI is closed and reopened, the restore DSP order FIFO is empty. The restore DSP order FIFO is only populated when set state information is called, and atomic flag is used by the editor to signal that it needs the latest DSP order. Here is where we check that flag and push a copy of DSP order into the restore DSP FIFO for the GUI to retrieve callback. All right, then finally, let's go over to the editor's constructor, and we just set it to true over here. Let's go to that constructor. Let's do this before we add our listener. Audio processor, wake up, there it is. Audio processor, GUI needs latest DSP order dot set true. Okay, here's how we test this. We launch the GUI, we select a tab, we close the plugin but not the host, and then we reopen the plugin and we should see the same tab. Okay, so let's select Overdrive. We'll close this, we will reopen, and we should see Overdrive. And boom, it works. Let's switch to Chorus, close this, reopen, and select to Chorus. All right, perfect. Let's save and quit. All right, now we can mark these to-dos as done because we tested those scenarios. All right, where are those to-dos? Right here. Restore tab order when window opens the first time after quit. That's done. Restore tab order when window opens. Restore tabs when closing and opening. That's also done. And then restore selected tab when opening and closing without quitting. Also done. Cool. Let's commit all of that. The message is implemented. Oops, implemented. Restoring tabs when GUI is closed, reopened without quitting APH. Excellent. All right, let's get started on the metering. Now, metering is actually very simple. All you need to do is map a value from one coordinate system to another and then draw it repeatedly, usually with a timer. In our case, we will be mapping decibel values into screen coordinates. For this plugin, I'm going to use a decibel range of -72 decibels to +12 decibels. Let's add these to the top of plugin processor.h after the general filter enumeration. Expr int -72, and then static const expr int max decibels. Actually, this general filter enumeration is supposed to be not part of the class, so all of these are going to go to the top of the header file. So you're going to go way up here, right there. Okay. Next, we need a variable to store the value we will be mapping. This plugin is going to display 4 values: input left, input right, output left and then output right. And since the audio thread and GUI thread are separate threads, we need to use thread safe variables to store these values. We will use atomics for this, just like we used in the section on the selected tab. The need to send the current DSP order to the GUI whenever the GUI is reopened. This plugin will display RMS levels and not peak levels. So let's go add 4 more atomics. Let's go add those right here. These will be atomic floats. JUCE atomic float, and this is going to be left pre-RMS, right pre-RMS, and then left post-RMS, right post-RMS. Pre and post refers to before DSP processing and then after DSP processing. Now we just need to update these guys in process block. All right, so the pre-RMS values will be computed before the DSP is applied, and the post will be computed after. So let's go to where that is happening. Let's see, here's where all of our processing occurs. So this is code that happens before this line is before it. Code that happens after it is post. So anything that comes before this loop is pre-processing, and everything that comes after it is post-processing. Okay. All right. We're going to update this snippet prior to the start of the, first of all, this is going to be const. Auto samples remaining. Let's see what is happening here. So first things first, the audio buffer, the audio buffer class has a member function called getRMSLevel, and it needs the number of samples. I'll just show that real quick right here. Buffer.getRMSLevel. It needs the number of samples and the sample you want to start at in order to compute the RMS level. So we're going to cache the number of samples locally and use it when computing the max samples to process and the RMS levels. So we've got our samples remaining. First of all, this is going to be num samples. I'm not going to change that. And then we're going to do auto samples remaining equals num samples. So we've got an unmodifiable version and then a modifiable version. All right, and then now we've got our max samples to process, and down here is where we can get those levels. So left pre-RMS channel dot set buffer dot get RMS level. Our channel is going to be 0 because it's the left one. Our start sample is 0, and our num samples is. Do it again for the right side. Dot set buffer.get RMS level. Channel this time is 1, 0, and num samples. To be consistent with my spacing around parentheses. Okay, at the end of process block, do the exact same thing, but do it with the post. Left post and right post. Post, post. Okay, let's compile that and make sure there are no build errors. If you want to see if this is working, so just run it, run some audio through it, and then add some breakpoints on these lines. Let's do that. I'm going to wire this up so it doesn't produce any sound, but just so we can press play and see it. Let's go like that. Hopefully it's not making, that's down. All right, so this is running audio through it right now. Let's add a breakpoint right here, and then let's go look at these. Let's see, where are these pre and post RMS levels? Let's collapse our DSP order. So here's the RMS. We can see our actual atomic values here. We can see that our left pre-RMS value is different than our left post-RMS value, which means the DSP is doing something that's changing the signal level. Same with on the right side. We got 0.082, and here we got 0.094. So a little bit of gain is actually being added. Okay, we know that that's working. Remove this breakpoint, press commit. Quit this, and then make this commit. You can do some graphics in the next chapter. RMS levels are computed and stored in atomics. Commit. Okay. In the next chapter, we will use these atomic variables to implement GUI metering. All right, chapter 33, adding meters to the GUI. In this chapter, we will make use of the atomic variables we created and updated in the previous chapter to draw an incoming and outgoing signal level. All of the work that we will be doing in this chapter will take place in plugineditor.h and plugineditor.cpp. The first thing we need to do is make room for the meters. So go to plugineditor.cpp. All right, under set size. This thing's got to be wider, so we're going to make it 768 units wide. Next, we need to shrink the tabbed component's width on either side so there is room for the meters. Go to the resized function to do that. Let's think about this a little bit. We want the meters to have the same fixed size, so let's add a constant expression int to do that. Let's put that below the tabbed component. Static const exper int meter width equals 80. We'll just hard code it at that. Now let's use that to define the meter area in resized from our local bounds. Left meter area equals bounds.remove from left meter width, and then auto right meter area equals bounds.remove from right meter width, like that. All right, we're just going to ignore those two for right now. JUCE ignore unused meter area, right meter area. Come back to them later. All right, let's get rid of this. And then we've got our tabbed component sitting in between them. Let's see how that looks. We should see gray slides on either side of the main GUI. All right, yeah, gray on the sides. All right, let's leave this on the chorus. Cool, save, quit. All right. Our next job will be to start displaying a meter. For this, we create a black background in the meter area, then we fill a rectangle with another color. The rectangle will have the following qualities. Let me pull this up so we can look at it. The bottom will always be the bottom of our background meter area. The top will be defined by mapping that atomic RMS value from the decibel range to the height and top of the rectangle. So here's a bit of background information. A decibel value of negative infinity maps to a normalized value of 0, which is way down here. Remember, we defined negative infinity to be negative 72 earlier in this project, and a decibel value of 0 maps to a normalized value of 1. So if the normalized value is greater than 1, I'm going to want the part of the signal that is greater than 1 to be displayed as a red rectangle, and the other part from normalized 0, way down at the bottom, to normalized 1 to be drawn as a green rectangle. I'm going to be using lambdas inside the paint function to accomplish building the meters because I just don't want to create a bunch of member functions right now, and that just slows down the development process, getting bogged down with C++ semantics. So here's how the lambdas are going to work. First of all, let's go to the paint function. Get rid of all of this. We don't need any of that stuff. Okay, the first lambda is going to work like this. We're going to pass in a bounding box to draw inside. We're going to pass in the RMS source, and then any RMS value over 1 is going to be shown as a red rectangle, and then any RMS value up to 1 will be shown as a green rectangle. Pretty simple, but when we build it, it's going to be kind of complex. All right, let's start with an empty lambda to get started. Actually, we'll leave our background color in there. Rid of this stuff though. All right, so autofill meter equals lambda. We're going to capture all of our stuff because we're going to deal with our graphics context. Here's our rectangle, and then here's our, let's see, we're not going to modify this, so this is going to be const RMS source, like that. All right. That is step 1. Inside, let's start by filling our rectangle with all black. G.setColor, colors black, G.fillRect. Next, figure out if the RMS level is greater than 1. Auto RMS equals RMS source dot get. If RMS greater than 1, we're going to do something. And then inside this block, we are going to do 4 steps. First, we're going to define a point at 0 dBFS. Then we're going to define a point at RMS dBFS. we're going to define a rectangle using those points, and we're going to fill that rectangle with red. So remember, we are mapping values from the range -infinity max decibels to bottom of rectangle, top of rectangle. Let's set our color to begin with. Set color, colors red. All right. Let's define a point at 0 RMS, auto lower left equals JUCE point. And this is going to be a float. This is going to be rect.getX. And then we're going to have JUCE JMap. This is going to be JUCE decibels, gain to decibels, 1. And then we're mapping that value to -infinity, max. And this is going, let's see, you know what, let me do it this way. JUCE JMap. Our source value is going to be our decibel, a gain value of 1 converted into decibels. With our source range minimum, it's in a gain, it's in decibels, which start at -infinity, and they go up to max decibels. And then our target range is going to be the bottom of the rectangle to the top of the rectangle. So rect.getBottom, and then rect.get. And because this is a float and these are integers, we actually need to make this templated and force it to treat everything as floats. Am I missing an extra one? I am missing an extra one. All right, that's our lower left point. And we need to do the same thing with the upper right. Auto upper right equals JUCE point. Same thing again. Float. This is going to be rect.getRight. And our Y value is going to be the same type of mapping of, let's see, JUCE RMS. I'm sorry, JUCE JMap. All right, yeah, JUCE JMap. Our source value is going to be the RMS level. And this is going to be the same. Oh, we have an extra one. And this needs to be force it to treat each of these values as a float value. Okay. So now we need to define a rectangle using these points. So auto over threshold equals JUCE rectangle, and then corner 1 and corner 2. This will be a float rectangle using lower left and upper right. And then finally, we fill that rectangle g.fillRect over thresh rect. This takes care of drawing any signal over 0 dBFS. So again, we are mapping the value of a decibel value of 0 that exists on the scale of -infinity and max decibels. -infinity being -72, max decibels being +12. -infinity is the bottom, max decibels is the top. We have a value of 0 that sits between them. This is mapping that point. That point forms the bottom of a rectangle, and our RMS level is going from here up to max decibels. And that's what gets figured out right here. And then we're just drawing that as a rectangle. Okay, let's draw the rest of our signal. And we do this by clamping the RMS level at, we clamp this RMS level at 1. JUCE, so we go RMS equals JUCE JMin, and this is going to be RMS 1.f, and let's force that to be a float just for safety. So if RMS is like 1.25, we're basically drawing the 1.25. We're basically drawing the 0.25 here, and then we're drawing the 1 right here. That's what we're going to draw for this. G.setColor, colors green. Then we're going to do the same thing, G.fillRect, and here we got rect.widthY. And then here's where we do our similar mapping, actually the exact same mapping. So this gives us this rectangle. We've given it with a width Y, and we want to give it with a width bottom, rect.getBottom. All right, so the rectangle has a top at the Y value, whatever it was. If it was greater than 1, then it's got a then the Y value is right at 1. And then the bottom of it stays exactly where it was. That's what this line does. And then finally, we're already doing the fill step, so that's fine. Why has this not turned green? Let's see if we got a build error. And if not, then we're just waiting for the syntax highlighter to do its thing. Okay, cool. It's doing its thing. All right. It's thinking in the background. Cool. Let's test this out with the left channel pre-RMS. So let's get the bounds of our component. Auto bounds equals get local bounds. Let's get our pre-meter area. Auto pre-meter area equals bounds.remove from left meter width. And now we just need to call fill meter with our pre-meter area. And our RMS source is going to be the audio processor left pre-RMS. In order to see something, we need to make the GUI continuously repaint. So let's add a call to repaint in timer callback way at the end, way down here, repaint. Hey, it's future me. I'm just going through and editing this. The next 7 minutes of footage involve me figuring out why this is not repainting correctly. If you want to watch it, it's valuable in its own right for the explanation of the debugging process to figure out how to find bugs like these. But if you just want to get to the solution, jump ahead 7 minutes. I'm going to have a little clip that explains what the bug was, why it was caused, and then we'll proceed with the rest of the tutorial. All right. Go ahead and check it out if you want. Otherwise, skip ahead about 7 minutes. Let's go ahead and run this and pass some audio through it, and we should see the meter light up. Let's see what we get. Let's press play. Oh, what are we forgetting to do? What did we not do? We didn't do something. Now we got to go figure that out. Well, let's make sure this lambda is looking correct. You know what? We can go into plugin processor and make sure our left pre-RMS is actually changing. Our left pre-RMS value is 0. Is that because we're not playing any audio? Press play. Add that breakpoint. Check that again. Left pre-RMS level is 0.24. Okay, cool. That's fine. Let's go into plugin editor.cpp. This is going to hit this breakpoint here. Oh, it's actually not refreshing. Did we not start our timer? Well, let's see what we got. Left meter. Step on in here. All right, let's see what our RMS source value is. Okay, that's not 0, so this should be drawing something. So now it's just a question of why isn't the paint function being called? Am I not reading the right thing? That's supposed to be jmin or jmax. Oh, it is jmin. Let's add a debug statement right here. It's very odd this isn't coming through. I must have copied something wrong. All right, it's changing It only changes values whenever I mouse over it. So what's going on with this timer? Is timer callback not being called? Let's find out. This is very odd. You know what? Let's do that clean and rebuild thing. I always forget to do that. It's usually the easiest way to find a problem. It was only refreshing whenever I moused over it. And it should have been repainting every single time. Oh, you know what? It's because of this. If there's nothing to restore, then it's going to exit. So we actually don't need to do that. We just need to move this repaint to be right at the top. Make sure it always does that. Ideally, what I would do is put this in curly braces and make an else statement and then put the repaint at the very end. But this is fine for right now, which means we don't need this debug message. A little bit of sleuthing. It's all right. It's part of the process. We should see some movement now once this is done building. All right. It's doing it. Let's jump forward to a quiet part of the song. It's pretty high level. Let's jump way to the end. Why is that not, it should be decreasing. You know, I'm going to put this back in here. Debug, RMS. Did I forget to convert this? I did forget to convert this. This needs to be converted. That's a big problem right there. It's always something. JUCE gain to decibels. All right, that's going to work now. The RMS level was really, really close to +1, which is really, really close to the top of the meter. There it goes. Now it's moving. All right. Apologies for the chatter. Trying to get that working. That's what happens sometimes. It's okay to make mistakes. That's how we learn. That's how we learn to solve for stuff. All right. Let's turn this off, save and quit. All right, just doing a quick overview of what the error was that caused that. So there's two issues. The first issue is that when I did the mapping, I was not converting the RMS value, which is a value from 0 to 1, into decibels, which is what is needed for this JMap call. The JMap is mapping from decibels into screen coordinates. So I need to pass it a decibel value, and I had forgotten to use the gain to decibels function. So I did that in two places. For this upper right coordinate of the rectangle, I forgot to do it there. And then I forgot to do it again for the remaining rectangle, the part that's not over the threshold, this part here. And then the second issue was in timer callback. I had put this repaint call after this return statement, and if the restore DSP order FIFO is empty, then no repainting was happening. This repaint call was way down at the end of here. So that was the second mistake causing it to not repaint, even though the timer callback was continuously calling. All right, let's continue on with the rest of the tutorial. Let's add the remaining meter by calling this lambda a few more times. We need to split the meter areas in half and also getting bounding box for the post meter. So let's do that. Pre-meter area is this, and then auto post meter area equals bounds.remove from right meter width. Now our left RMS meter is going to be pre-meter area dot remove from left. You can just say meter width divided by 2. Then fill meter pre-meter area, and this is going to be the audio processor right pre-RMS. Then do it again, fill meter post meter area dot remove from left meter width divided by 2, and this is going to be the audio processor left post RMS, fill meter post meter area, audio processor right post RMS. Pretty simple. Let's see how that looks. We should see 2 meters on one side, 2 meters on the other side, and if we do some big tweaks to our parameters, we should see some definite visual changes between them. Let's turn on our music. Okay, we got our stuff running there. If we turn on the drive, we might see the right side actually turn into the red. No, it's just clipping out. That's fine though. Just filter some stuff out and make the right side get really quiet. Oh, there it goes. Let's make that a 24 dB per octave low pass. All right, there we go. So the right side is definitely doing its thing. Okay, let's save and quit this. All right, let's add some tick marks so we know where 0 dB is and where the other signal levels are. I'm going to use a lambda for this as well. And ticks can be drawn by drawing a 2-point tall rectangle, the width of the meter rectangle, with the center of the rectangle set to a specifically component mapped decibel value. That's a weird sentence. In addition to drawing tick marks, I want to show decibel values, and this lambda will draw that as well. So let's add another constant for the font height where the meter width was declared. Static constexpr int font height equals 24. And I want to show tick marks every 12 decibels because 12 dB lines up nicely with our the constants that we've got for this. 72 is a multiple of 12, as is max decibels. So this is going to line up nicely. Or the other thing that I want to do is have the tick marks not extend from the left edge of the rectangle they are being drawn in to the right edge. I want the ticks to have a gap on either side. And I don't know how much of a gap will look nice, so I'll make the gaps be lambda arguments. So let's start with a blank lambda after all this fill meter stuff called draw ticks. Auto draw ticks equals, and we're capturing everything because we're going to be in the graphics context. Auto rect, auto left meter right edge, and auto right meter left edge. Okay. Let's loop through the decibel range we are supporting. I'm going to start at max dB and decrement. So for int I max decibels, I is greater than or equal to -infinity. I minus equals 12. Okay. First, we are going to compute the mapped y value for the decibel being displayed as a tick. Auto y equals JUCE jmap this thing, and we're going to use integers. Our source value is going to be I. Our source range is going to be -infinity. Our max source range is going to be max decibels. Our target range minimum value is going to be the bottom of the rectangle, and our maximum value is going to be the top of the rectangle. Rect.getY, like that. Okay. Now let's create a rectangle using that. Auto R equals equals JUCE rectangle. And we're going to use these 4 points. No, we're going to use our width and our height. This is going to be, let's see, it's going to be an integer type. Our width is going to be a rectangle, and our height is going to be the font height. And then we're going to set the center, r.set center, using British spelling. It's going to be the center, the x center of this, and then this y value. So rect.get center, and then y. Now, we're going to set the color to be red if the decibel value is greater than 0, white if the decibel value equals 0, and light blue if the decibel value is less than 0. So we do g.setColor, I equals 0. It's going to be JUCE colors white. Otherwise, if I is greater than 0, then it's going to be JUCE colors red. Otherwise, it's going to be JUCE colors and then a light blue. Looks like I went with light steel blue for some reason. All right, and now we can draw the decibel value inside the rectangle. G.draw fitted text inside this rectangle. Our text is going to be JUCE string. Our decibel value, known as I. Our area is going to be R. Our justification is going to be centered. And we're going to draw it on one line. All right, let's see what that looks like. Well, are we doing that yet? According to this tutorial, we are building more stuff first. I kind of want to see what that looks like though. So let's do draw ticks. Let's do the pre-meter area. Left meter, right edge is, let's just make that like 10, and this will be like, maybe that looks like some. Maybe, maybe not. Let's just see. We're experimenting. This is a 40 wide rectangle. We'll see. We'll probably, maybe this will look like something, maybe not. We're just testing out to see if this, or if it looks like anything. Okay, we got something there. It's doing its thing. We got a little crowding at the top, crowding at the bottom. We'll figure that out later though. All right, let's continue on. Let's draw tick marks inside of the meter bounds, not at the top or bottom. I'm going to use graphics draw line to do that instead of drawing a 2-point tall rectangle with a fixed center. As stated earlier, the other thing I want to do is have the tick marks not extend from the left edge of the rectangle they're being drawn into the right edge. I want the ticks to have a gap on either side. So let's define another constant representing the tick indent. Static const expr int tick indent equals 8. The tick on the left meter will sit between the x coordinate of the rectangle packed in and the left meter's right edge. So let me just pull that up. We'll run a little bit of signal through this so I can show you what I mean by that. Okay, so we want the tick mark to kind of appear over here, not on this edge here. It's going to appear right there according to this. So the tick for the left meter will sit between the x coordinate of the rectangle passed in and the left meter's right edge. So somewhere in here, but not on the right edge. And then the tick for the right meter is going to sit between the right meter's left edge, so right over here, and the right edge of the rectangle passed in. So looks like it's going to be kind of in the middle maybe. And the tick indent will offset these x coordinates. All right, let's close this. Let's go back here. All right, let me get rid of this line. We'll figure that out later. Okay, we just drew our text. Let's draw our ticks, and we're only going to draw them not at the top or the bottom. So if I does not equal max decibels and I does not equal -infinity, We can draw our tick. G.drawLine. Do this one. Rect.getX plus tick indent. And our Y position is going to be the Y. Our end X is going to be left meter right edge minus tick indent. And our Y value. So it's a horizontal line. Starts on the left edge. Starts on the left edge and goes inward. Then it goes all the way to the far right edge and then back. That's what that line does. Do the same thing on the right side. G.drawLine. Right meter left edge plus tick indent, a Y value, and then rect.getRight minus tick indent, and then the Y value there. Indent, not index. Oh, I spelled it wrong there as well. Okay, that should be fine now. Now, the left meter's rectangle is being chopped in half right here when the call to fill meter happens. So we need to make a copy of this first before we do that. Auto left meter area equals pre-meter area. Same for the right side. Auto right meter area equals post meter area. Okay, this line right here, pre-meter area dot remove from left is chopping the pre-meter area in half. We want to get the full size of it before we do that. Okay. Since we need room for the decibel text, let's define one more constant that will represent how wide we want each meter to actually be. So let's go to our constants. Static const expr int meter chan width equals 24. So even though the meters are 80 points wide, they're actually going to be the actual vertical channel is going to be it's going to be 24 units wide. So there's actually going to be a gap space in the middle, and the actual green meter level bar is going to be kind of narrow, surprisingly. All right, let's go back to plugin processor. Let's go back to plugin editor. After our draw ticks. All right, you know what? Let's move all of this stuff to be after draw ticks. All right, so we've got our fill meter code, Let's do our draw ticks function next. Draw ticks. Our rectangle is going to be the left meter area. And let's see, this is going to be left meter area dot remove from left the meter chan width. Get right. And then we've got our left meter area dot remove from right meter chan width. Get X. All right, that is complicated. What is that doing? Okay, we've got our left meter area rectangle, and then we are trimming off the left edge and getting the right side of that thing. Then we are removing the right from it and getting the X of that. So this is a little complicated. But basically, imagine that we've got this rectangle here like this, and we're chopping off the left side and getting the right edge of that. So this is still the far right side. Then we're chopping that off, and now we're getting this new left edge. It's not the most intuitive way to write this to make it easy to understand, but it's going to give us the look that we want. And we're going to do the exact same thing on the other side. Draw ticks in the right meter area. This is going to be right meter area dot remove from left meter chan width. Get right. It's going to be right meter area dot remove from right meter chan width. Again, get X. All right, let's check it out. We should see some ticks on either side, and then some numbers in the middle. We'll see how that looks. All right. Okay, cool. So let's press play and see how that looks with our meters running. Awesome. That actually looks like something. Let's consolidate this and write one more lambda that calls all of this code. Calls all of this code for each meter. and draws the complete meter. So this lambda will draw the following: the left value sourced and mapped, the right value sourced and mapped, and then the ticks and a label for the meter's name. So instead of capturing everything, I'm only going to capture the previously declared lambdas by reference. Everything else that's needed in here will be a function argument. We're going to need the rectangle to draw the full meter in, the graphics context to draw into, the left value source, the right value source, and the label to display. So let's start an empty lambda that has all of that. We'll put that right here. Here's where we're calling draw ticks, draw meter, all this stuff. Let's get these guys and get them lined up. All right, here's our rectangle, our graphics context, our left source. This is the atomic, and then here's the text we want to display. Okay, I want this meter to have a green border around it, and that is easily accomplished by drawing a regular rectangle and then shrinking that rectangle for every other call that uses that rectangle. So g.setColor, JUCE colors green. All right, g.drawRect, rectangle, then rect.reduce. Let me change this so it actually helps me out. It's going to be JUCE rectangle int. This is going to be a JUCE graphics, and these are going to be the JUCE atomic. By doing so, I actually get I can actually get the autocomplete to help me out with like what member functions to use and not just guess what to use. And then for the label, that's just text. So this is a JUCE string. All right. Let's add our label, g.setColor, JUCE colors, white. Let's hide this. g.drawText, and which text do we want? Our rectangle and justification centered. All right, label. This is going to be rect.remove from bottom, and this is going to be our font height. So we've got our big rectangle with the meter. We're going to chop off a chunk on the bottom to fit this label, and it's going to be centered in that. So JUCE justification centered. Awesome. Okay. Let's make a little gap at the top of the bounding box being used by the call to draw ticks so that the +12 isn't cut off. Rect.remove from top. Let's go font height divided by 2. All right, here's our little gap. Now, like we did before, we need to make a copy of the rectangle, defining the meter bounds before you chop that rectangle in half. That's this part here. So go auto, const auto meter area equals the rectangle. Then we can do our chopping, the remove from left and remove from right. Const auto left chan equals rect.remove from left, meter chan width. Again for the right side, meter chan width. All right, and now we can call fill meter for the 2 sources and then draw the ticks on top of all of that. So fill meter, this is going to be the left chan with the left source, and fill meter again with the right chan and the right source. And then we can draw our ticks. Draw ticks over the meter area with our left chan dot get right edge and then the right chan dot get x. All right, let's make a little note of what this lambda does. This lambda draws, oh, did I spell that wrong? I did. Lambda draws the label, then computes the rectangles that form individual channel. Then it draws the meters for each computed rectangle. Then it draws the tick. All right, cool. Let's revise our code that paints the meters and refactor accordingly. So we've got our pre-meter area bounds from left and our post-meter area. And we can get rid of all this stuff here. and instead just call draw meter with our pre-meter area, graphics context. Left source is going to be audio processor dot left pre-RMS. The right source is going to be audio processor dot right pre-RMS, and our label is going to be in, looking clean. Then do it again, draw meter. You put these all in their own line. Okay, our rectangle is going to be the post meter area. Our graphics context is going to be the G. Our left source is going to be the audio processor post left post, and then our right source is going to be the audio processor right post, and our label is going to be out. Input signal and output signal. Let's see how that looks. Should look better. Nice. Our text is no longer cut off because of that gap that we put on either side, plus the gap that we put on the bottom to make room for the label. We press play. That looks awesome. Okay. I really like the way that looks. Let's quit and save. All right. If your plugin looked like that, then mark this to do as done. Let's go to plugin processor. That was the metering one. That is now. All right, let's make a commit. That was a huge undertaking. Probably the longest chapter in this whole course. Implemented GUI metering. Commit 4 files. All right, in the next chapter, we will fix a few issues and eliminate some unneeded GUI rebuilds. More stuff to fix, always stuff to tackle. All right, see you in the next chapter. In this chapter, we will fix a couple of issues with the plugin's drag behavior. First is the following to do. Okay, mouse down on tab during drag should change the DSP GUI. Let's demo this issue. Okay, I'm going to switch to the chorus. Pay attention to what happens when I click on the general filter. Okay, I'm currently showing the chorus controls, and then when I start dragging the gen filter, it doesn't switch to the general filter control. Let's go fix that. It's not until I release the mouse that it does that. Okay, the cause of this issue is that the callback that rebuilds the GUI is not being called in the mouse down. That callback that refreshes the GUI is only called from calls to set current tab. So let's try calling set current tab index prior to the call of start dragging. Add the following code to do this. We're going to get our tabs. We're going to find the index of the tab button being dragged, and then we're going to the current tab index to that. And I know we have a function up here called find dragged item index, but it requires a drag source details object. And we don't have that, we just have, so that's why we're not using that to do this. Okay, let's test it out. It should solve that problem. All right, I'm currently showing the general filter. If I click on the chorus and start dragging, same for phase. All right, so that solves that problem. The GUI is now always showing the correct controls for the tab that's being dragged. Now, while I was testing out this fix when I wrote the tutorial, I found another issue. Take a look at what happens to the tabs when they're dragged all the way to the right and back. Past the gen filter, and when we go back, switch places with the gen filter until I get past the ladder filter. Do that one more time. Go past the chorus, go past ladder filter with the chorus, and go back past the gen filter. Gen filter should switch to the right, and it doesn't switch till we go past the midpoint of the ladder. Let's dig in for an explanation. While I was digging for the solution to this bug, what I discovered was that the array returned from get tabs, go over to that. This array sometimes did not match the actual order of the tabs displayed on the screen when dragging the tabs. In the array class, there is a function called sort. The sort function needs a default comparator element. So, adding a comparator class that implements the interface described in the array sort function. It's the array. Here it is right here. This will use a comparator object to sort the elements into order. The object must have the method of the form int compare elements, and it must return negative value less than 0 if the first comes before the second, a value of 0 if the two objects are equivalent, and a value greater than 0 if the second comes with performance. The compare element method can be declared as static or. So that's what we're going to build. In our case, the array elements need to be sorted based on their X position. We're going to do that in our comparator class. Sorting this tabs array seems to solve this issue. So let's build that now right above the get tabs. Let's copy this comment in here just so we have it. It's static. And we're going to be sorting our JUCE tab bar second. Let's follow these steps. Value less than 0 if the first comes before the second. We're comparing X values, so first less than. If they're equal, return 0. Now let's use this guy. We can do comparator. Now, if you want to test this out to make sure it's actually doing something, you can go auto unsorted equals tabs. And after you do the sort, see if it actually changed. Tabs does not equal unsorted. And this should fire when we drag the tab all the way to the right and then drag it all the way to the left. So if this JAssert gets hit, that is what are confirming. If this gets hit, it means the tab order, right? So it triggered the JAssert, so we know that the tab order, the unsorted tab order did not match what was on. And by sorting it, now it tested again, and that weird drag behavior should be gone. Bug fixed. Awesome. Save and quit. Cool. Let's get rid of this. We don't need that to appear anymore. MS : and then also, if you still have debug tab movement turned on, be sure to turn that off. You don't need that anymore. The whole point is just to clean up the console output. Let's make a commit of that. Issue with selected tab sometimes not causing the next issue is that the selected tab attachment is firing before the GUI is rebuilt. Now, unfortunately, I did not leave myself an explanation of what the problem was that this particular commit is addressing. And as I'm looking at where this change was made and noticing that it was made way back on May 13th, 2023, compared to the date that this chapter was written, which was 28th, 2023, my hunch as to why this change was needed has to do with the callback. That has to do with this callback right here. That is called whenever the parameter value changes. In this callback, this thing right here, the selected tab changed. And then the callbacks that are fired when this function is called, editor selected tab changed, this thing here, this callback is potentially called. We don't know if it will be. It really depends on what happens inside of or inside of that other thing that changes the tab. Either way, it might cause the GUI to be rebuilt. And regardless of what happens when the attachment has its value changed, at some point I decided that calling this rebuild interface function before setting the value was the correct code change to make. So just move rebuild interface before, set value as complete gesture. And then try dragging all the tabs around, and the GUI should always show the correct controls for whichever tab is selected. Make sure of that. All right, so overdrive is always shown whenever it's dragged. LadderFilter, chorus, all seems to be working as expected. All right, this is one of those instances where I wish I had taken better notes, so I would have written down what was the actual bug that was being experienced. What's the problem? What is the solution? Why does the solution solve the problem? Having those three pieces of information would have made understanding why moving this line there makes sense. To this day, I'm still like, I don't know why that actually fixes it, because I don't really know. I didn't do a good job of documenting what the actual problem was. Either way, let's make a commit of that. Fixed issue with selected tab attachment firing before GUI is rebuilt. All right, commit that. All right, the next issue to tackle is an optimization. If our params didn't change, then there's no need to rebuild the GUI. Rebuilding the GUI is an expensive operation. Let's go close this down. Let's go look at that. Rebuild interface. A lot of stuff happens in here. All of the sliders and combo boxes and buttons are constructed. They're added to the GUI, and then all of the parameter attachments are also created. And we want to avoid doing all of that work if we can. So rebuild interface is called whenever the selected tab changes. And let's go to that selected tab changed callback. This guy right here. The selected tab changed callback is always called whenever you click on a tab, and that means every tab click causes all of that work to be performed. That is unnecessary work, and we want to prevent that. So the simplest way to know if the param vector has changed is to store a cached copy of it over here. The simplest way to know if the params have changed is to store a cached copy of this and then just compare it with the new one. let's make a copy of this. Let's add it, plugin editor.h. Go to our button attachments. We're going to stick it underneath it. We're going to call it current params. All right, and then there's no need to initialize this vector either. When the DSP GUI is constructed, this vector is going to have a size of 0. When rebuild interface is called, the vector of params passed in will always have a different size. So now we just need to check if the param vector passed to rebuild interface is the same as the params in this vector. So if params equals current params, they're the same, so the interface did not change, and therefore it should not be changed. Debug interface didn't change. We don't have space. Let's get out of there. Otherwise, we need to update current params and rebuild the interface. So debug interface changed. Current params equals params. And then we do all the other stuff. All right. Here's how we can test this. Let's click on a tab and then click on that same tab again. Let's click on ladder filter. All right. Interface didn't change. Let's switch to chorus. All right, so it says interface changed, item drag enter, then mouse release, interface didn't change. Awesome, so that's working as expected. Now notice that clicking on the same tab still calls all of the mouse down, item drag enter, and then item dropped code when you release the mouse. We can't disable any of that stuff, but our change prevents all of this code here from running, and that is going to make the plugin be more responsive to the end user. Let's make a commit of that. And our commit message is GUI is not rebuilt if params didn't. Let's mark that to do as done. That's the mouse down on tab during drag should change the GUI. Awesome. All right, let's commit that. Cleared to do. Okay, in the next chapter, we are going to make the bypass buttons move to the tab directly. We're going to do this button right on the tab itself. This is going to allow the effect to be bypassed without having to click on the tab to show the GUI where the bypass buttons are currently located. As an example, let's say you've got the phaser running and you got the chorus turned on and you're trying to tweak the chorus, but the phaser is making it really hard to hear what the chorus is doing. So when we make this change, you will be able to bypass the phaser like this. You'll be able to bypass the phaser just by clicking that button. You're not going to have to actually you can be on the chorus tab and you can bypass the phaser just like that. You won't need to be on the chorus tab and then be like, you know what, I hate this phaser, let me go turn that off button. You won't have to do that. Right there. That's going to make the user experience a lot better and more efficient. Save time for the end user. All right, let's do that in the next issue, the next chapter. In this chapter, we will improve the user interface by making it possible to bypass an effect that is not shown on the DSP GUI. Let's get started. Now, all of the changes we will make for this chapter will take place in plugineditor.cpp. In the simple multi-band compressor project, there is a nice power button in the upper right-hand corner that was used to toggle the plugin's bypass state. I want to use that same power button here on each of the tabs. So we need to customize this power button class so that they can be attached to an audio parameter. Our first step is to include the header file that contains this power button class. Let's go over here. Let's close our project down. All right. Add the following to the top where the other header files are included. We need we already got utilities, so now we just need custom buttons. Include custom. All right, let's do a little build just to make sure that that actually works. So it searches it correctly. Build succeeded. Okay, good times. All right, the tab bar button class supports having an optional component placed next to the tab name. Let's go look at that. Let's go look at that. Tab bar button. To definition. Set extra component. Sets an extra component that will be shown in the tab. This optional component will be positioned inside the tab, either to the left or right of the text. You could use this to implement things like a close button or a graphical status indicator. If a non-null component is passed in, the tabbed button bar will take ownership of it and delete it when required. Okay, so this is what we will make use of. The only thing we need to remember is who is going to own the component we will. Let's make a customized power button. The power button from the simple multiband comp does not support an audio parameter. I want this bypass button to be self-contained, so we will create a power button with param class that inherits from power button and has an attachment member variable. So, sorry, above, yeah, create tab button. Above this, we're going to add a class. It's going to be struct power button with param. It's going to inherit from power button. Okay, it's going to need a constructor that takes the parameter power button with param. We need a JUCE ranged audio parameter pointer. We're going to need a void change attachment function, ranged audio parameter p, and then we want to have an attachment as a private member. And remember, these always got to be heap allocated because we can't create them until we know what the parameter is, which means we got to delay the construction order to be within the constructor. So unique pointer, JUCE button parameter attachment. Okay, let's add some implementations after the class and before the create tab button. We're defining these outside of the class. Same for right here. Okay, first of all, the constructor is just going to call our change attachment function. So let's make sure we don't have a null pointer, not equal null pointer, and call change attachment. Now, finally, the change attachment function is going to reset the attachment and then create it, and then send the initial update. And also, we will be checking if the pointer is valid or not, because even though we're calling it from this constructor, this is still a public function that we can call from elsewhere. So attachment.reset, not equal null pointer. Attachment std make union button parameter attachment, our closing angle bracket for the template. Clear this out, semicolon. Now our parameter is going to be that pointer dereferenced, and then the button is going to be ourself as a reference. Then we can send our initial update. Attachment, send initial update. All right. Next, we need to stop creating buttons for the bypass parameter in DSP GUI rebuild interface. Let's go look at that. Rebuild interface. Right here, we are not going to make these buttons. All right, so let's comment this out. Let's just add a message to ourselves. Debug DSP GUI rebuild interface, skipping a PVTS button attachment or audio param bool. This guy right here, p get name. Okay, now for the tricky part, how do we add bypass buttons to the tabs themselves? Tabs are currently created based off of the DSP option, and I don't want to modify the implementation that creates the tab itself. Where am I talking about? I'm currently talking about in that create tab button. This right here, this is where we create that stuff. I don't want to modify this implementation right here. And doing so would be fairly complex because we would need to look up the bypass parameter using the DSP option. And looking up the bypass parameter would require access to the audio processor instance. And that's just a lot. Okay, I don't want to modify the tabbed button bar class to have access to it. So instead, I'm going to add the bypass button to the tab after the tab has been created and added to the tabbed component in editor, add tabs from DSP. I'm going to do it down here. Okay, the editor has access to the audio processor, so that works out in our favor. And let me copy this comment over, which explains the algorithm we are going to be using. All right, we're going to put that right here. Bypass buttons are added to the tabs after they have been created and added to the tabbed component. The mechanism is kind of ugly. The DSP order is used to retrieve the params for a DSP option. Then the params are searched. We are looking for an audio parameter bool instance. Then the found audio parameter bool is checked to see if the param name contains bypass. If those two conditions are met, the bypass param has been found. Now the button can be created, configured, and added to the tab as an extra component. So first, we need to get the number of tabs. Auto num tabs equals tabbed component get num tabs. Next, the power button we are adding needs to have its size set. In order for the power button to appear as a circle, it must use the same size for its width and height. So we're going to use the height of the tab component to provide that width and height. Auto size equals tabbed component dot get height. Now we need to do the following. loop through the tabs, get one of the tabs, get the vector of parameters for that tab's option, search that vector of parameters for the bypass param, and if you find it, create the button, set the button size, add the button to the left side of the tab, passing ownership of the button to the tab. All right. Now, since we are creating something on the heap, we don't want any raw new keywords being used. This means we must use make unique to create a unique pointer to own the heap allocated power button with param. And then in order to pass the button pointer to the tab, we must release the pointer. And it's smart to use unique pointer in this way because it contains exception handling code in the rare, extremely rare situation that the heap allocation process fails. The internal unique pointer code makes sure the heap allocated memory is released correctly and safely and doesn't become a leak. I talked about that in an earlier chapter. Here is what that is going to look like. All right, so first we get a tab, and this returns pointers. So if our tab is not null pointer, then we can get the order for that tab, and then we can retrieve the params for that tab. And then we can search through those tabs to see if we have a bool one that contains, so see if we have a bool parameter. It's a bypass candidate. And if that bypass candidate param has the word bypass in its name, ignoring the case, because I don't remember if I used capitals or lowercase, if we did, then now we can make our power button with that bypass param. We can set our size of that button, and then we can set the extra component and tell it, place it before the text, and then give up ownership of it as well. Let's test this out. We should see bypass buttons next to the tab name. All right, there they are. Awesome. We can click on them and they work as expected so far. Let me set this up so we can run some audio through it. We can have the LadderFilter tab open. We'll turn on the phaser, make it super annoying to listen to, and then go back to LadderFilter tab and then toggle the phaser that way. That'll be our test. All right, quit. Well, let me do that now. Okay, this is wired up to the outputs now. As we said in the example, we're gonna leave it on LadderFilter. Well, no, I'm gonna turn on the phaser, make it pretty annoying to listen to, and then on the LadderFilter, we'll display the LadderFilter and then bypass. It's got some music going. All right, okay, let's set our phaser mix pretty high, 100%. Let's set our phaser depth. There's some feedback. Okay, that's pretty annoying to listen to. All right, so we can be on the LadderFilter page, and then we can bypass the phaser and not hear the effect of it. That's why that feature is useful. Okay, good times. All right. Okay. If you run audio through your plugin and you toggle those buttons, and the effect controlled by that tab should be bypassed. Let's plugin processor, add bypass buttons to the tab. Bypass buttons are now shown on tabs directly. Awesome. All right, in the next chapter, we will replace the combo boxes with sliders, and we will make the selected tab visually different from the unselected tab. Let's get into it. In this chapter, we will replace the combo boxes with sliders and also make the selected tab more visually apparent compared with the other tabs. Now, originally, the to-do said we would replace the generic JUCE combo box with the slider multiband comp combo box. However, the simple multiband comp did not use combo boxes. It uses sliders for the choice params. So that is what we will do in this plugin as well. Now, replacing the combo box with sliders is extremely easy. All we need to do is eliminate the if block, this stuff right here. We just need to eliminate this if block that handles choice params. And that leaves the logic here as follows. If it's a bool param, then debug skipping button attachments. Else, sliders are now used for float and choice params. Sliders are used for float and choice params. Super simple. So we just need to say if it's a choice, just don't do that anymore. We can just literally get rid of that. And then for here, we can literally just copy this and put it here. And then instead of if it's a bool param, we can just say if dynamic cast bool. If it's this is our it's a bool param. If it's this, then it's that. Let's get rid of all this code. If false. This makes this way simpler. Okay, run and test that. All right, ladder filter mode is now a slider. Are there any other sliders? Let's see, I think overdrive. No, ladder filter, general filter. Cool, that was super simple. Let's mark that to do as done and make a commit. Commit that. Replaced combo with sliders for choice params. Next, we will modify the selected tab to have a distinct color so it's easier to tell which tab is selected. Let's go to our tab creation. So that's where the magic's. In order to change the color of the selected tab, a few things need to be investigated. Number one, how is the button painted? And then number two, where is the color set? Now, number one is answered by looking in JUCE tabbed button bar and looking for the paint function. So let's go to the CPP. Let's go to the paint function, tab bar button. We want tabbed button bar, or tab bar button paint function. Paint button, I think that's the one we want. Tabbed bar button paint does not exist. Instead, there's a paint button function. And internally, this function uses a look and feel to draw the button. So now we can investigate the look and feel function to see how the button is painted and filled with whatever color it is filled in with. Let's go to that draw tab button implementation. We get a few choices. We probably want version 3. And this is where we get color background equals button get tab background color. This lets us begin to answer question number 2. Where is this color set? And here are the steps to answer that and see how we can leverage this value. Figure out where the color being used to paint was being set, and the answer is in the add tab function. So let's go look for that. Add tab. Right here. Tabbed component add tab. JUCE color white. Let's go look inside that implementation. We want tab background color. We want to see where that gets used. That's right here. Tab background color. All right, and this is stored inside of this tab info. So now we need to figure out how to change that color. And that is going to be tab button bar, because we're going to look for where is this new tab color. Let's go look for that. We just want to look for find this in a few places in the code base. Here's how we get the tab background color, and then here's how we set the tab background color. All right. Now we need to figure out if changing that color during the mouse down event would suffice. And the answer is yes. Mouse events cause the tab to repaint itself. And then figure out why that color isn't shown when the plugin first launches. And then the answer is the color is only changed when the mouse down occurs, and the solution is to refactor code that changes color into a function and call it during mouse down and when the tabs are created. So let's do that. Let's declare a function in tab button bar, in our extended tab button bar. Let's declare a tab in this called set tab colors. Void set tab. Apparently I'm using the British spelling of color. And we're going to implement this before the power button with param definition. Go find that right here. Here's the logic. Number one, loop through all the tabs. And then for each tab, if the tab is the front tab, pick a blue color. Otherwise, pick a dark gray color. Set the tab background color for that tab with our preferred color, and then repaint that tab. All right, so I'm going to add a comment here explaining this process, just so it's in the code base for later, because it was pretty complex to figure it out when I did it. It's going to look really simple now when we actually implement it and use it, but it's good to have that historical context. Okay, with this background information in place, let's build this function, void extended tab button bar, set tab colors. Okay, as we said, we're going to loop through all the tabs. Auto tabs equals get tabs. For each tab, int I equals 0, I is less than. Auto color equals If it's the front tab, it's going to be sky blue. Otherwise, it's going to be dark gray. Tabs. Is it the front tab? Yes or no? Yes, it is. So it's JUCE colors sky blue. Otherwise, no, it's not. So JUCE colors dark gray. And then let's set that tab's color. Set tab background color. Index I. And the new color is going to be color. Now that that has been set, let us repaint that tab. Tabs, repaint. Cool. Now we need to call this member function in two different places. Number one, in the mouse down function. We do this after we set the tab index. And then again, prior to rebuilding the interface in the editor, add tabs from DSP order. Okay. After we, right before we rebuild our interface, that's here. Right before we do that, we want to set our tab colors. Tabbed component. All right, now let's build and test that. And it should be much more obvious what color our tabs have, the selected tab versus the. All right, whoa, look at that. That is way better. Okay, awesome. Let's clear the to-do in plugin processor. Make selected tab more obvious. Done. Now there is an issue. Look at this. The issue is when we drag a tab over a bypass button, you see this little glitchy thing that's happening where it like kind of, okay, let's add a to-do for that. To-do, fix graphic issue when dragging tab over bypass button. We'll tackle that soon. Let's make a commit, all this stuff. And our commit message is selected tab is now visually different from unselected tabs, as well as added to-do. All right, in the next chapter, we are going to implement input and output gain. In this chapter, we will implement input and output gain and add the necessary GUI controls. Input and output gain is pretty simple to add. We need audio parameters, cached parameters, smoothers, DSP gain instances. We need to initialize the cached parameters. We've got to update the smoothers, update the DSP gain. Then we need to apply the DSP gain. We need to give the GUI some sliders. We got to make room for the GUI. We got to make room for those sliders on the GUI. Then we got to add attachments for those sliders. So let's tackle each one at a time. Head over to pluginprocessor.cpp. Go to the top. We're going to add names to generate the IO names. This is at the end of our name list after selected tab. Auto get input gain name string input gain d, and do it again for the output gain db. Cool. All right. Next, prior to the Phaser Param creation, let's create two audio parameters for these two gain settings. We're just going to work our way down the CPP file. Just bang all this stuff out. All right. Create audio parameter, create param layout. Let's do this prior to the Phaser creation. So we'll change this to be name right here, and we'll do auto name equals get input name gain, get input gain name. Then we'll do our layout.add. We're adding an audio parameter float. This is going to be, let's see, we're using a range of -18 to +18 and a step size of 0.1. We'll have a default value of 0 and a unit of dB. Okay, that takes care of that. Let's do the exact same thing for output. Duplicate this and change this to be out. That takes care of the audio parameters. Let's go to pluginprocessor.h and declare two audio parameter floats. These right at the top, and name them input gain and output gain. Okay. Now we got to add some smoothers. You know, let's actually move these to the very end. These way down here after selected tab. All right, let's add some smoothers for those. After the general filter gain smoother, we'll go input gain smoother, then output gain smoother. Okay. And then finally, we need to add two instances of the DSP gain object before the DSP choice class. Gain of type float, and this is going to be input gain DSP. All right, that takes care of the audio side of things that need to be declared. Let's initialize our cached params next. Go back to your constructor, and then let's look for where we initialize the float params. General filter gain, let's do these guys here. Gain, output gain. Float name functions, put these down here at the end. Input gain name, and then get output gain name. Okay, that takes care of initializing the cached params. Let's go prepare our DSP instances now. Go to prepare to play. The gain units can process stereo audio. So this line right here, we need to do this after we prepare these guys. So first let's set this spec.num channels equals get total num input channels like that. And now we can prepare our gain modules, input DSP dot prepare and output prepare. All right, spec.num channels then gets assigned to 1. That takes care of preparing the gain instances. And actually, I don't like this change where we're doing this. So we're gonna just move this down to be after we update our smoothers. So it's a smaller change. Okay, let's make sure the smoothers are prepared. Let's go to our get smoothers function. Here we are, get smoothers. And let's add our input and output gain smoothers. Input gain smoother, output gain smoother. All right. And then we want to make sure the update smoothers from params function has the correct list of parameters that need smoothing. So this is where we add our input gain and our output gain. We got to make sure that that list order matches here. We got input coming before output, list input before output. Okay, cool. That was super easy. Next, we need to update the DSP that makes use of the gain effects. So let's head over to process block. This block. Okay, here it is. Now, we need to move the block creation. That's this part right here. This needs to be done before the pre-RMS level computation. We have to do 5 things here. Okay, number 1, we got to move block creation to before the pre-RMS level computation. We need to create a pre-context. We need to set the target value for both the input and output smoothers. Then we need to set the input gain decibel level from the smoother. And then we need to process the input gain using the pre-context. That, let's see, what does that look like? And all this happens before any of this stuff here. Okay, so let's move this block up. This over here. All right, that goes there. All right, let's make our pre-context auto pre ctx equals JUCE DSP process context replacing. Uses a float, and it's going to take our block. Let's set our target values for our smoothers. Input gain smoother dot set target value. This is going to be input gain. Do the same for the output. Output gain smoother. Set target value. Output gain. All right, now we need to set our input gain decibels. This is going to be input gain DSP dot set gain decibels because the parameter itself is being stored in decibel format. Now we can go input gain smoother dot get next value. Then we can do our processing input gain DSP dot process with the pre-context. Okay, that takes care of that. All right, now it's time to process the output gain. Let's do the following before computing the post RMS levels. We need to create a post context. We need to set the output gain decibel level from the output gain smoother, and then we need to process the output. So let's create our context. Auto post ctx equals JUCE DSP. Process context replacing. This is a float, and we're using our block again. Let's set our decibels. Output gain DSP.set gain. This is coming from our smoother. Output smoother. Get next value. And then we can do our gain processing. All right, awesome. That takes care of the DSP side of the input and output gain. Let's switch over to the GUI. Plugin editor.h. Right. In the editor, we need 2 sliders, 2 attachments, and a constant to define the IO control size. So during the process of adding these controls to the GUI, I did all of my size refinements in resized, and I ended up with a preferred size of 100 for these sliders. So feel free to mess around with this value when you come up with your I/O gain slider positioning. Let's declare a constant near our tick indent. Static const expr int I/O control size equals 100. All right. And then let's declare 2 sliders and 2 attachments. And these are going to be rotary slider with labels and slider attachments, like that. Okay, we've got our rotary slider with labels as a unique pointer and our in-gain control and out-gain control. Here's our unique pointer holding a slider parameter attachment called in-gain attachment and out-gain attachment. Okay, now our constructor's job is to create the sliders, add them to the GUI, add label pairs, create attachments, and make room for them in the editor. All right, so let's go to our constructor in the CPP file. That's here. All right, we are going to do this after the DSP GUI is added. All right, let's make our rotary slider with labels. These guys here. All right, it's going to use the input gain for the in-gain control, a unit of decibels with a name of in. Let's make them visible now. Let's add our label pairs. Okay, so we're updating the in-gain control labels with the in-gain parameter and using decibels. Doing the same thing for the out-gain control and the output gain parameter. Finally, let's make our attachments. All right, so we're making our slider parameter attachment using the input gain and the input gain control. Same for the output gain and the output gain control. All right, let's make the GUI a little bit taller. This is going to be 400 plus, you know what, we'll make it even taller than that. 450 plus I/O control size. All right, so the GUI's got a little bit more room. Let's head over to the paint function. And we need to make room at the bottom of the editor for these controls because the meters are going to sit on top of the controls. Let's go to where we get our bounding box. It's right here. Auto bounds equals get local bounds. Bounds.remove from bottom I/O control size. Okay, so now all the meter drawing is happening above the area that we made room for on the bottom. All right, let's go to the resized function. And we're going to do a similar thing as well. Editor resized. Okay. Auto bounds equals get local bounds. We got rid of our remove from top 10. All right, so let's do auto gain area equals bounds.remove from bottom I/O control size. Now we can do in gain control, set bounds, gain area, remove from left I/O control size. And do the same thing for the out gain control. Gain control, set bounds, dot remove from right I/O control size. All right, let's test it and run it out. Let's test it out. We should be able to use these. And when we do our tweaks, we should, let's see, I'm going to get rid of these because I don't want to hear this. We should be able to actually see the overage thing happening. Move this up here. Let's get some audio playing back. Let's boost our input. Look at that. We get our red box, our red boxes, red rectangles showing that. Double click it to reset it. Pull our output down. Let's boost our output. All right, fantastic. So we actually didn't have a to-do for this. Let's save and quit this. Let's make one. Make a to-do for this. We've got our add smoothers. Let's just add it right here below that. To-do I/O in out gain controls. All right, so we've got our to-do for that. All right, let's commit all of these changes. Although there's one thing that I'm not sure about, and that is how are we making sure that these smoothers, they're getting their target value set, but how are they actually being advanced? Where does that happen? Is that an artifact that's happening? Left channel update DSP from params. Where am I updating my smoothers? Where am I advancing my smoothers? I'm advancing my smoothers. Update smoothers from params. Right here. Okay, cool. All right. So that was the only thing I was a little concerned about, was that we are pulling a value out of our smoother here, but we're not advancing it anywhere in process block. And that is because we're actually advancing them inside of this loop here. Okay, so that is a non-issue. Yeah, we're actually advancing each smoother right here. It just so happens that the gain smoothers, their value is being pulled not here, but actually from, and if we wanted to, we could say, you know what, we could be applying our gain here and adjusting our stuff that way. But we're just applying gain outside of this loop. Gain gets applied in blocks of whatever size process block is currently handling. We're not breaking it down into chunks of 64 samples at a time. That's fine. All right, let's make a commit of this implemented IO gain. Commit 5 files. All right, awesome. In the next chapter, we are going to fix some more drag to reorder issues, as well as make some to-dos. And yeah, we're getting pretty close to the end. We're on chapter 37. We're going to hit chapter 38, and then 39, and then 40. And that's going to be the end of the tutorial.
Hey, if you like this tutorial that you've been following along with and have been wishing for a written version, check out the link below. You'll find this course as well as my other courses, all available in written format. They're full of detailed explanations, code snippets, and more. Each chapter is crafted to be easy to read and easy to follow. Complex features and ideas are turned into simple concepts with clear code snippets. You'll progress quickly as you elevate your app and plugin making skills by working through these projects. Programming isn't hard, it's just taught wrong. All right, let's get back to making this plugin.
In this chapter, we will fix the drag to reorder issues once and for all. The drag to reorder logic is fairly complex. We are going to make it bulletproof in this chapter. Let's dive into fixing drag to reorder. The previous system for switching the tab order didn't work completely. Now, I'm talking about this stuff here. This is a revision that works correctly, and it depends on a separate array existing that takes a snapshot of the tab order prior to the drag events starting. Here's how it works. In the mouse down function, it's going to take a snapshot of the tab order updating the extended tabs button bar tabs array. The item drag move, let's go to that, reorders this array and repositions the tabs manually. Then the item dropped function is where the calls to move tab actually occur, and move tab updates the tab button bar internal list of tabs. New rules are also used to govern how the tab swapping occurs, which means that all this stuff, all these rules right here, are going to change. All right, these rules are going to focus on the transition from one side of the adjacent tab to the other. This new approach requires storing the previous position of the tab being dragged. From there, the usual sequence of callbacks are called when the move tab function is called. So in plugin editor.h, let's go to after our list of listeners. Let's add a JUCE array of tab bar button pointers after the listener list for holding the tabs, and a JUCE point instance. It's going to store the previous center position of the tab being dragged. Dragged tab. The member name tabs is being used in get tabs. So let's go to that function, go to get tabs. So this right here, this is a conflict. All right, so in order to avoid a compiler warning about overshadowed member variables, let's rename this thing here to be called internal tabs. We're also not going to need the comparator to sort. Next, we need to populate this tabs array. So in the mouse down function, change this line auto tabs equals get tabs to just be tabs equals get tabs. Now we're messing with the tabs right here. We're messing with the actual snapshot. Okay. This takes the snapshot and populates the member variable with the tabs prior to the code that handles the mouse moves. Now we can begin updating item drag move. The first line to change is getting the IDX right here. Let's use our member variable tabs as the array to search within. Let's get rid of this line. We're going to say tabs.index of, we're looking for our tab button being dragged. Okay. All right, and I'm going to insert a comment here that kind of explains the process as well. All right, here's our explanation that we said earlier. Previous system didn't work completely, depends on a separate array now, uses new rules. Here's how it's going to work. Mouse down takes a snapshot. Item drag move reorders this array and repositions, and then item dropped is where the calls to move tab will actually occur. Here are the new rules for how the tab movement should be handled. If the center of the dragged tab transitions from to the left of next tab.x to either to the right side, if it transitions from the left side of the tab to the right side, then we want to swap these guys. This handles dragging the tab from left to right. And then if the center of the dragged tab transitions from to the right of the previous tab's right edge to the left side of the previous tab's right edge, meaning does the tab go from right to left, my right, this is my right hand, to the left side, then we're going to swap it. This handles dragging the tab from right to left. Okay, now let's go a little bit further. Instead of using get tab button, let's get the previous tab and next tab from this tabs array. So we do tabs.index of. Previous tab equals, oops, my mistake. We're not using index of. We're going to go JUCE is positive and below. Previous tab index. If it's less than tabs.size, then we can do tabs previous tab index. Otherwise, we're doing null pointer. Do the same thing for next tab. JUCE is positive and below. Next tab index. And this is going to be tabs.size. It's going to be tabs. Next tab index. Otherwise, it's null pointer. And then, let's see, where do we get our center X? That's here. Okay, and we can get rid of this. We're not using that anymore. We can get rid of this comment as well. We just go straight to center X. Now we can delete all of the previous logic that handled the previous case positions. Get rid of all this stuff. Goodbye. All right. Now our new logic is going to be like this. If center X is greater than previous drag tab center position dot X, transitioning right, else if center X is less than previous dot X, transitioning left. Okay, now remember we are manually repositioning the next tab or previous tab and then swapping their position in the tabs array. If we are transitioning right, we need to check the following. If next tab is not a null pointer, next tab is not a null pointer. If the previous center X was less than the next tab's left edge and the next tab's left edge is now less than the center X, then we're going to do some stuff. So let's do that check. If previous dragged, let me spell that right. Previous dragged X is less than next tab get X. Oops, that's a pointer. And next tab get X is less than or equal to center X. Now we can. Now we're going to swap next tab with the tab being dragged in the tabs array. So let's add a debug message that says that swapping the IDX or this tab's name with the next tab index. Now we just do tabs.swap. Oh, sorry. First we got to set the bounds of next tab. Next tab, set bounds. Okay. Next tab is going to keep its bounds. We're just going to change the X position. Next tab, get bounds. But we're just changing the X. And the new X is if the previous tab is not null pointer. If the previous tab does exist, then the next tab should move to the right of the previous tab. Otherwise, it should move to the 0th position. So, previous tab not equal null pointer. If previous tab exists, then we want the previous tab Give me the right side of that, plus 1 pixel. Otherwise, go to the 0th position, all the way to the left. How can we make that look a little nicer to read? Let's do set bounds, with X, and then if it's this thing, it's this, otherwise. Okay, and then finally, swap the tabs. Tabs.swap. We are going to swap IDX with, okay, let's tackle transitioning left. The logic is very similar. If previous tab is not null pointer, then if the previous center X was greater than the previous tab's right edge and the current center X is less than the previous tab's right edge, then we get to do stuff like this. All right. So let's add our comment explaining the swap we're going to do. Then let's set our bounding box. So to set the position, if next tab exists, previous tab should move to the left side of next tab. Otherwise, previous tab should move to the last tab position, as in the tab on the furthest to the right. Previous tab set bounds. That's the first thing we're doing. It's going to keep its bounding box. Previous tab get bounds. And we're just changing the X with X. And the X is going to be, if we have no next tab, or if next tab exists, then we're going to be next tab's X position minus the width of the previous tab, and then a little bit left. That looks like this. Next tab not equal null pointer, question mark. If next tab does exist, then it's going to be next tab's X position, and then go backwards, go to the left, previous tabs, and then 1 pixel left. Otherwise, it's going to be the current width of the component itself, of this bar, minus previous tab's width minus 1. And now we can swap these positions as well. Okay, fairly complex. We just got to remember that we're moving a rectangle, a little rectangle. If we got a tab here and we're moving it over here, then this tab goes where that one was. So we just need to move the X position around based on the width of this and the X position. I got to remember that I'm showing you all these reversed, not from my perspective, that sort of thing. I might flip these videos in post to make it look proper. Sure. All right. The last thing to do is to update the previous dragged tab center position with the dragged tab center. So after we switch to the front, then we need to go previous tab drag position equals tab button being dragged, get bounds, get center. All right, in the tutorial, there is a snippet showing the fully revised source code. I'm gonna copy that in here for the full function. Hopefully there aren't any major changes. It should be identical to what we've done. So a little bit of formatting. Let's see, what is the actual change? Oh, the position of the, all right, that's fine. What about this one? Pretty sure this is all the same. Okay. All right, this takes care of moving the tabs to the correct position on screen, but it does not update the internal array in the extended tabbed button bar class that owns the tabs and ultimately controls where the buttons get positioned. We need to do that next. We handle that in the item dropped function. So let's declare a function called reorder tabs after drop. Let's go to where our scaled image is handled, after our get tabs. Bool reorder tabs after. Okay, this function needs to return a bool because we need to know if the tabs were reordered or not. If they were not, we still need to lock the position of the tab that was dragged to the correct position because it is possible to drop that tab anywhere within the tabbed component. Here's the job of this function. Let's go back over here. This function needs to put the tabs in the same order that the tabs array has them in. There are 2 ways to reorder tabs in the tabbed button bar class. Number 1, delete all the tabs and recreate them in the correct order. To do this, I would need to create a list of the tab names and then clear the existing tabs and then create new tabs. This is expensive and not ideal. And the second way is to just call move tab with the updated indices. We're going to do the second option. We'll use this function in the item dropped function to make sure our tabs are in the correct order. First, we assume that the tabs have not changed, and we do that in this function by declaring a Boolean that we're going to return at the end. Let's just put that right here. Extended tabbed button bar, reorder tabs after drop. bool tab order changed equals false. Now, I found it useful when working on this to print out the starting tab order when figuring out how to make this function do the correct thing. So I'm going to add that in here. Define debug tab order true, and then if order, and if. We're going to go, we're just going to print this out. Debug starting tab order is this, followed by for auto t tabs, and let's just print out the name with some indentation, t get name. Next, we will be comparing the internal tabs array with our tabs array until they match. If the elements are not in the same order, the tabs array has the final say on whether a given tab should be placed in the internal array. We'll check each index one at a time. To do this, I used an infinite while loop with the array comparison at the beginning. While through auto internal tabs equals get tabs, if internal tabs equals tabs. All right, if the arrays don't match, then we loop through the tabs array. For each tab in our tabs array, we do the following. Get the location of that tab in the internal tabs array. If the locations don't match, we call move tab to update the location in the internal array. We set tab order changed to true, and then we break out of the for loop so we can start the while loop over again. The idea is that we move one tab at a time until all tabs are in the correct order. I used the debug tab order macro inside this for loop so that I could confirm that the tabs were actually changing order. Here's what that loop looks like. All right, here's where we get a tab. Here's where we get the index of it. If the index in the internal tabs does not match the index in the index of this tab, then we know that the internal order is weird and we need to switch them around, which means that the tab order has been changed. Here's the end of our while loop. And then finally, we just return our tab order. Let's take care of item dropped now. Item dropped. When the tab is dropped, we need to lock the tab position and then update the internal tabs list. Our resizing needs to be conditional. So let's comment this out. And instead we're going to do, we need to call the reorder tabs after drop function we just wrote, which will reposition the tabs internally if needed. If the tabs weren't reordered, call resized to snap their position. Reorder tabs after drop equals false. And the idea again is, if you didn't reorder the tabs but just dragged the tab, you still need to lock the tab position of the tab that you dropped. And resized will do that for us. As in, if you just drag a tab a little bit like this, and then let go, we got to snap it back to position. That's the behavior we are implementing here. Let's run and test, and let's keep an eye on the console output while we're doing our testing. Move this out of the way. Okay, let's drag our phase. Okay, swapping phase with chorus, swapping phase with overdrive. And pay attention to those indexes, how those are also correct. Okay, and that snaps to the right place. Same with ladder filter, let's just move it there and then let go. Interface didn't change. Starting tab order, chorus, overdrive, ladder filter, phase, gen filter. That's over there. All right, everything works as expected. So now we can drag any tab to any position and the tab order is correct and the GUI shows the correct controls. We can mark some to-dos as complete and quit and go do that. First of all, IO gain is now done. All right, there's that one. Fix graphic issue when dragging tabs over bypass button. That is also done. That was the big side effect of the code we just wrote. And then now we have two more to-dos. Restore selected tab when window opens. And then finally, to-do, bypass button should toggle rotary slider enablement. All right, let's make a commit. Fixed drag to reorder issues added to-do. In the next chapter, we will handle these to-dos that we just added. All right, in this chapter, we are going to fix the display of the selected tab when the plugin launches and also implement toggling the enablement of the sliders when the bypass buttons are toggled. For example, right now, these are still all enabled when this is on and when this is off. They should not be enabled. Okay, so the first item to fix is the display of the selected tab when the plugin window opens. The 0th tab is shown as selected when the plugin window opens. So even though I've got the phaser selected, close this, reopen it, it's still selecting the 0th tab. Let's see, notice that the chorus tab is selected, but the phaser sliders are shown. So we're going to fix that too. Let's go back over here, plugin editor. Let's see, let's go to selected tab changed. I'm sorry, not here, it's the timer. All right. When the plugin first launches, editor selected tab changed is called after the send initial update. That's way down here. This thing is called after the send initial update is fired, which is called whenever the restore DSP Order FIFO has new data, which is what happens when the plugin first launches. Okay. Every time the current tab index changes, we want to refresh the tab colors. Previously, tab colors were changed in only the add tabs from DSP order function and when the tab is clicked. For some reason, add tabs from DSP order wasn't changing the tab color. Calling tabbed component, where do we do that? It's down here. Calling tabbed component set tab colors wasn't changing the color. Calling this line right here, tabbed component set tab colors, after calling rebuild interface inside of editor selected tab changed, ensures that the tab color changes correctly. So now when the plugin is open, the selected tab is always shown with the correct. Okay, we're on Overdrive. Let's switch to the phaser. Save, quit, reopen. We should see the, and there it is. All right. Why is that 0? How many tabs do we have? Well, either way, let's put that on phaser. Save. Let's just close this window, then reopen it. Phaser is selected. Let's switch to LadderFilter. Close this. Open LadderFilter. All right, cool. If we quit and reopen, do we get LadderFilter? We get LadderFilter. All right, good times. All right, fantastic. We'll leave that open. Save and quit. Let's mark this to do as done. This is restore selected tab when Windows opens. So it turns out it was doing that, or maybe not. I don't know. We only made one change to the code. I think it was just a graphical thing. There's the to do. That's the only change that we made. Let's make our commit. Oh, you know what? Let's add our comment that explains why we are adding this code where we are adding it down here. Let's add our comment for that. I think that's important to have. Just throw this in here. When the synth first, let me type it and then I'll read it. Okay, so to recap, here's the issue and here's the solve. When the synth first launches, or when the plugin first launches, this callback is triggered. This callback is triggered from the selected tab attachment send initial update call inside of timer callback. Every time the current tab index changes, we want to refresh the tab colors. Previously, we were changing tab colors from add tabs from DSP order and when the tab is clicked. For some reason, add tabs from DSP order wasn't changing the tab color, and calling it here ensures that the tab color does change. All right, now we've got that comment in there. Make sure that's committed. And there's our fix. Fixed display of selected tab when launching plugin. All right, let's tackle connecting the slider enablement to the bypass button. Here's generally what we need to implement. If the button that was clicked is the same button on the active tab, refresh the slider enablement on the DSP GUI. This means that we need to configure each bypass button's on-click lambda. Let's go to where we make those bypass, but it'll be right here. All right, here are some more details. We can get the active tab by calling tabbed component get current tab index and then tabbed component get tab button with that index. We can then get the extra component by calling tab button get extra component. And if the button that was clicked and the extra component are the same, the sliders shown should have their enablement changed. Finally, there are a few more details to consider when figuring out how to make this work. Number one, the DSP GUI needs to have a mechanism to toggle the slider enablement. And number two, the DSP GUI needs to toggle the enablement whenever it rebuilds itself. Since we're changing the enablement from two places, we should create a member function in the DSP GUI class that does this. So let's go to our DSP GUI class, and let's add this after the rebuild interface function. Void toggle slider enablement. All right, internally this function is going to iterate over every slider, combo box, and button, and just call set enabled. And actually, we don't have any more combo boxes or buttons, but we'll just keep it simple. We'll make that change later. Let's go to where that is, DSP GUI rebuild interface. Copy these guys, put them in a new function, void DSP GUI toggle slider enablement. Now we just loop through this, and then for each of these, we do slider set enabled, CB set enabled, enabled. Same for here. BTN set enabled, enabled. Super simple. Enabled. Save. All right. Next, we need to read the enabled state from the bypass button's parameter. Since the bypass button is already attaching to the param during construction, I'm talking about over here with our bypass button, this thing here, we do this. Okay. Since the bypass button is already attaching to the param during construction, updating the class to also store the param is trivial. The editor is going to be the intermediary between the button onClick lambda and the DSP GUI.toggle slider enablement function. So I chose to write a function in the editor that is past the power button and reads the power button's parameter to get the enablement value. So let's go add the following function at the end of the editor after rebuild interface called void refresh DSP GUI control enablement, and we pass it a power button with param button. Okay, this declaration will produce an error because power button with param does not exist in the header file. Let's move that class over from the CPP. Let's get right here, just grab this. You may need to move the necessary include statements as well. Let's just put that up here, give it our separator. Let's grab our header file that includes that, custom buttons, up at the top for power button. All right, while making this edit, it makes sense to change the constructor argument type to audio parameter bool instead of ranged audio parameter. Audio parameter bool, same for change attachment. First of all, let's store a copy of the param internally. Parameter bool, param. Let's add a getter function as well. Get param const return. All right, next there's going to be a couple of errors related to the power button with param implementations. Let's go to that, this and see those errors. Okay, out of line definition does not match. Audio parameter bool, same for this one. So revise those function signatures accordingly and be sure to update the param member when calling changed attachment. So right here is where we update it. Param equals P. Now we can implement editor refresh DSP GUI control enablement. Go way down to the end of your editor, way down here. Let's add a comment explaining what this is going to do. All right, here's how it's going to work. Number one, if you pass in a valid pointer, and if that button has a valid bypass param, we're going to update the enablement of the DSP GUI child components. And remember, if bypassed is true, then enablement should be false. All right, here's some thought process to go with that. Enabling the bypass buttons to control the slider enablement requires a few steps. Number one, the button onClick must be configured to toggle the GUI slider enablement. Number two, the onClick must only toggle it if the button being clicked is the button in the currently selected tab. Number three, the DSP GUI needs to have a mechanism to toggle slider enablement. Number four, the DSP GUI needs to toggle the enablement whenever it rebuilds itself. So let's dive in. Void project 13 audio processor refresh. Oh, you know what? We didn't declare that. That's important. Go way down to the end. Oh, we did declare it. Why didn't it show up? This thing here. Power button with param is our button. Okay. As we said originally. Oh, why is this complaining? Let's make sure that builds. It's throwing an error message for some reason. Out of line definition does not. What is happening? Oh, because it was audio processor, not processor editor. That's why. It's always something. Always some small detail that gets missed. Okay. If button is not equal null pointer, And if the bypass param is cool, so bypass button is cool, then we can do DSP GUI, toggle slider enablement, bypass, because remember, if bypassed is true, enablement should be false. All right, let us start using this function. In the rebuild interface, if the current tab has an extra component, refresh the DSP GUI with that extra component button. If auto btn equals dynamic cast power button with param ettb get extra component. If we got our button, then refresh the GUI button, refresh the DSP GUI control enablement with that button. We are almost done. We now need to revise how the buttons are created and create the on-click lambda. Let's refactor the search for the bypass param and create a function to do this. And I'm too lazy to figure out the correct type, so we're going to do a templated thing so that the way the compiler can figure it out for me. Let's go way up to the top where we looked for custom buttons. Pull this up here. We're going to use the same logic from the bypass button creation. Go look at that real quick. We do that. Create tab button. Is that where we do that? Where do we do that? That was way down here in tab, or add tabs from DSP order. Right here. We're going to do the same logic here. We're going to iterate through the params vector right here. If you found a bool audio parameter and the name contains bypass, then congrats, you found your bypass param. Let's return it. And return null pointer if you didn't find anything. So we can actually borrow a lot of this code. Header file and make our templated function here. Type name params container and JUCE audio parameter bool pointer find bypass param, and then we need our container. Now we paste this in. Let's get rid of that stuff first of all. All right, looping through all of the parameters. If you found a bool parameter and the bool's name contains bypass, then return it. Otherwise, return null pointer. Okay, now we can use this in the code that creates the bypass button. That's right here. Instead of this loop, we can instead just go if auto bypass equals find bypass param. We create the button, we set the size, and we add it. But now we also define the on-click lambda. This lambda is fairly simple. We compare the current tab with the tab that this button is on. And if they are the same, then we call editor refresh DSP GUI control enablement with this button. So here's how this looks. PBWP on click equals, and then we do our lambda. Lambda, lambda, lambda. First we capture this because we are going to call refresh DSP GUI control enablement. And then we need the button itself. So btn equals pbwp.get. This is getting a copy of the pointer owned by the unique pointer. And now we can say auto idx equals tabbed component get current tab index. And we can say if auto tab button equals tabbed component get tab button. So if we pull a legit one, and if we say if tab button get extra component equals the button that is currently being clicked on, then we can just refresh our DSP GUI control enablement with that button. And let's add a comment to just make it really clear what this, okay, if the button that was clicked is the same button on the active tab, refresh the slider enablement on the DSP GUI. All right, let's test it out. And we will test this out by clicking and on an inactive tab and pay attention to the slider enablements. Uh-oh, we did something wrong. Let's go back and do a clean and rebuild. Okay, rebuild. Oh, my mistake. We have to do this before we release this. That's the other part of it. So easy fix. Just move this set extra component release call after the on click. Just be aware of that gotcha. I'm glad that didn't take hours to fix. Okay. All right, here's how we test this. Let's click the bypass button on an active tab. We see the slider enablements change. Cool, let's do it on a bypass tab and then switch over to that tab and the sliders are disabled. So let's go over to our ladder filter and that's working. Fantastic. All right, let's mark this to do as done. Save and quit. Plugin processor. Bypass button should toggle rotary slider enablement. Done. All right, in the next chapter, we will add the spectrum analyzer. Let's get to it. Oh, let's make a commit first before we do that. Our commit message is going to be implemented bypass buttons toggling the DSP GUI control enablement. All right, in the next chapter, we will add the spectrum analyzer. Let's get to it. All right, welcome to the final chapter of this tutorial. This is the core tutorial of Project 13. There's a ton of bonus content. In this final chapter of the core tutorial, we will add the spectrum analyzer from the simple multiband compressor. Our job here is easier than you might think. I have refactored the spectrum analyzer from simple multiband compressor into modular classes. So all we need to do is include the necessary header files and start using the classes found in them. Let's go over to ProJuicer and add the following source files to the GUI folder, existing files. We're going to add the analyzer path generator, the FFT data generator, the path producer CPP and header file, and then the spectrum analyzer CPP and header file. Now in the DSP group, we need to add the single channel sample FIFO. Save and open in IDE. Okay, plugin processor.h. Up at the top, we need to include the single channel sample FIFO header file. Okay, then we need to declare two instances. Let's go down to where those atomics were declared. All right, simple MB comp. We want single channel. Wait for the autocomplete. Sample FIFO. Our block type is going to be JUCE audio buffer float, and it's going to be called left SF, and it needs a channel parameter, and that's going to be simple MB comp channel. All right, we're going to duplicate this, or not duplicate it. We're going to add another instance called right SCSF, and that takes simple MB comp channel. All right, let's try to build that before we do anything. Make sure we don't have any build errors because we just added several source files. All right, build succeeded, cool. Next, we need to prepare our single channel sample FIFOs and update them. So plugin processor.cpp, prepare to play. After we set our output gain spec, we need to prepare our left and right single channel sample FIFOs. Prepare, buffer size is going to be samples per block. And then right, prepare, samples per, whoops, prepare, no, not prepared, prepare, samples. Okay, in process block, or you process block, we need to update each single channel sample FIFO after computing the post RMS processing. Go way down to the end. After we do the right post RMS, this is where we do left single channel sample FIFO dot update. Do it again for the right channel. Okay, that's it for the DSP side of things. I told you this would be super simple. Plugin editor.h. Let's include the spectrum analyzer. Include spectrum analyzer.h. Now in the editor, declare an instance. Go all the way down to the bottom. Let's do it after our tabbed GUI. Now remember, we must initialize it with the audio processor and the two FIFO instances. Let's take a look at that header file. And here's the constructor. It wants an audio processor instance, the single channel sample FIFO, left and right side. Super simple. Let's do one of those. Simple MB comp spectrum analyzer. Let's initialize it with our audio processor. Our audio processor dot left, SCN audio processor dot right. Okay, the last thing we need to do is position it and make it visible. So in the constructor, plugin editor constructor, let's add it. Add it after the DSP GUI. Add and make visible. And then at the end of the constructor, let's just shrink the editor's height a little bit because it is kind of tall. All right, now we need to adjust the layout of the child components. Let's go to our resized function. Since we've been using those rectangle functions like remove from bottom, remove from left or right, to chop chunks out of any edge of the rectangles, we need to adjust the order that we do these chops in. So let's get rid of the code that sets the bounds of the IO controls. Okay, we get rid of that. We're still going to do our meter width area. That's all fine and good. Now we set the bounds of these guys from these meters. Left meter area, in gain control. Set bounds is going to be from the left meter area, and it's going to be removed from bottom. So we've got our column that has the left meter area, and we're going to remove a chunk from the bottom, and that's going to be the gain control. All right, we'll do the same thing for the out gain control. That's going to be from the right meter area, also removed from the bottom. All right. Now we need to remove a big chunk from the top of the bounds. I went with 70% of the remaining height of bounds. This is going to be the bounding box of the, this is before the tapped component. We can get rid of this. So we're going to go analyzer.setBounds, be bounds.remove from top, bounds.getHeight times 0.7. All right, and then we've got our tabbed component. That's from the very top. So we're going to have our analyzer sitting on top of our tabs. Let's take a look at that. This should make it all work. We should see our spectrum analyzer. Super simple. All right, we got our analyzer in there. Let's run some music through it. It's currently disconnected. There it is. There's our analyzer. Awesome. All right, save that and quit. Let's add a to-do and mark it as done. And we have one more to-do that's still on here. GUI design for each DSP instance. We did that when we made our customized GUI. So that's done. And let's add our to-do and mark it as done. Add spectrum analyzer from simple MB comp. All right, let's make a commit. Added spectrum analyzer from simple MB comp. All right, congrats for making it through all 40 chapters. I have a whole bunch more bonus content where you can learn to make this thing. In the bonus content, you learn how to make all this stuff, including all of the extra features you see here, like the pre-filter, the post-filter, the curve that gets displayed on here, reflecting the pre and the post-filter, which all respond dynamically in real time. There's also modulators, which you can use to modulate any of the parameters. For example, let's modulate our pre-filter cutoff using this guy over here. So we can see how this is modulating. You get to see all that stuff. You can change it from sine wave to a rising saw path, speed it up. We can also make it bipolar or make it unipolar, so it goes from top to bottom. Oh, my song finished. You get the whole new meter design. It's all available at pfmcpp.com. There's a ton of bonus content. There's also wet dry knobs for all of these guys. That's the wet dry stuff right there, the mix controls. There's mono and stereo versions. Right now, this plugin is operating in a stereo mode, but it can be operated in mono mode. That is a new feature that's added. The filter updating is thread safe, meaning your general filter and your post and pre-filters, you're not going to get any weird artifacts when you change the parameters. That problem is solved. You also get the filter response curve. You learn to build the tap delay module with feedback from scratch. We correct the filter response accuracy. We build the modulators. We build how to show the actual modulated value. Where did I have that? I think that was on the pre-filter. Yes, this thing right here. Let me speed this up so it's like really obvious. We build that functionality. We get the response curve to show modulated values. And then we add unipolar and bipolar switching to the modulators. The filter slider enablement based on the filter mode, as in right now we're in the cut mode. There's no gain for that one. But if we switch to the shelf mode, there's no slope control for that one. But this one does have gain. So that's one of the things we build. And then beyond that, we remove all data races because there's one or two of them in there. And then we also add the ability to save and load presets. So some pretty good functionality in the bonus content. Again, thank you for tuning in. I really appreciate you watching all the way to the end and supporting this course. I had a ton of fun making it. It was quite a beast to put together. There's a total of 108 chapters in the final version that builds this plugin. All right, thank you so much for tuning in. I'm Matt Cat Music, and I will see you in the next video.